there or not.
I see. Now I'm just saying prepare to live stream. So,
I can see that, yeah.
That's cool. I've never done that before.
I will also record here on my end each session, okay?
Yeah, and that's strange because I can hear myself with a little bit of delay, I guess. So something like. That's fun. I'm going to Skype and putting the link there if you want to. So.
Once again, Hossein, I didn't get what you said. This link is to look at what is happening.
It's the live stream on YouTube.
Okay.
I guess so. Just double checking if that's fine, then we can share with everyone else. That's fun. And I can hear myself. So you need to mute your YouTube.
Okay. Then I'm muting myself and also turning off the video.
Okay.
My video. Stop video. It's strange because when I stop the video, I cannot see.
Yes, you cannot see anything because I didn't share any screen. So this is like the default page, default screen that you can see.
Okay.
So it's live on YouTube, and I can see now on YouTube, which is nice. So live YouTube stream, which is nice because it can probably remove, alleviate a little bit of bandwidth from the Zoom if some people decided to go and then watch through YouTube. Okay, good. Also, we have checked the functionality and everything was in place, which is good. Also, Martin, would you please record individual sessions? Maybe a few minutes before starting, like one or two, and a few minutes after that, because then we can cut it easily.
Yeah, sure.
So, good. Okay, good. So it's going to start in like 10 minutes. So I can maybe share my screen to be ready for that. Just double checking. Can you see now my screen?
Yeah.
Yes.
Okay, good. And it's under presentation, right?
Yes.
Good. Martin, I have muted you, but you can unmute you, of course, whenever you like. But if we are not talking, maybe we can just all unmute ourselves.
Yeah, it's better.
So shall we start?
Yes.
Okay. I'm just double checking my headset.
How many people are participating? I cannot see.
Share my screen. Okay. Okay, great. Good morning, everyone. Distinguished guests, colleagues, and researchers. I'm Hossein Shokri, a research fellow of KTH Royal Institute of Technology. Together with Dr. Martin Barres and Professor Carlo Fischione, we welcome you to the second round of the International Workshop of Machine Learning over Networks. This workshop is at the end of our recent PhD course on the same subject, hosted by the Division of Network and System Engineering at KTH. This year, we have around 400 attendees across the globe, and we are really pleased about that. And I hope that you are all safe and sound. We have a 2 days program with 3 distinguished speakers, 4 panelists, and 5 special topic sessions. We cover recent advancements of the interplay between machine learning and networking. Such interplay becomes of paramount importance as we start to deploy state-of-the-art machine learning algorithms in communication systems, but also use networking backbone in the machine learning workflow. So as you can see here, there is a very complex interplay between these two very important blocks. In one way, heavy state-of-the-art machine learning models and algorithms, while working perfectly or over some clusters, they cannot work well on cheap noisy sensors with limited memory and computational resources that we usually have in most networking scenarios. In another way, limited communication resources, link failures, and network congestion may drastically affect the machine learning workflow and the accuracy of the final results accordingly. You will hear more about these challenges and potential solutions in these 2 days throughout many different sessions that we have. Here you can see the program. Today, we have 3 invited talks, starting from the interesting talk of Professor Dennis Gundes from Imperial College in London. We then proceed to special topics where a group of fellow PhD students and researchers present an overview of their chosen topic. We would then have a virtual poster session at 2 p.m. today and also tomorrow, where you can join their different rooms designed for different topics and discuss more on those topics if you want to. And of course, you're welcome to just leave some of those rooms and then join some others, walk through different rooms, of course. After the second invited talk by Vince, we would have today an exciting panel discussion with people from both academia and industry. The first day finishes by our last invited talk by Valley. We would also have 3 special topics and a virtual poster session tomorrow, as you can see in the program. The workshop will be entirely over Zoom, and I would like to say a few words on logistics. Attendees are muted by default and cannot unmute themselves. Also, they cannot use the camera, and the reason is we want to save the bandwidth and prohibit any lag in the streaming of the videos. If you want to ask questions, you can use the Q&A functionality of Zoom. And if you wish to speak and use your mic, you can raise your hand over Zoom and the organizer will unmute you. But of course, this would happen after the talk. And if you prefer not to talk, still you have a question, of course, you can write your question down again using Q&A functionality. We have disabled the chat for attendees, but we use that for the announcements. So I would suggest you to keep an eye on the chat box just to see the announcements. The poster session will happen on different Zoom rooms, as I already said, and you can find the links either on our website, but also in the chat prior to that session. We're going to provide that. We have also a live stream on YouTube, and the link is provided already in the chat. Without further ado, we can start the first invited talk. So Deniz Gündüz is an associate professor in information theory and communications at Imperial College London and the director of the Information Processing and Communications Lab. He is also an associate researcher at the University of Modena and Reggio Emilia and held visiting positions at the University of Padua and Princeton University. He is the area editor for the IEEE Transactions and Communications IEEE JSAC Special Series on Machine Learning in Communications and Networking, and also serves as an editor of the IEEE Transaction on Wireless Communications and IEEE Transactions on Green Communications and Networking. He is the recipient of the IEEE Communication Theory Technical Committee Early Achievement Award in 2017, ERC Starting Grant in 2016, IEEE Communication Society Best Researcher Award in 2014, and many other Best Paper Awards from top conferences. He is a distinguished lecturer for the IEEE Information Society this year and the next year, and he will give us his lecture on machine learning in the air. I'm very looking forward to his promising talk. Deniz, you can have the floor and share your screen whenever you want, but still you have a few minutes before that.
Hussein, could you promote Deniz to the panel? I cannot do that.
Okay, I'm on it. So I'm just stopping sharing my screen. Okay, allowed to talk more, promote to panels. Hi, Deniz. You can unmute yourself and activate your camera whenever you want.
Okay, hello. So let me start sharing right away. It says the host disabled attendee screen sharing, so probably you need to.
Okay, let me see. Ask to start video. Do you have the permission now?
Okay, let me try.
Yep, I can see you at least now.
Yes.
How are you?
Disabled. Let me try again. No?
No.
Screen sharing is still not possible.
Just a moment.
Should I try to re-log in or?
Well, I can make you host, but and then definitely you can share your screen. So let's do that.
Okay. Yeah. Okay. So let's see. Yes. Okay. Is it fine now?
Yes.
Yeah.
Okay. Perfect. Should I wait until 30?
It's completely up to you. I would suggest waiting a few minutes.
Okay.
And in the meanwhile, if anyone has any questions, you can raise your hand or ask in Q&A. Martin, just in case, can you please unmute yourself if you're not talking? Sorry.
There's one question. Do you see the pointer, my mouse pointer?
Yes.
Okay.
Yeah, we can.
Yeah.
And if you want to write, of course, you can do that as well, but probably going to be hard with the mouse.
Yeah, no, it's just PowerPoint. So
Okay.
Okay, so let me start with the, it's almost 30, so I can start with the generic, the introduction. So first, thank you very much for the invitation. So I think it's going to be a bit interesting to do this kind of online workshops, but I believe there are going to be more and more of these, and we are all getting used to probably both attending and giving talks at these workshops. So what I'm going to talk about, let me give a very kind of brief synopsis of the talk, just in case you, now that, you know, everybody's at home, you know, you might lose interest, or you might have your kids come into the rooms, which might happen for me, by the way. So what's the kind of very short summary of this talk is that, so I will argue that the next big challenge in machine learning today is to extend the success of machine learning algorithms to network of agents. And when particularly these network of agents are distributed physically, and which means that they will have to communicate with each other. So I kind of find this very similar to kind of the development of intelligence for humans, that we probably first developed our brains, learned to kind of interact with our environment, develop tools, etc. But then kind of the next big step came when people developed language, and they started kind of communicating and kind of distributing this intelligence and what they learned among each other. But this was also mainly limited to their vicinity. And then the second, maybe biggest step forward came when we developed writing, that we managed to communicate not just with our physical neighbors, but also across time in longer distances. So these all show the importance of communications when we talk about learning. And I believe that in machine learning so far, obviously there are many big successes, but this communication aspect is something we are just starting to think about and maybe learn about. And we, especially as people from the communications side of things, have, I believe, a lot to say about this. And the main focus, of course, this is a very general topic, distributed machine learning in general. But the main focus of my research and this talk is going to be on when machine learning meets wireless communications, when these agents are somehow connected through wireless links, either during the training stage or during the inference stage. And the particular, of course, focus is on the wireless network edge. So these devices at the very edge of the network, typically connected to wireless links. Okay, so the first, of course, acknowledgements to my students, postdocs. So this is some of our group members, not all current members, of course, but either I will talk about some of their work today, or some of the ideas that I will talk about are thanks to them. And of course, our funders. So this is basically, we are Information Processing and Communications Lab, located at Imperial College London in London. And you can see also more kind of about our research in our group website. Okay, so we can all agree, I guess, that the success of machine learning can be attributed to three major factors. One of them is, of course, the massive data sets that we collect more and more data these days, and we can store more data, process more data. And of course, the growing size and complexity of models that we try to learn. And more importantly, the enormous processing power we have today, that we can process massive data sets and complex models. So we can kind of combine the two and come up with this kind of complex models based on huge data sets. Of course, the trend is to kind of increase both the size of the data sets and the complexity and the size of the models. But even though the processing power is quite impressive, what we have today compared to years ago, even a decade ago, the scale, the trend of how much the processing power improves over time cannot meet the growth in data sets or the models. So the challenge is that today, many of these huge models or the big large data sets we have, we cannot process them on a single machine. So of course the solution for that is to parallelize, somehow distribute these machine learning algorithms. So now many machine learning algorithms are actually parallelizable. So that is already kind of a big benefit. So we can now exploit the resources, computational resources of many machines. and somehow, scale, hopefully, the processing speed linearly with the number of workers that we use. But of course, it's not as easy as it sounds, even though these algorithms are parallelizable. The problem is that when you scale things to many machines, of course, now these machines have to communicate with each other. So in the kind of easy, let's say, setting, if these are in a kind of big server farm, so they are physically next to each other, still, you might have maybe wired connections, but still you need to develop some communication algorithm that enables this distributed learning. And typically what people observe is that when you increase this number of worker servers, the processing speed does not scale linearly as communication becomes more and more bottleneck. And moreover, of course, there's the challenge that typically these servers, especially in the case when maybe you are using, let's say, computational resources like Amazon Web Services, like that are distributed physically, and these servers might not be homogeneous, and you become kind of limited by the slowest of these workers. So now both kind of the communication and the computation speed becomes a challenge. But there are also kind of even more challenging cases where communication maybe, let's say, is more essential and more challenging, is when the data that actually we collect is distributed across, let's say, nodes on, for example, an IoT network. So we are adopting more and more IoT devices, collecting more and more data through these devices. So now in this case, the data is distributed intrinsically. And moreover, so the decision making, the processing also has to be distributed. So many of these devices, let's say autonomous vehicles, drones, etc., even mobile phones, have quite powerful processing power, but they are distributed. Again, now we need communication to somehow orchestrate the processing across these devices. So what is the kind of the current convention is that we collect data across these edge devices and somehow offload this data to a powerful central, let's say, cloud server, where we can run whatever processing power we want and then train a huge, very complex model. But this approach has its limitations. And what are these limitations? First of all, if we talk about particularly the inference phase, so when we actually want to make decisions on our data, so that there are typically in many applications latency constraints. For example, if you want an autonomous car to make a decision about some people on the streets, about its environment, and take actions on that, you cannot basically allow many vehicles to jointly kind of exchange information, etc., over long delays. So the delay of such kind of distributed decision making becomes a bottleneck, is a serious problem. And there's of course the growing privacy issue. So we can, for example, harness the photos taken by all the mobile phones in the world to come up with the best image, let's say, image vision detection algorithms, which is currently happening, but people are getting more and more concerned about this. So we don't want to actually offload our private information to some untrusted cloud server for even if we want to kind of use that powerful learning model. And then in general, there are of course the issues of when especially these communications are taking place over wireless links, the limited bandwidth and power. So this is particularly an issue when the information content of these data sets are limited, in the sense that you collect huge amount of data, but maybe there's little to learn from them. So offloading huge amount of data to a edge server or a cloud server might not be worth the kind of the amount of learning you will get from this. So in all these cases, basically the communication becomes an issue. So we need to kind of harness the processing power and the data distributed over a network through some distributed intelligence. Okay, so I guess it's more or less clear that when we have in many cases agents distributed physically, so they want to learn together, and so they need to communicate. But so what's the problem about this? So we already know how to deal with communications. So even in the case of these links being, let's say, wireless and hence unreliable, we already have very good communication protocols. We have error correction codes. We know how to compress data. We know how to do multi-access, random access, radio access protocols, so on and so forth. And especially, for example, in 5G, we even, kind of extended our vision to include, to kind of focus our network design not on just like particular type of data and data rate and reliability trade-offs, but now our networks are even more flexible to have a much higher degree of freedom to trade off latency, reliability, rate, or the resources that we have in the network. So the argument is that, so is there something really fundamentally interesting from a communication perspective? So the statement that, yes, the current communication systems are not designed maybe with many typical machine learning applications in mind, but can we just overcome this simply by playing with the parameters of our communication networks and operate on whatever the required point on this multidimensional trade-off curve? So maybe the main technical message of this talk is that this is not the case, because there are kind of interesting requirements and settings stemming from the particular learning applications that actually says like this approach completely separating the communication network design and the machine learning algorithm design would be strictly suboptimal, and we have actually a lot to gain from the joint design. And this gain can be particularly significant when we are interested in the machine learning algorithms, which are basically the type of performance measures we have for machine learning algorithms. Okay, so kind of to briefly summarize what I have said, and maybe what I will go into more details, is that machine learning algorithms, communication protocols are currently designed separately, but of course communications, especially in the wireless setting, introduces not just delays, which is of course an issue, but also errors, so which are often ignored in the machine learning literature. So I said that the current kind of biggest achievement of the machine learning algorithms are more about centralized processing, but of course I have to say that there's already a huge literature that talks about this kind of communication bottleneck of distributed learning and how we can reduce the communication requirements, the amount of communication, etc. But I have to note that a majority of those works consider error-free channels, maybe rate-limited channels, but they do not really take into account the kind of the wireless channel imperfections that we know today, so that we know very well. And so the goal of this talk, as I said, is to somehow look into how we can jointly design these two aspects. And if you want, maybe we can call this as like machine learning on the physical layer. So how we can exploit communication and coding theoretic tools for the physical layer to speed up or to improve the performance of machine learning algorithms. Okay, so the talk is actually organized into more or less two parts, and because these are typically require different type of processing. So one of them, the first part, I'm going to talk about distributed inference. So here from a machine learning perspective, basically the assumption is that I have the resources to do some offline training. So let's assume I have some neural networks or whatever trained, but now I want to somehow implement them maybe over the network edge, over possibly wireless links. In the second part, I'm going to talk about distributed training. So this is that we don't have any network train model yet, but we have the model we want to train in a distributed fashion. So there will be either the data is distributed, and then somehow these can be distributed, or centralized, but the processing can be distributed, so on and so forth. Okay, so the distributed inference at the edge. So as I said, let's assume, you know, there are these devices, like in the picture here, autonomous car. You can even, you know, have a very powerful neural network model embedded on these devices. So let's say they might even have so their own processing capabilities. But in many cases, it's possible that the correct decision that these devices can make might depend on data that is not locally available. So at the inference stage. So for example, let's say this car wants to take some action, detect pedestrians on the street or some kind of like something about the physical environment. It's possible it has all its sensors, it has the models, it has the processing power, but it's possible that some information about the physical environment that's available in a, let's say, nearby base station might be needed to improve the reliability of this decision. So in that case, this car still needs to communicate with this maybe an edge server, and the delay is a fundamental issue here, a fundamental challenge. Of course, there are maybe even a more kind of common case that would require communication is that many of these IoT devices that collect the data that needs to make a decision, but they don't have the processing power. Let's say there's a bike, you know, you kind of want to also make a decision about the physical environment, but the bike maybe doesn't have the processing power like an autonomous car. So it has to communicate with now a processing unit at the edge. And again, of course, the latency and the reliability of this communication is a major challenge. So we first started. We first thought, you know, how can we, you know, can we formulate a fundamental problem that, you know, somehow reflects these issues, and understand the interaction between, you know, the learning part and the communication part. So the formulation we came up with is basically a hypothesis testing problem, but now over noisy channels. So interestingly, this hypothesis testing has been studied, you know, for many decades. So a lot of, you know, things we know, but somehow nobody looked into it actually. What happens when you put a noisy communication channel in between, let's say, the observer that collects the data and the detector that makes the decision. Now, the setting that when we have, you know, we just have this kind of communication channel, and let's say the data is available to observers, so the detector is just making the decision. So basically, in the very simplest case, we can model this as a binary hypothesis testing problem. So let's assume this data observed at the observer UK comes from either distribution PU or QU, and somehow this, you know, this observer has to communicate over this noisy channel with some fixed bandwidth ratio. So it has certain number of channel users per sample. That's the constraint. And we want to make a decision at the detector. So now we can, for example, we can either look at the, you know, the trade-off. Now there will be, of course, two types of errors you can make, type 1, type 2. And we can look at in general the trade-off between the two, or as common in hypothesis testing literature, you can kind of limit one type 1 probability of error and try to minimize, maximize the error exponent of the type 2 probability of error in the asymptotic sense, when this number of observations and the number of channel users you are allowed grows to infinity. So this problem is actually, as one would expect, intuitively, is as a simple solution. So it says that the observer basically just should make a decision because it has all the data. So it's kind of in the best position to make the most reliable decision between these two hypotheses. And all you need to do is to kind of then communicate this one bit of information in the most reliable manner over the channel. So then your performance is a trade-off between the typical kind of the error exponent you would have when you make the decision at the observer, which is limited by this divergence between the two hypothesis distributions, and this kind of reliability function of the channel. So this is expected, as I said, because so we did not put any complexity constraint of the observer. So why not the observer should make the decision locally? So in general, basically, there's this kind of this separation is actually optimal. So you need to make the decision and then just communicate in the most reliable manner your decisions. And the main difficulty here is, of course, the complexity constraint is something difficult to model, to include in an information theoretic model. So typically, we don't have such constraints in the information theoretic formulations. But still, there's a more interesting scenario that's even, let's say, very interesting from an information theoretic perspective, is when the observer cannot make this decision locally. So it doesn't have access to all the information required to make this decision. So which would be the case, for example, when the detector has some information also it observes, this VK, and maybe the two hypotheses are about the joint distribution of U and V. Either these samples might be coming from some distribution PUV or QUV. So in general, actually, this is an open problem, even in the when the channel is error-free. But but we were able to solve this problem when we are testing against independence. So the alternative distribution is the product of the marginals. So again, in that case, we are able to actually define a single letter kind of information theoretic performance bound. And it says basically we need to kind of reduce some, take some features out of these observations represented by this auxiliary random variable W, and then communicate these features at the capacity of the channel. So interestingly here, in the case of testing against independence, you can prove that, again, communication and the learning can be separated. So you can operate at the capacity. So you design a channel code completely ignoring the hypothesis testing problem. But this actually does not generalize. So when this, if it's not testing against independence, we are able to prove that separation can be strictly suboptimal. So this kind of already tells us that this problem is even fundamentally is quite interesting, and you can have kind of more interactions between the channel, communication channel, and this kind of learning task. Here is hypothesis testing that will give you better performance if you can design the two jointly. Okay, so what is the kind of the practical version of this problem? So the distributed decision problem. So the application that we looked at is person re-identification. So this problem is a very popular problem in machine vision. So it's as follows. So let's say you have a data set of a database of images taken from of a certain group of people taken by different cameras. So these are completely different angles, different backgrounds. You have this database. And at some point, you get another picture for one of these people from one of these, let's say, cameras, and your goal is to basically identify whether that person is, like that image belongs to a person in your data set or not. So you want to say that, okay, this is the same person. Let's say here, this image taken, even though it's from a different angle, but you want to detect that these are actually the same person. So it's quite a challenging task. And of course, the standard approach is, so in this case, we are assuming that somehow this is a wireless camera connected to the cloud or to the edge processor through a wireless link. So the standard approach would be, take the image, transmit to the cloud as reliably as possible, and do your best re-identification baseline. So these are typically neural network algorithms, these deep convolutional neural network architectures, like let's say based on ResNet 50. And so you capture some features of the image and then do somehow some nearest neighbor detection, or there are other ways as well within your data set. But of course, now, again, intuitively, if we think about it, from also depending on our previous result, we know that we don't really need to send all the image. So we are not really interested in the image itself. So we don't care if we can reconstruct this original image at the cloud. All we want is to get the features that are needed to make this decision. So for this, so the first kind of thing we did is to design a task-based compression and channel coding scheme. So we said that, okay, so we have this limited capacity link from the wireless camera to the network. So we are of course assuming now that we want to make these decisions as quickly as possible. So we cannot use a very large bandwidth to transmit these images or features over the channel. So in this case, so what we do is that we first run a re-identification baseline, so get some features. Now, what we want is to compress these features to the rate allowed by the channel, which we will transmit reliably using some basically efficient channel code. But now we want to do this compression as efficient as possible. So for this, what we use is to first quantize this latent representation, and then we look at the entropy of these quantized bits, which we will later do some compress further using some arithmetic coding scheme. And the idea is to somehow trade off basically use and loss function that also takes into account this entropy that you get from after the quantization. So that gives you how much rate you need to transmit over the channel. But another scheme which kind of is motivated by the fact, that, as I said, that the separation approach is actually in general suboptimal, meaning that so if you just compress some features and send them using the optimal capacity achieving channel code is in general suboptimal. So for that, and we know that, so that's even suboptimal, even information theoretic in the sense of, asymptotic block length, etc. So we know that in practice, we don't even have asymptotic block lengths, right? We are limited by the bandwidth. And in general, this type of separation is definitely suboptimal. So we actually looked at in this work here, not any detection, any machine vision problem, but just to transmit images over a wireless channel. And actually, you can show that obviously, the separation is suboptimal, and we were able to actually design purely neural network-based joint source channel coding schemes that can beat the state-of-the-art, let's say, image compression codec combined with a capacity achieving channel code. So just kind of overcoming this limitation of separation can give you gains. And here now we are going to do that. We can apply the same idea for the transmission of the features, because the features now we can treat as some source, some information source that we want to transmit to the receiver over a wireless channel. And we, in general, of course, since the channel is limited, so we need to do some lossy transmission of these features. So we want to design a neural network type joint source channel coder to transmit these features. So the benefits of this, as I said, first of all, it improves the performance, but moreover, there's kind of an interesting side benefit, is the fact that this type of joint source, deep joint source channel coder, so this is also what we observed in this paper, is an analog communication system. So we don't limit ourselves to transmit, either to turn image into bits or even to transmit from a constrained constellation. So we completely, let the encoder to be free to whatever it wants to transmit over the channel. And this becomes since almost all the operations that you do on the neural network are similar to analog operations, you get an analog type of communication system rather than a digital communication system, and which gives you a graceful degradation. So meaning that if the channel quality changes over time, so you don't need to target a fixed channel quality. As opposed to in digital communications, if you want to do like a capacity achieving channel code, you need a very reliable estimation of the channel quality. And if for some reason what you experience is worse than your estimation, you will lose everything. So there's this kind of a cliff effect. Whereas this type of, in this architecture, when we use this kind of joint compression and channel coding scheme, even if the channel quality changes, gets better or worse, your performance, end-to-end performance changes gracefully. So here's some results. So if, for example, limit 128 uses of an AWGN channel at this SNR, here SNR is given at the bottom. And you can see that, if you look at the top one, accuracy, so basically, we want to see if the system is able to identify the correct person, at what rate. So we can see that here, so this is the digital approach, assuming capacity achieving channel code, even though it's only 128 channels. So we are quite generous to this digital separation-based approach. This is the reliability you will get, even if you are using actually a task-based compression scheme, basically compressing the features for the purpose of detection. Now, if you were to use actually compression of the image itself to transmit and then to do re-ID at the remote receiver, that wouldn't be even in this figure. So it would require huge amount of SMR, and at this bandwidth, of course. So these are two different kind of versions of this joint source channel coding scheme, and you can see that it's significantly better. And actually, at some, even at 10 dB, you actually achieve the performance as if what you would have if all the data was available to the decision maker. So you kind of completely overcome the channel noise. And of course, as you increase the channel bandwidth, you have more and more bandwidth, and these are still very, very short kind of block lengths. You can get almost, even at, let's say, minus 5 dB, you are as good as you would be if you had the data at the decision maker. And I said that another challenge typically in practice is when your device doesn't have the necessary processing power, or it's slow, so it would take a lot of time to do the same decision making, whereas maybe you have a much more powerful processor at the edge. So as I said, this is difficult to model from an information theory perspective, but we know, again, in general, of course, this type of separation would not be possible, would be suboptimal. So here, the typical approach is to do kind of this co-inference by splitting the deep neural network. So in the literature, what people do is that they train kind of this very, deep, let's say, ResNet structure, and then they say that, okay, so I divide it into two. So the device, let's say a smartwatch, runs only the first few layers due to its limited processing power, and the rest will be run on the edge server. So of course, what we need now is to communicate these features over the link. So typically people, this literature, they look into, again, error-free links. But they still need to compress. So they look at rate-limited links. So somehow, because this is actually a nice figure here, if you look at the data size of the features in the kind of this ResNet network, if the input size is this, you see that actually at the initial layers, you're actually expanding your space, so your data. So this is typically what this deep neural networks do. They first expand and then reduce the size. So if you can only do a few layers, you end up having to transmit a huge amount of data, even a larger amount of data over the wireless link. So typically the literature, what they do is that they use some sort of image compression tools, standard compression tools, typically based on image compression to reduce the size of that feature vector. Or there are some, basically in this work, they design some neural network based compression scheme for feature compression. But what we said is, again, motivated by the previous result, is that if you want to, if you kind of just look at how many bits you need to transmit, so this inherently assumes that you separate communication. So you assume that you actually have a reliable way of communicating these bits over the link. So otherwise, you need to take into account that it's some probability you will not be able to transmit the bits. So we said basically, so why don't we actually do this kind of joint source channel coding of these features, just like we did before? And now we can actually look at the joint complexity, of both the channel coding, so there's no explicit channel coding, but basically the channel transmission and whatever learning we do. So here again, what we do is that we combine the first layers, now take the features, but transmit these features using this kind of joint source channel, deep joint source channel coding scheme. Of course, to kind of reduce the complexity compared to our previous designs, what we did is to reduce the complexity of the encoder of this deep JSCC and transfer the complexity more to the decoder side. And if you compare with this kind of state-of-the-art scheme, so this actually bottlenet++ is a scheme that considers actually this kind of the noisy channel as well. And on top of it, we were able to reduce the on-device computation much more by using pruning. So pruning is a common tool in neural networks to reduce the complexity, because people have observed that actually many of the connections in a neural network, we can basically remove them without a big decrease in the accuracy. So that's what we did. If we kind of allow, let's say, 2% reduction in the end-to-end accuracy of the system, here you can see that is for a limited on-device computation of, let's say 100 megaflops, we can see that we can reduce the channel bandwidth significantly. So these are actually in the logarithmic scale compared to the state of the art. So this is again basically using this kind of pruning plus deep joint source channel coding feature transmission. So this again, so basically all these examples show that if you take into account kind of the physical layer, the reliability, the kind of the errors and the latency over the channel, you can gain a lot for the inference of kind of this type of deep neural networks at the edge. And we will probably need many more kind of interesting and intelligent designs, how we can do these things jointly. Okay, so this is more or less what I wanted to say about distributed inference at the edge. And now I will start the second part of the talk, where I will be talking about distributed training. So in distributed training, so the main challenge is that, so as I said, we have a huge amount of data and we want to train a model, a very large complex model. And now we cannot run this on a single machine. So the processing power of a single machine is not going to be sufficient to handle such complexity and data. So as an example, this DeepMind's AlphaGo, the famous AlphaGo result, was obtained by using basically running the algorithm, the training of this deep reinforcement learning algorithm on 1,920 CPUs and 280 GPUs, and for a very long kind of training time as well. So this kind of gives you the scale of the things. Of course, for such examples, maybe you're not so much limited about the time, if you want to just do once and then write a paper about it and do it offline. And all you need is basically an impressive result. But if you want to kind of scale these things and do these things, apply these things to many, many applications in parallel, of course, we need this algorithms to run, to be very reliable and to be very efficient. So the first kind of model for these problems is more on what I just said. So we have, let's say, a master server which has huge amount of data, but it cannot, process the data itself. So somehow it needs to harness the processing power of many different worker machines. So now, through some communication links with these machines. So but the main issue is that here, this master server has the freedom of, it can decide how to distribute the data and tell the workers what type of computations to do. Another very interesting and very relevant scenario from a wireless networking perspective is this kind of federated learning setting, is when actually the data itself is distributed. So now the devices have acquired their own data, and either because of privacy concerns or the limitations in bandwidth or power of these devices, so they cannot, they don't want to send all the data to the central server, and somehow they want to train a joint model. And in general, also for this setting, there can be different kind of models. And I think it's a kind of very, very rich application area for also from a communication perspective. And so I will be talking about today mainly this type of centralized, which is called a parameter server type architectures, where basically there's this one central parameter server that orchestrates the learning across these different machines. But you can also have the kind of more kind of decentralized setting where these devices will communicate through device-to-device links rather than assuming the existence of this kind of centralized parameter server. I think, yeah, both are very interesting scenarios. Okay, so let me first give a very brief kind of summary of what is the distributed learning problem. I know that there will be many more kind of interesting, even much more technical, detailed discussions on this during the workshop. But just for kind of completeness, let me give this kind of very basic overview. So the goal is that we want to learn a model, this kind of parameterized by this theta, across this data set. This we denote this data set as D. So it consists of many data and labels. So this here we're assuming a supervised learning setting. So we have data, labels, XY pairs. And so we want to find the model theta somehow that minimizes this kind of empirical loss, this function L that's specific to the application across this data set. And we know that in general, this can be solved as a common way of solving this type of problems is gradient descent. So what we do is that we kind of try to learn this parameter vector in an iterative way. And at each step, so we have a current model and we kind of update it along the gradient descent direction. And so we at each iteration, basically, we need to find this gradient across the data set. So which direction we need to update our model. Now, the nice thing is that, so this type of, gradient descent type of application is very much amenable to distributed implementation. So all we need to do is to distribute the data set across these workers. So we can give one chunk of the data set, let's say, to each worker. Now, at each step, all I need is to, to compute this kind of full gradient, let's call it. I can retract partial gradients from each of the workers and simply take their average to recover the full gradient, and this master server can update now the model along the kind of the gradient direction. So this is great, but as I said initially, there's of course, due to this kind of communication required between these workers and the master server, communication becomes the kind of main bottleneck. So there are many methods to overcome this in the machine learning literature. This is just a one slide, very extreme brief summary of that very interesting literature. So one of the approaches is assumes gradient compression. So the idea is to somehow, instead of sending the gradient vector as it is, so we can try to compress it into as few bits as possible. So there are many different algorithms on this. The second approach would be gradient sparsification. So instead of compressing it, like into bits, the assumption is, I can actually remove many of the insignificant entries and then send a very kind of reduced dimension gradient. So it's just another way of compressing the gradient information. Or another approach would be to reduce the communication frequency. So instead of, computing based on maybe one batch of your data, in the case of stochastic gradient descent, implemented in a distributed manner, what we can do is then we can increase the batch size, so we can do more computation locally, which means that you will have less communication kind of per computation, or you can even run multiple kind of local iterations. So you can do multiple iterations of a stochastic gradient descent, update the model, and then instead of sending the gradient, we can send the model update. So it's kind of all different methods. You can use a combination of these as well. But there is another challenge that is kind of orthogonal to the kind of the amount of communication that we need to have from the workers to the server, which is about the kind of the straggling behavior. So the straggling behavior, the idea is that, so we need these gradient estimates, so these local gradient estimates from the servers at the parameter server to take the average. Now, the challenge is that, typically in practice, these servers, even if, they might have kind of similar processing power, but for various reasons, they might have different inhomogeneous response times. So it might take them some random amount of time, maybe averaged across some mean, at every iteration. So you typically don't know exactly how long it will take them to kind of compute these gradients. Moreover, now that, like they need to communicate these gradients to the network, they're also delays that might be due to communication over this network. Now, which means that, in this kind of implementation, if I want to kind of recover the full gradient at each iteration, this means that I need to wait the response from every worker at each iteration. So I will be limited by the communication or the computation speed of the slowest so-called straggling server. And this may lead to a significant slowdown in the process. So we might actually lose completely the gain that we were expecting from this distributed parallel processing across a network of devices. Okay, so there are, again, many solutions that have been proposed in the literature. I will mainly talk about kind of how we can use ideas from coding and communication to solve this problem. So so one approach is to introduce backup servers. So now we can actually have more servers, and instead of maybe, we divide the data. And remember, so in the case of stochastic gradient descent, so each worker, instead of computing the gradient based on all its data, it just chooses a batch. So it basically computes an unbiased estimate of its local gradient and sends it back. So now I can have, I can introduce more servers, and instead of hoping to get result from all of them, I can only wait a certain number of them. So in a way, I can ignore a slowest, bunch of the servers. So instead of being limited by the slowest server, now I will be limited by the kth, like the nth slowest server. So this will definitely provide some trade-off, but this is based on, in a way, the idea is to introduce like more servers, and which brings some redundancy, right? But in a way, we can do something a little bit, let's say, smarter. We can introduce the redundancy at the worker level. So what we can do is that we can say that, okay, since the workers have this kind of different processing speeds, I can actually try to exploit the faster servers to compensate for the slower ones. So to be able to do that, I need to introduce now redundant computation. So instead of, for example, instead of giving one chunk of data to each of the servers when I want to get a full gradient recovery, not necessarily in the stochastic gradient descent setting. So let's say normally I would give them one piece each, and I would wait all three to respond with their gradients. Now instead, I'm actually giving 2 pieces of data to each. So now each piece of data set is replicated at 2 of the workers. And I basically say that, okay, try to compute both, gradients based on both chunk of data. So you get 2 estimates. And then, so if you complete the 2, then send me some linear combination of your computations. And these linear combinations are kind of fixed in advance. And for example, in this setting here, so I have these kind of linear combinations, and you can see that actually, if this worker does not respond for some reason, so it's, let's say, struggling at this iteration. So I have now these 2 linearly combined kind of gradient estimates. And you can see that there exists some linear combination of the 2 that will actually give me this the sum of the gradients, and which is what the master server is interested in. And you can actually verify that this is the case for any 2 out of these 3 servers. You can always recover this full gradient. Now, so what we did here in principle is we kind of increase the computation load, which is denoted by this parameter R. So here it's 2, to compensate kind of for the slowest servers. But of course, this required us to design this, special coding scheme, which basically, like any combination, any let's say k out of these n servers is kind of good enough to span kind of this full gradient vector. So this is quite a nice idea. And actually, they have also in this paper where they introduced this, they also showed as an example that, like this type of, full gradient, this gradient coding type of computation actually gives you better reliability compared to ignoring the straggling servers. If you just, like kept every time just the few best ones, so you wouldn't get as good. Of course, this depends. So I have to kind of make some conditional statement here that this might not be the case for all types of applications. Okay, so it turns out that you can do even more interesting type of codes and this kind of trade-off between reliability and the communication and the computation across workers for more kind of specific, especially a linear regression type of problem. So what happens is in the case of linear regression, now I can write this kind of squared error loss function, and the gradients now can be written in this vector form. So here basically this X is the data matrix, stacked data matrix. So each one you can consider as one data sample. And so now every iteration, I need to compute this gradient. I want to compute this in a distributed manner. But if you notice, this is X transpose Y is just a function of the data. So this is just, the data samples and the labels. So we know this from the very beginning. So we need to do this just once. And so what we need to really compute every time is this multiplication. And this is a matrix-matrix multiplication. And we can write this matrix-matrix multiplication in this form, which is an outer product. So basically here, if you can see, so this is now, so I can divide this into kind of sub matrices, x1, x2, xk, k matrices. And I can write this multiplication as a sum of these k multiplications. So now, which means that if I can ask, a different server to compute each of these multiplications, I can simply add their results. So it's a nice way of distributed, implementing distributed matrix-matrix multiplication. And furthermore, if I looked at, the same problem as you see here, X transpose X theta T minus X transpose Y. So here we said that this could be done once, but moreover, we can actually see that this matrix-matrix multiplication is also just, is constant throughout the iteration. So I can actually also do that once. So now I get this W matrix, matrix vector multiplication. And basically all I need to do is to do this computation every time in a distributed way. And now here it's even simpler kind of to see a way to distribute it. So this is just so I can actually just divide this into, again, like sub matrices. Let's say here I divide it into two. So one way to parallelize this easily is to just divide this W into kind of 3 parts. And each one, each worker could do just, W1 theta T, W2 theta T, W3 theta T, and I would just get the result putting the 3 together. But if I want to introduce some redundancy to trade off between, fast and slow servers, I can actually divide into 2 instead. So now each worker needs to do more computations because they are kind of multiplying it a larger dimensional matrix rather than 1/3 of W. They're multiplying 1/2 of W with theta T. But now, I can assign this W1 plus W2 to the third server. Now I have this redundancy, right? So this is like a linear code to give me redundancy. So any 2 out of 3 will give me my required result. So this was actually the first kind of time that this type of coded computation idea was introduced for this kind of regression problem in this paper. And there are many extensions on that, which I will also talk about in a bit. So now going back to this matrix-matrix multiplication, one of the nice implementations of this is actually through this Lagrange coded computing. So here, like what we do is we divide this matrix that we want to compute into this kind of R groups. Now each one, let's say, the xkj is the jth element in the kth group, and we form this R structurally identical polynomials using different elements of this kind of R parts of this matrix. So this is like a Lagrange polynomial. So this is like this, if you remember if you know about polynomial coding in general, basically this is the same idea. And but the idea, so this is the kind of, we can interpolate the way, we're interpolating a polynomial using kind of these different values of it in different roots. So we choose these arbitrary points. And then what we are doing is actually, what we will do is that we will actually require each worker to compute this function that these polynomials at different arbitrary points. And by kind of collecting a subset as sufficiently enough of them to interpolate a desired polynomial will be enough to then we will recover the polynomial. From that, we will basically recover what we want to compute. So here, so these are the polynomials we form, but this is the polynomial that we want to recover, which is actually the result of these multiplications. So they get this kind of WKs, FKs, which are linear combinations of the data. So they do the multiplication of this kind of coded data. So instead of now having the data itself, they're having the coded data. They're multiplying. And so this H polynomial has this degree to n over r minus 2. So I need, one more of these evaluations of this HC polynomial to be able to interpolate that. And once I have HC, if I know HC at the master, I can now compute these different values of this H polynomial at different alpha I values that we initially fixed. And summing them will give me exactly the computation that I want. So this is kind of using this type of polynomial coding ideas to have to implement this distributed computation. So here there's an example, but I won't go into the go through that in detail. But the idea is, again, so basically we have this kind of now we send to the workers coded data. We centrally did this coding, which is just a kind of a linear combinations of the original data vectors. And each worker just computes all these three, form this kind of one result as a kind of linear combination of all these three computations, and sends that result once it's completed. And as long as, if we have, so the degree of H is in this particular case is 3. So this is 2, but I need to get from, response from 3 workers. So if these are, like struggling, doesn't matter. As long as I get 3 results, I can interpolate H, and then I can get basically what I want, the full computation. So now this is, in general, this kind of coded computation, this especially in this kind of linear coding schemes are quite interesting, quite nice. Again, using the ideas from coding theory in distributed computation to overcome the struggling behavior, either because of the inhomogeneous computation times or some inhomogeneous delays over the communication network. But there are, like 2 limitations of this approach. So one of them is that, so this kind of the redundancy that we introduce, this R parameter, it determines the recovery threshold, right? So how many, like workers that we need to be able to recover. But this needs to be done very carefully, and it requires actually the ideal kind of optimal choice of this will depend on the computation speeds of the workers, which we might not know. For example, if I set R is equal to N, that everybody does all the computations before responding. So this means obviously now I can recover the result from a 1 worker. So each worker is doing the whole computation. So it's great. The recovery rate is very low, the recovery threshold, but of course, I need to wait, a lot for each worker to compute all the computation. So there's this trade-off, and in general, there's a chance that I'm doing over computation. If I fix this R basically too much, I end up waiting a lot, even 1 worker to complete it, even the fastest worker to complete its computation. Right? So there's kind of over computation problem. Another problem is that, like here, the assumption is that, if a worker is struggler, so it doesn't send me anything, I don't need its information, I completely ignore its computation. But in practice, if we actually, simulate these type of systems, what we will see is that, yes, these workers might have different processing speeds, but they are not significantly different from each other. They're typically, centered around some average computation, but some are a bit higher, a bit lower. And in that case, basically, we are not utilizing at all the computations done by this kind of relatively slower servers, so which are called non-persistent stragglers. So they're not doing anything. So they are just a bit slower. So to overcome this, what we introduced is to kind of trade off computation and communication, in the sense that, instead of requesting each worker to do all the computations before communicating, we will allow them to send multiple messages. So if you're a very fast server, I will allow you actually to send the result of your first computation when it is completed. And if you later run more computation and get further results, you can send another message, which is not allowed in all the kind of the previous implementations. So here, for example, I can give like 3 different computations, and the server computes first one, sends it, second one sends it, this one sends its first computation, which is just the third one, and I'm done. So I don't even need anything. But here, as you can see, so I get some partial results. So this wouldn't be possible in the kind of this coded computation framework. So for this, the one thing that we kind of, the one of the results that we had was, instead of having this, remember, so we had before R polynomials, structurally same polynomials, but each worker was basically computing one value of these, like different polynomials, and then sending a linear combination of these results. So now we form instead a single polynomial of degree, n minus 1. And now this H polynomial, the multiplication is degree 2n minus 2. And I send to workers as before, again, the computation redundancy is R. So I send R different coded, vectors to be computed at this polynomial. So these computed, these coded vectors are, different kind of evaluations of this polynomial fz at different points, are different points. And each one basically does now this multiplication. So they get this kind of computation of fc at different values. When they do the computation, basically they get different evaluations of h at different r points. And I allow them to send each one as soon as they compute. Now, the difference here is that now this H polynomial has a much higher degree than before. So our kind of recovery threshold, if you think about it, is higher. But instead of getting only one computation from each server, I can get actually multiple, up to R computation. So if you're a super fast server, you can send me R messages. So I can get R different evaluations of the same polynomial. So here, for example, now I have, I need to collect this 11 computations, and I can collect it as any combination. So of course, this is now much better, especially if these servers are, not completely, regular, non-regular. So even not some very slow, relatively slower server can give me a certain number of evaluations. And here, if we actually look at the average completion time with some underlying assumption on the, let's say, the computation, this computation speed of the workers, here you can see that this kind of multi-message version of, so this is what gradient coding would have. So the Lagrange coded computing is much better. It has much kind of lower, better, more efficient recovery threshold. But here, by using this multi-message aspect, we get actually even much faster. But of course, there's the trade-off. The trade-off is that we are introducing more communication in the sense that, the total number of messages that needs to be sent to the master is higher. But on the other hand, we have to say that actually, these messages are not, so before all the workers do same number of computation, and they all send as soon as, they complete all the computation. If they are similar computation speed, they might end up actually sending all simultaneously. Whereas now here, these messages might be actually more kind of staggered across time. So here, for example, average completion time, as you see, is much lower with this Lagrange multi-message Lagrange coded computing. And here you can see also, for example, increasing R for the traditional, it is kind of the original Lagrange coded computing. As you increase R, at some point it's actually hurting you. So you need to wait more for each server to respond. But of course here, now the communication load, the total number of messages can be higher. Now, of course, the real kind of trade-off will depend on what kind of communication protocol you do, right? So this increasing number of messages, what is really the impact of it? If it's slowing a lot to communication, this might be worse. But actually, you have a communication protocol that kind of take care of these things in a more efficient manner. Maybe it's going to be much better in terms of the end-to-end computation time. And here, basically, what I'm showing you is that this approach, so we had like one polynomial compared to R polynomial. You can actually have anything in between. So there's a kind of so our scheme has this kind of very general kind of spectrum of different implementations. Okay, so let me see. So I have about half an hour. So I will briefly talk about this another aspect. So as we said, like if we are doing this kind of linear regression problems, if I do this computation initially, this matrix multiplication once, now I can have this kind of matrix vector multiplication, which I can, easily distribute. the interesting thing is that now if I don't get some results, so, okay, so I can do the coding to kind of target full gradient recovery. So it's easy. I can use any kind of MDS code, you know, like linear code that allows me the recovery of the whole computation of, you know, K out of N, etc. But if I lose something for whatever reason, let's say I fix a certain time, I only wait at the time, whoever responds. If you don't respond, I kind of ignore those servers. What I'm going to miss is actually parts of the gradient. So I'm not, you know, not losing, you know, like some computations of the gradient vector, but actually I'm getting kind of just some entries are lost. So I'm getting a partial, you know, gradient recovery. But we know from for example, this stochastic gradient descent literature is that I don't really need actually full gradient to kind of get a, you know, convergence result for, you know, gradient descent based stochastic gradient descent. So I can actually trade off now. So instead of targeting a full recovery, like in pretty much all coded computation literature, we can actually trade off this kind of reliability. So I can allow partial recovery by, and at the end, you know, in return, speeding up of each iteration. Now, you know, very simple kind of setting here. Let's say I want to do this kind of WX matrix multiplication. I divide it into 4 parts for 4 workers. Computation load is 2. Either I can use this kind of MDS coded thing that, you know, any 2 out of 4 will be sufficient. Here, if I do this code, you know, each worker computes, you know, these multiplications, these linear, you know, like combinations. And if I get 2 workers out of 4, I will be able to kind of recover the result. Or I can just, you know, uncode it. So each give like 2 parts to each, you know, like, and I tell them, okay, compute one, send the result, compute the second, send the result. So it's again, multi-message. And I will stop, for example, I can stop, you know, like even either I try to recover the full gradient, or I can stop, you know, recovering 3 out of 4, whatever. Now our code is something like this. So we are saying that now I design a code which has lower degrees in the, so for example, here they first compute, you know, like 1 row each, and then some, you know, linear combination. So the idea here is that, you know, like they will all return as soon as they compute. But for example, if worker 4 is for some reason struggling, now you can see that, you know, like I get kind of different linear combinations of W4, which I can recover, you know, from, you know, if I, for example, if I get W2 and this one, I can get W4 as well. Or if I get W3 and this one, I will get W4. So this kind of adaptive redundancy. So the motivation of this is that, you know, it's unlike in a kind of erasure coding setting where all the erasures are equally likely. Here, because of this kind of staggered computation, so there's an order of computations, these messages are not erased with equal probability. So that's why I basically need to design a code with an increasing degree distribution. So that's why, you know, like that's what, so it's a very simple, of course, implementation of that. And here you can also see, for example, what kind of result scenarios. Let's say, you know, here Ni is the number of workers that completed I computations. You know, you can have, for example, just one, or let's say all of them computed 2, you know, in the first row, 2 computations, or, you know, in the last row, you have like 4 servers computed 1 computation. Sorry, one computed 4 computations and 1 computed none. Yeah, exactly. So anyway, so for all these kind of different scenarios, we can actually have, you know, we can look basically how many of those scenarios each code can recover. So we can see that actually this partial code will do, you know, at least as good as, you know, all the other codes, but better in many scenarios. So there are many scenarios that it can recover full gradient that others may not. But more kind of impressively, if we actually say that I'm okay with recovering 3 out of 4 gradients, now our code is also better, you know, even better than these 2 alternatives. And this, of course, reflects in the, you know, if I kind of use this tolerance parameters of what percentage, you know, like I am okay not to recover. Now you can see that, you know, average completion time of our this kind of partial gradient schemes becomes much lower. Again, of course, the communication load compared to this MDS coded kind of scheme is higher, but there's a trade-off. So, and it actually also reduces if I play with the tolerance. So this gives, let's say, another kind of dimension. In a way, I'm using this kind of computation, the coding idea to play with the trade-off between communication and coding. Okay, so this is more or less about this distributed training. But here, if you notice that the kind of motivation was slightly different than what I talked before. So the originally I was talking more about the physical layer aspects, how I would use coding to overcome the error in the channel. And here I use kind of again the ideas from coding theory, communication to more overcome errors, not necessarily due to communication, not from definitely physical channel, but could be from communication network, but also, for example, for the processing speed. So that's another kind of dimension in that we need to take into account when we talk about machine learning problems. So now in the federated learning, I will go a little bit back to the, that very briefly, this kind of physical layer aspect. So as I said, in the federated learning approach, we have many devices, each with its own data set. They are trying to learn a common model. So the way it's done, so we use basically this kind of distributed stochastic gradient descent approach, but, each will compute either a gradient, or if they do multiple iterations, they will compute some model update and then send it to this kind of central server, which will update the global model, broadcast it to the devices again, and they will again do local computations and so on and so forth. So they will, this way, instead of sending their data to the server, they will communicate through this kind of either gradients or model updates. So this is kind of motivated for privacy. Of course, there are kind of recent work that questions how much privacy actually this provides you. But okay, so now in the case of, in the machine learning literature again, so they typically look into either rate limited links, etc. So they don't really consider these devices to be in a shared wireless medium. So this is more for us, the motivation is that if, for example, these are mobile devices that are in the same cellular environment, and they need to now for this kind of uplink sending their model updates, if they need to share the wireless medium, how can we do it? So we know that when you actually have multiple devices, we have developed all sorts of different resource allocation, radio access network protocol. So how should we kind of tweak those for this type of problem? Because here now we don't really care about the rate of the communication. We're interested in more kind of the end-to-end accuracy of the model. So we looked at a simple kind of scenario where, if you have a one cellular system, many devices, you're training, you want to train this kind of a model through federated learning. So we said that if you just orchestrate this through the base station, one macro base station, all the devices need to communicate with this device, macro base station. Of course, they need to transmit maybe with higher power. So they are all sharing these resources. And alternatively, what we can do is actually we can introduce some sort of a hierarchical network architecture where we have this kind of small base stations, and actually which they can do some local learning, and then only once in a while they can update the model at the base station. So this kind of this hierarchical structure. So this will improve it improves both the learning kind of accuracy, but also gains, of course, in terms of the communication. So here a very simple result, comparison for CIFAR10 image classification. You can see that. So the baseline is if everything is centralized, and here federated learning, if it's just through the macro, everything is orchestrated. You can see that it's slower and the final accuracy is lower because they can have much less they're more limited than, let's say, by the furthest user from the at the cell edge. Whereas if I introduce now this kind of local learning mechanisms, so it becomes much more efficient, much better, basically. So this is kind of a way to show that, an example to show that how this kind of resource allocation has to interact, has to take into account the machine learning problems specific needs to solve the optimization. Now I will go back to kind of the type of model that I had initially, where I again introduce the physical layer aspect. So here in the, and I think it's a kind of a nice, interesting observation and a very kind of significant illustration of how machine learning and wireless channel would interact. So as I said, in this federated learning approach, at each iteration, each device, let's say, computes a gradient estimate, and they need to transmit these over this kind of shared wireless medium to the parameter server, which will eventually take average of these estimates and update the model. Now, again, the standard approach would be that, okay, so let me use some kind of, communication scheme, some radio access protocol, some channel code modulation. So now each device is given some resource, channel resource, so they can transfer at a certain rate. So which will require them to, compress their gradients to this rate, and then communicate as reliably as possible. And the parameter server does the, update. But this is, again, this is a separation-based approach. So this is still an interesting problem. So the whole kind of, allocation, optimization of these resources, how we should do the compression of the gradients efficiently, so on and so forth. But there is another kind of more interesting observation is that I actually, the problem here is, I don't really need to send each of these gradient vectors reliably to the parameter server. All the parameter server wants is their average. So this is not a communication, in the strict sense problem, but it's actually a computation problem. It's actually a lossy computation problem over a noisy multiple access channel. And so what we proposed here is actually, instead of doing this kind of first gradient compression and then channel coding, resource allocation, and all of this, we said that why don't we just take these gradient vectors and then just transmit them as they are in an uncoded fashion over the wireless, kind of in a synchronized manner, so that the wireless channel is actually just adds them. So the wireless channel also already has this kind of signal superposition property. So they will be already added, and the parameter server is happy, so it doesn't need to do anything more. So of course, the first challenge is that these parameter vectors are typically huge. So we need to somehow reduce the dimension. So for that, we proposed gradient sparsification followed by random linear projection. This is kind of an idea that we borrowed from compressive sensing, right? So we reduce with this kind of random, pseudo-random projection. So now we have, so we don't need to kind of send the entries of all these kind of sparse vectors, so that reduces the communication requirement, and they are again naturally aligned over the air. So we showed actually that this is so much better, because now basically we are kind of doing a distributed beamforming using the power of all these devices rather than actually sharing them, allocating the resources to them. So here you can see that this analog approach is almost as good as error-free shared link and much better than all other kind of digital approaches. And if the data is non-IID, it actually interestingly, it gets the gain is even more. And yeah, so here we are basically showing that this kind of the trade-off between the how much you sparsify, how much you transmit over the channel. And the second challenge that of such a scheme is, of course, before I assumed, the channel adds them with the same gains. That's what I want. But typically there are different channel gains. So I have to kind of take care of that, because I don't want to create bias towards one user. But for that, we can if we know the channel gains, we can estimate these channel gains and apply some sort of channel inversion at the device, some power allocation algorithm. So that would still be fine. So here we are showing that basically this is possible. You can still get very good training accuracy with this analog scheme, much better than the digital alternatives. But we later also showed that you don't even need this channel estimation if you can use multiple antennas at the base station. So this is kind of the using this multiple antenna benefits of multiple antenna to kind of compensate for lack of channel state information. So here we are showing that as the number of antennas increase, you can see that with this analog scheme, you get better and better performance, almost as good as the having all the data centrally. So so this problem, I think in general, so this is there are many kind of interesting problems along this line, whether you do digital or kind of analog look at transmission of this, either the gradients or the model updates. So we recently, for example, looked into how when you do this kind of allocation, who transmits, how many, because when you decide who transmits, in the case of, for example, especially wireless channel, you might decide on, for example, the users with the bad channel don't transmit, because you need to align them all at the same power level. So now you need to kind of have a decision rule whom to schedule at each iteration that should depend both on the channel, but also kind of the significance of their gradient estimates. So kind of there will be kind of interesting interactions between the machine learning aspect, the significance of data and the channel aspect, so how good the channel of each device will be. So I'm going to wrap up here. So this was, of course, a very kind of short, brief introduction to this kind of problems in the federated learning setting. But I guess the main message, as in the rest of the talk, is the fact that, you know, when communication comes into picture, particularly if, you know, the physical layer is there, then, you know, we definitely need to, you know, take this communication aspect into account, because, you know, the channels will introduce, you know, delays, errors, uncertainties. There's all sorts of kind of channel imperfections. And just assuming that, okay, so we have already these communication protocols that take care of all these things is not going to be sufficient. At the least, we will need to kind of optimize the parameters of these kind of solutions that will match the requirements of the learning algorithms. But if you want to go even further, then we need to do a redesign, a complete redesign of a joint machine learning and communication system. Okay, so I will stop here. As I said initially, so for more information, for kind of more recent publications along kind of these lines, you can check our group website. And we had a recent, now the time is passing so fast, and the developments in this area are so fast that, you know, this feels like quite in the past. But so we had this paper, basically machine learning in the air, that overviewed kind of the challenges and the promises of using machine learning for communication problems, or using kind of improving the communications aspect of machine learning problems. So I didn't touch upon the first aspect too much here, where how we can use machine learning tools to improve communication systems. But that's also, of course, a very interesting research direction. Okay, so I will stop here. Now, I think we have some time, very little time for questions. So how do we do that?
Yep, so I will reclaim the host so I can maybe have a better control, if that's fine. But can you please, now
So
I'm the host. Yeah, but can you please just check if you can share your screen if it's required, or you don't have that option?
Okay, so now I'm not the host anymore, is it?
Yeah, you're not the host.
Okay, no, I cannot share the screen now anymore.
Ah, okay, this is strange. Just a second. I don't know why, but anyway, if anyone in the attendees have questions, you can raise your hand. I see that someone raised hand. Henrik, you may talk now. You need to unmute yourself.
Can you hear me?
Yep. Jaya, you can go next.
Yeah. In the first part of the presentation, when you were talking about inference and this joint source channel coding scheme, I was wondering about the training of this scheme, because it seems like there might be a risk that you overfit the channel scheme to the particular channel. So is there a risk that you're training for one channel and then the channel changes and suddenly it doesn't work anymore? And if so, how would you combat this?
Yes, okay, very good question. I mean, in general, yes, there is that risk, but I think that risk is, of course, there even for all our communication systems, right? We assume some model, design some communication system, and then, you know, we expect that it will work in practice. We don't know, you know, if the practice will fit into that initial model assumptions that we had or not. So what we observed, kind of empirically, let's say, is that actually these solutions are quite generalizes quite nicely, in the sense, the one that I mentioned, for example, which we also have in this DeepJSCC paper, is that if the SNR changes, these are like they really nicely work. So even if you train for a specific SNR, and if you reduce the SNR, increase the SNR, the performance actually changes gracefully, so they don't completely disappear, you know, like in digital. And also we looked at different kind of more kind of fading, you know, like scenarios where, you know, different parameters of the channel changes. Again, empirically we observe that actually they work fine. Of course, you know, if you have kind of richer models, the way, you know, these things would work, it would change in the practice, whatever, you can even train taking those into account. That's something we didn't do. But I think actually these models are quite powerful, in much more powerful than, let's say, our very fixed model-based solutions.
Okay, that's very fascinating. I thought it would be a much greater risk then, but it sounds like it might be quite robust.
Yes, and I think the main feature is this kind of analog aspect, as I said, because we are not designing like a digital kind of thing, right? So that's very, in the digital design, you really target a very kind of fixed, you design optimally to an exact kind of channel model.
I see. Thank you.
So Jaya, allowed to talk now. You can unmute yourself.
Hi, can you hear me?
Yes.
Yeah.
Hi, Dennis. Thanks for the presentation. I have a couple of questions. The first one is again in the distributed inference. You have showed this distribution of the neural network between the local device and the edge. So there I want to just understand what are the numbers here. Like if you want to upload the image of the dog, or if you want to upload the parameters of this neural network, like what will be the difference? I mean,
yeah. Okay. So I mean, so I gave this kind of. I guess I will not now like go back to the slide, but hopefully you remember, and the slides will be available later, so you can so if you just look at in terms of pure dimension, so that plot was showing how the dimension changes. So let's say you have an image dimension, typically height, width times the three colors. So that would be your input dimension. So it's pure kind of number of real numbers that you represent your data that you would normally feed into your network. And then the other numbers we are showing as you go kind of layer by layer in your network, what is the size of the features that feature vectors or matrices you will have. So if I cut the network there, how many real numbers that I need to pass to the next layer.
Okay, so I was wondering if that would be smaller or greater, like, because it would, to me, it feels like if you can send the image itself, right? Because in neural network, I am not completely an expert here, but in neural network, I heard that there will be like millions of parameters, something.
Yes,
like,
exactly.
Depending on the.
So first, we are not talking about all the neural networks. So I mean, we are talking about like how many features there is at each kind of after each layer. But you are right, and actually that figure was exactly showing that. So if you look at actually in typical this type, especially deeper neural networks, so the dimension initially goes high, so you kind of expand your data in a larger space, and then you again project it in a lower dimensional space. So that's typically the trend. So if you actually are very limited in computation power, and if you want to do a few layers, actually you do a few layers of computation, but you end up transmitting a lot. So that is kind of the main thing, right? So that we are addressing actually. So you are right, and that's the challenge. And basically you need to find a way kind of to transmit that much larger dimensional information in a very efficient manner. Otherwise, yes, you would just transmit the image.
Okay, thank you. So and the second question is, when you're doing coding for this gradient computation, to avoid the straggling, to overcome the straggling nodes problem, there I didn't completely get how the convergence time of the finally trained model will get affected when you're doing the coding.
Okay, so if you are doing like normal gradient coding, the original kind of is in that paper, you are actually getting full gradient. So every iteration, you are recovering the exact gradient across all data sets. So that will have the same convergence time as gradient descent. Okay. The main difference is that the time it takes for each iteration will be different. That is the time that you need to collect enough data to recover the full gradient. Now, if you do different schemes, for example, in this partial gradient scheme, so we are actually allowing some noise in the gradient. So that that is you need to do kind of a convergence analysis. If for example that you make sure that noise you introduce is unbiased, so that's kind of standard. There is a way. But again, the main issue here, most of these things will converge, but the main trade-off is in the kind of the time of you're playing with the time it takes for each step of these things.
That's where my confusion is. If you look at SGD, right? I mean, even if you take I mean, theoretically, even if you take a single example, then you might end up converging faster than SGD. That is known, right? So once you're doing coding and I mean doing all this, bringing in all these intelligent techniques, how much gain we will get in terms of convergence time is what I am.
Yeah. So I mean, that's exactly, you know, like the kind of the comment I try to make is that in the end, it all boils down to how much time you really take to communicate these things and to compute these things. Yes, in SGD, you know, like you might end up having faster convergence, but it also, you know, depends on the fact that, you know, it takes like 1 unit of time compared to, let's say, you know, whatever that's, you know, like you're doing 1 batch instead of maybe 100 batches computation, right? So you have this kind of linear gain of based on the batch size, and then you do less iterations. But, you know, so here when you distribute things, it's not clear basically that, you know, how these things scale. I mean, you can even say that, yeah, I will get like 1 batch, but there's still some sort of, you know, because of the computation speeds, because of the communication speeds, you know, these things are not as clear. They are not just, you know, like counting this number of operations or counting the number of iterations. I mean, and another thing is, of course, I should also say that one thing is the convergence behavior, but another thing is that what happens in the practice, right? I mean, for different, and my kind of take on that is that this will depend a lot on, you know, what is the type of problem that you are using, you're solving, and of course also the real implementation, what kind of communication protocol you have. I mean, it will be different if you're in a server farm, all these things are connected through wires compared to a edge network scenario where, you know, you're connected wireless or whatever.
Okay, thank you very much.
Thank you.
Nice. Is there any more questions from the attendees? So if not, maybe I can ask one last question maybe here. So first of all, I really enjoyed your talk. It was covering many different aspects, all of them really interesting. Regarding your gradient, by the way, you can, I guess, now share your screen if you want to. There was a permission problem. But regarding the gradient coding, actually, so I wasn't really clear that the base assumption is that you need to have access to essentially all the server should have access to all the data and then decide on how to engineer these data dissemination over the users, right? Whereas in many cases, especially concerning networking scenario, we do have this data privacy, so we don't want essentially to share data. So then how we can somehow address this problem?
I mean, yes, that's why I kind of grouped these into 2 different approaches. So all these kind of coded computation ideas are typically applicable when you can kind of curate your data to the workers in the way you like, and especially this coded computation where, you know, this kind of Lagrange coded whatever. So it all assumes that I have the whole data set, I do some coding and then distribute it. So these are especially, you know, maybe more relevant if I want to do some big computation using this type of servers. But there are also a lot of papers, for example, looking at the privacy of these things. So this coding also gives you some privacy. So that would be also a benefit of that. Now, if your data is distributed, you can't do that. And especially if the data is like fully distributed, if everybody has their own private data, if there's no data redundancy, I mean, there's no way. And if you don't allow any kind of exchange. So we, for example, had a paper where we said that, I mean, maybe it's possible that, you know, like if, for example, I am close to you, our data might share some, depending on what this data is, right? So we might share some part of our data. So that would give some natural redundancy. So could be the case, some application. Or maybe you can allow somewhere, again, you know, depending on the application, you can allow some local like exchanges. Maybe I don't trust the network. I don't want to send to the network, but maybe if I'm going to gain a lot, I can exchange with my neighbors to do some computations, you know, to have some redundancy. Maybe we agree, right? And then maybe that might be another way of kind of having this. But you are right. I mean, so if this data redundancy is not there, that's, you know, those are not possible.
Yeah, that's actually very interesting, because if we want to define the redundancy in the data, either we can be very in the deterministic setting where we can say that the data are like duplicated, or we can say that the data are not duplicated, but they are statistically the same or similar. For example, if we look at some big data sets like MNIST data set, this is just coming from my experience, it has like 60,000 samples or examples in the data set. And if you just randomly throw away something like 50,000 of those samples, still you can recover the exact same solution, essentially saying that 90% of those data are like redundant. So now if you somehow distribute those statistically redundant data among different workers, I know that probably the gradient coding, your approach as it is now, it won't work because you need duplicate of the data, but have you thought about extending that?
In my opinion, I mean, we need to think a little bit carefully, but I think that type of redundancy is actually what is exploited in more kind of this stochastic optimization technique. So when you do stochastic gradient descent type of things, I guess intrinsically that is what you are exploiting. Anyway, so if you, for example, like when we do, for example, this kind of federated learning implementations, so what we do in some simulations, you can just randomly distribute this, MNIST data set, and then every time you just schedule one of them or something like that, right? So that is good enough because, as you said, like this, what you get is kind of representative enough. Whereas, this kind of federated learning also kind of becomes harder if you do non-IID. So if you put all the classes, the same data of classes in each user, for example, then you don't have that benefit. So I think the gain, the kind of trade-off there is more or less because of this type of statistical redundancy. So it comes into more into picture there. But if you want to use this kind of more kind of very coding theoretic ideas that you really want to recover something, you have coded versions of it. I'm not sure, how. So that's a very interesting thing, actually. Like,
yeah, that would be
more
very
like a
interesting.
distributed compression type of thing, right? So we have correlated data. We want to recover a kind of a combination, a function of that data. Can we do still coding? We know we can, but probably we need a very good model of that statistics. So that
because
would be very interesting.
Yeah, because to me, one of the greatest benefit of gradient coding is coming from this robustness to straggler, which we know by definition SGD and those stochastic algorithms are not that much robust. So if somehow it can be addressed, it would be pretty cool, I guess. So any more questions?
Yes, I have a question. Regarding the linear combination of the gradients that you want to send when you have the kind of slowest worker, how do you find the slower worker, and how do you distribute the data set? I mean that if we want to have the data set that distributed in a way that each workers don't have the other workers data set, okay, what's the point to other workers be able to compute the gradients of others?
Yeah. Okay. So first of all, this kind of typically this distributed computation against straggler framework assumes you don't know exactly who will be straggling, because if you know the speed, who is going to be slow, you don't even use it. So you don't even maybe like request the computation. So that would be in a way easier. So actually all the results are actually assuming we don't know who is going to be straggling, and it might even change over time. And we are giving this, it's like, I mean, the coding, both the coding scheme and the attitude approach is the same as erasure channel. So as if you're generating coded data, some will be lost. You don't know which will be lost, but still, let's say k out of n will be enough to recover your, what you want. So it's just to do the same thing in a coded computation framework. So in that sense, like your first question, like we don't really need to know that. So we kind of create this sufficient redundancy that any k out of n of the servers will be enough. Now, in terms of your question, like if you want, so here again, so the data is centralized. So I am sending to, so there's no, intrinsically, there's no constraint on who has what data. I can send the same data to as many workers as I like in the kind of, if there's no additional constraint on that. But there are also, as I said, at least the one I talked about was like that. But as I said, there are also works that talk about privacy aspects, security aspects. So in that case, you might actually require, for example, the workers not to have any idea about, what they are computing. And actually this coded computation gives you that in a way, because I'm sending each worker a random kind of computation of a polynomial at an arbitrary point. So it can have no idea about, like on its own, it cannot interpolate that formula, that polynomial. So it will get zero information. So that's actually an additional benefit of these schemes.
Yes, thank you so much.
Thank you.
Yeah, thanks a lot, Dennis, for your fantastic presentation. And Martin, now you can take over and introduce maybe the next speakers.
Okay, I would like to just thank very quickly before you do that.
Absolutely.
Thank you everyone for listening. And yeah, if you have any questions at all, I'll be happy to hear any questions, feedback later.
Yeah, and we will see you in the panel anyway in this afternoon.
Yes, yeah, talk to you. Unfortunately, I will not be able to follow the probably in between, as I will have to take over kids now.
Yeah, I see. Sina was, I guess, he was looking forward to having you in his presentation.
Sorry, yeah, I will. I mean, but if anything, yeah. So if there's anything you might need, tell me. If this will be recorded, right? So I will try to do that.
Absolutely.
Yeah.
Absolutely.
Thank you very much.
Thanks a lot.
Thanks a lot, Dennis.
See you soon again. Bye for now.
Bye. Okay, so let me start introducing the speakers and what are the presentations about now. Just a moment. Yes, okay. I think you can see my screen now. And so let me put it here. Yeah, can you see the slide presentation?
Yeah, I can see the presenter mode actually.
Let me. Yeah, it's easier this way. Yeah. Okay, so the presentations that we are having now, they are part of the PG course, Fundamentals of Machine Learning over Networks, that Jose and I that we are giving this semester. So this course is held by the Network and Systems Engineering Division, NSE, at the Electrical Engineering and Computer Science School at KTH. Overall, we have 80 participants, out of where 65 are outside Sweden, and the remaining are within Sweden from KTH and other universities spread in Sweden, like Uppsala, Mid Sweden, and among many others. Overall, we had 16 lectures, 10 lectures of fundamentals, going from the basics of convex optimization, distributed optimization, and machine learning. And now we have the special topics presentation. If you want, we also put the course website where you can follow the material, the lectures. We also have content available online, also on the GitHub of our course and on the YouTube of our course. So I'll put the links in the chat for you. Now going to the special topic today. We have the pleasure of having a special topic on privacy and security in distributed learning. The presenters are Jaya Prakash Sampati, Rahul Rondon, Ritkard Mugisha, and Sina Molavipur. And these 4 references will be the basis of their presentation. So I'll stop sharing and I'd like to welcome Jaya, right, who'll be the presenter.
Yes.
Thank you. So now I'll give the floor to you. Thank you very much.
Thank you, Merton. So can you see my screen?
Yes.
Okay, great. Welcome everyone. My name is Jayaprakash Sampati. I'm a postdoctoral researcher at KTH Royal Institute of Technology. Me and my teammates Sina, Rahul, and Richard will present the topic privacy and security in distributed learning. So this is the outline of our talk today. I'll first introduce distributed machine learning and talk about federated learning, which overlaps with what Dennis already introduced. And then Sina will cover privacy in federated learning and some basic concepts in differential privacy. Rahul will take over from differential privacy in deep learning. And finally, Richard will cover differential privacy in online learning. So today, most of the machine learning applications at scale run in data centers where data is collected centrally, and then machine learning models are trained by having a set of master nodes which distribute this large amounts of data among thousands of worker nodes, and then they coordinate these worker nodes to finally build these ML models. This distributed machine learning architecture is now being complemented by this federated learning architecture, where the idea is to exploit or take advantage of the data that is available on edge devices, or we call here as clients. For example, the smartphones, tablets, or Internet of Things, and so on and so forth. But the proposal here is that these devices, the data can be sensitive and private, so the data cannot be directly uploaded somewhere and do the training. So the clients will train some local models using the data they have at the disposal, and send some global updates, and a central server nearby will be coordinating these clients by aggregating these updates and build a global training model. So here is the federated learning system schematic. On the left, you can see there are clients which are training local model and sending some updates to a server. And this training process can go for days or months. And then the trained model will be tested, and then it can be deployed on the clients in the rest of the world. Several existing applications are already using this federated learning system by building. I mean, these are all they build this independently. So these applications like natural language processing, Google Keyboard, Apple QuickType Keyboard, and so on and so forth. They have built the systems and their own systems and deployed in practice. In general, the main challenges in federated learning are that the data that is available on these devices, there can be overlap. So unlike in data centers where they collect data centrally, they can distribute this data as they wish. So they can maintain that this data can be IID. But if the clients have data that is overlapping, which is actually the case, so how do you overcome this non-IID data assumption to ensure the algorithm convergence and performance? And of course, the data is unbalanced. And also these client devices, as I mentioned, they can be smartphones which are connected through internet, or they have the users of the smartphones have some requirements, like to have a minimum battery level before they can participate in federated learning. So this is another challenge that needs to be overcome. And because of the same reason, communication efficiency has to be taken into account, because if you have large number of communication rounds, these users might not participate in federated learning. And the last but not the least, and the most important concern in federated learning is to ensure privacy. Of course, it is proposed by saying that it can alleviate the privacy concerns, but still, even if the data is not completely transmitted, the eavesdropper or neighboring clients can still refer the data features of the of a client. So this talk will focus mainly on privacy, and from here on, Sina will take over. Thank you.
Hello, do you have my voice?
Yes.
And the screen is okay, the slides?
Yeah.
Okay, hello, my name is Sina Moulavipour, and I'm a PhD student at KTH. So continuing the talk about the privacy concerns in federated learning from here. So in an ideal world, each actor in this system would learn nothing more than the information that they asked or they needed to have to actually can have that information from the different users. And it is clear for participants in the system that what personal information is revealed to each party. So everything should be clear, but this is an ideal world. Maybe a bigger step toward this ideal concept is to have data minimization. So what does it mean? It means that instead of sending the raw user data, we can send updates of the model, or let's say gradient updates in particular. So the advantages of this is that we are not sending the raw data. So a big amount of information, private information, is secured. And also we can actually add this function that the server can expire these gradients, so they're not remaining forever in the system. But is it really solving the problem? The short answer is no. So in fact, while these gradients are communicated to the server, one maybe expert can actually reveal some information from these gradients about the raw data. And so it's not completely securing the private data. Other aspects of security also could be discussed. For instance, apart from confidentiality, where we want to keep the information private, we have also the problem of an adversary wants to prevent the model to be trained. Also, an adversary can bias the training procedure by I don't know, by updating with false information. So these are also other scenarios that could be concerned. Also, each of these players in the system, as Jai explained, so they can actually become a malicious player, and also and can disturb the training. For instance, a client which is listening to the server's messages, they can actually tamper the training process, or the server itself can actually become a malicious player and tamper the training process. Also, engineers or analysts who have access to the output of the model, they can also, since they have an advantage of knowing different hyperparameters, they can also do some modifications. And also we can, since the final model is deployed on let's say, in some example, on mobile devices or IoT devices, maybe one user can actually find out what is inside that black box or that model and use that information. So these are all threat models that we can imagine for, in the federated learning. So these are, I mean, I'm going to talk about some concepts that they play a role in privacy in federated learning. So one is the multi-party computation, where we consider a set of parties computing a function of their private inputs in a way that they only reveal the intended output to each other. So another concept is the trusted execution environments. You can imagine this as a secure cloud environment that you can send out your processes and your computations there and receive back the result. Also, there is another concept known as differential privacy, which would be the main focus of the rest of talk. Differential privacy is actually a quantification, a measure of how much information can be learned about an individual from the output of this training and this training procedure. So regarding the MPC and TEE, we can actually, instead of implementing the whole concept, we can actually only implement subparts. For instance, we can only implement a secure aggregation where every client sends a value to the server and can only learn a function of those values. Also, we have secure shuffling where clients submit some reports, some messages, and the server can only learn an unordered. So the server doesn't know which client sent what report. Also, we have the notion of private information retrieval, where the client query from the server remains a secret to the server. So maybe I'm presenting this simple example of how to implement this security in a decentralized federated learning. This is more an intuitive example. So we can consider that we can add some noise. It would be a Gaussian noise that is added to the global model that we have. Also, each client can add locally some noise at each gradient steps. And in the end, maybe the output of the model can encrypt it when we want to deploy it or we want to store it somewhere. But this is more intuitive example, but there should be a theoretical proof behind this. So here comes the notion of differential privacy then. So differential privacy addresses the paradox of learning nothing about an individual while learning useful information about a population. It's like learning statistics of a population. You can imagine that. So one example is that consider a medical database, and we want to study the effect of smoking on cancer. And so the results can affect, let's say, the policies or the prices of an insurance company for their customers. So if they know that someone is a smoker, they will charge them more, perhaps. So now the question is that if a person A, considering a person A who's smoking, and so then the insurance company, if they know that that person is smoking, then they know more about him after this study, and they may charge him more, in fact. But is this a leakage of private information? So differential privacy answers this question, and the answer is no, because the impact on the smoker is the same, independent of his or her participants in this study or in the database. So it doesn't matter that he or she was in the database. It's not, and the impact of the insurance company on the price is not changing. So then we say that it's not a leakage of his or her private information. So if I want to formally define the differential privacy, here's the definition. So consider a randomized algorithm A, and we say that this algorithm is epsilon delta differentially private if for all S belonging to the range of A, and for all adjacent data sets D and D prime, the probability of this AD belonging to S is smaller than e to the power epsilon, the probability of AD prime belonging to S, plus a delta. This delta is like a boundary, a threshold that we have for this inequality. So what is the notion of adjacency here? So we say that D and D prime are adjacent if they are different only in all the records of a single client, or in a different notion, the D and D prime are adjacent if they only differ in one in records of one user. So if epsilon and delta are 0, this means the absolute privacy. So it means that the events of AD belonging to S is equally probable with the event of AD prime belonging to S. So it means that it doesn't matter where that person was in the database, D or was not. So it means that it's like, informally, we can say that it's like the algorithm is generating pure noise, or it's random noise. So while it is absolutely private, on the other hand, it's not useful in the sense that it's not giving us useful information. So we cannot use it in practice. So now to have a better understanding about the delta in epsilon delta differential privacy, consider this definition of private loss, which is equal to this log likelihood ratio, the log of the probability of AD equal to some zeta over the probability of AD prime equal to the same zeta. Then we have this lemma that tells us that if D and D prime are adjacent, then epsilon delta differential privacy ensures that the absolute value of this log likelihood ratio is smaller than epsilon with the probability at least 1 minus delta. So it means that if delta is smaller, then we are more confident about this inequality. And if epsilon is smaller, then the difference between these two likelihoods are smaller as well. So another notion which is named as Laplace mechanism is really is used quite a lot in this topic that I'm going to define it here. So consider this definition: the L1 sensitivity of a function f is this is equal to delta f, and it's equal to the maximum of norm 1 between fx minus fy, where x and y are different only in one element. So you can consider this as data sets that they only differ in one record. And this delta f is L1 sensitivity. Now, given any function f, this is the Laplace mechanism definition. So given any function f, the Laplace mechanism for that f is the f plus some noise here, where this noise z1 to zk are IID random variables drawn from a Laplace density. So this means that here we're adding some noise to the output of this fx function, and this is a random algorithm. The Laplace density looks like this. So it's like it's proportional to the e to the power minus epsilon zi over the delta f, which was the L1 sensitivity. So why this example is important? Because so now consider the epsilon delta differential privacy with delta to be 0. So it means that we need this log likelihood ratio to be smaller than epsilon, with probability 1, of course. Then the theorem about this Laplace mechanism tells us that the Laplace mechanism for a function f preserves epsilon 0 differential privacy. So that's why this Laplace mechanism is important, since they are preserving this epsilon 0 differential privacy. And the reason is that if you can substitute the log likelihood ratio and they substitute the densities with the Laplace densities, we can see that this log likelihood ratio is smaller than summation of epsilon multiplied by absolute value of fxi minus fyi, meaning that the ith value of fx over delta f. And the summation is over all the elements of this fx, the output of the algorithm. And this is, we can say that this is smaller than epsilon because of the definition of delta f. So it means that it is the epsilon differential privacy is achieved here with this mechanism. So we have variants of differential privacy. I mean, in a centralized setup, maybe a server can orchestrate these mechanisms to ensure the differential privacy. But if we want to have maybe to reduce the burden from the server, we have the local differential privacy, where each client applies differential private transformation on the sharing data. So this is so they locally they implement a mechanism to achieve differential privacy over their own local data. So it's not general data, so only on their own local data. Also, there is we can actually have this distributed differential privacy, where this is just an example that we can apply this local differential privacy on each client, and then the output of each output of this would be sent through an MPC mechanism. So we can actually compute a secure. We can have a secure computation function, and then the output of this MPC would be sent to the server. So it's like adding one layer of security before sending to the server. So these are different types of implementation. So one example could be this figure, where assuming that we have 4 clients and they are sending this x1, x2 to x4. So there is this local randomizer playing the role of local differential privacy algorithm, and the output of the outputs are these variables y. And then we can have this shuffler. So this is a subtask of a multi-party computation. So with this shuffler, then the server or the analyzer here doesn't know that who sent what information, and then all this information would be sent to the analyzer. So with this, I'm going to hand over the rest of the presentation to Raul, talking about deep learning and differential privacy in the deep learning. Thank you.
Hello. Do you hear me now?
Yes.
Okay. So good morning. My name is Raul Rondon, and I'm a PhD student at Michigan University. As Sina mentioned, I will be talking about topics on differential privacy in deep learning. So deep learning is a subfield of machine learning that has become prominent in many applications, such as cognitive tasks, which includes speech, text, image recognition, also in natural language processing, self-driven cars, gaming, and many others. In deep learning systems, we have deep neural networks with many layers that are used to extract features from raw data. These neural networks allow us to parameterize input-output functions as a composition of the different activation functions of each one of these layers. However, deep learning requires large amounts of data to produce better utilities. And if you have better utilities, that will in turn incentivize users to share more data, producing better utilities, creating this cycle of improvement or innovation, if you wish. But this data, for the user to be comfortable in sharing the data, the privacy of this data should be preserved. So then we look into the protection of the training data used in the training of the system. So we can use different methods such as data encryption or having different policies in data retention and data deletion, but these measurements are not enough. And as this training data becomes more sensitive, the most important question to understand is what the machine learning model is actually revealing about the data, the training data set. So in this picture, we have a common pipeline in a machine learning system, in which we have a training data set that is used to train a model to fit the model. And this model is then fed into an inference engine that will predict outputs based on the live data that it is receiving. And we could think that we could protect this system by protecting the actual output of the system. But an adversary could input their own data into this system, and it could also get hold of the model. And if this happens, it could learn things from our training data set, losing then the privacy that we are looking for. So the best way to protect our training data set is to ensure that the model itself is privacy preserving. And this is the focus of this part of the presentation. So we want to use this training data set to fit a model that preserves its privacy. So then how do we how do we have differential privacy in deep learning? As Sina was mentioning, differential privacy is one of the ways to ensure privacy in general, and is a very efficient way of doing it. So we want to see how to do this in deep learning. We said that the privacy of the training data could be tackled using a black box method, in which we focus only on the final parameters that result from our training. But this approach might lead to an insufficient characterization of the dependence of these parameters that we obtain and the training data set used. And also, it might leave the actual training data set vulnerable to some attacks. So a better approach is to instead control the influence that the training data set has on the training process. And that's where tools such as the differentially private stochastic gradient descent come into play, allowing us to achieve differential privacy in our deep learning model. Over the years, different versions of this concept have been presented in different works. However, in this particular presentation, we are focusing on the variation that was presented by Martin Abadi in the work cited below. So before we go into that, we can remark some of the important properties of differential privacy. And these properties are they come from the actual definition of differential privacy, and not necessarily from the actual implementation of the algorithm itself. And these are: one, we have robustness to auxiliary information. This means that the ratio of probability that Sina was explaining in the definition of differential privacy is unaffected by new information, meaning that if someone sees the output of the system and then gets other kind of information related to the same data set or the data set itself, these ratios should not be affected. We have also group privacy, and which means that if we can offer epsilon delta differential privacy for a single individual, then this will yield to k, the epsilon delta differential privacy for a group of size k, mean that this epsilon and delta add up. And this is linked to the composability property, which is probably the most important one on this list. And this means if we have all the components in a mechanism being differentially private, then the composition will also be differentially private. And this implies that we will have a bounded privacy loss due to the differential privacy over all different analyses that we might conduct on this data. And this comes from or is derived from more theoretical concepts of there are different basic, advanced, strong composition theorems that I won't have the time to go into, but this is where the idea comes from. And this is especially important in neural networks because of the layer composition that we mentioned before of the different activation layers, and also of the iteration process itself. Also, we have that due to this composability, we could also have larger, more complicated problems be broken down into smaller and simpler problems without losing differential privacy. So this is the outline of the differentially private stochastic gradient descent algorithm presented in the article mentioned. And as we know, this is going to train the model, trying to minimize the loss function. At each iteration, we will compute the gradient for a random subset of samples. After that, we have to clip the norm of this gradient, and then add some noise that will protect the privacy, will offer the differential privacy that we are looking for. And after that, we will just take a step in the negative direction of this average noisy gradient. At the end of this procedure, we should obtain our final parameter and also retrieve a measurement on the overall privacy loss involved with the training process. I'm sorry. And this is achieved by use different accounting methods. The common one using is the commonly one used is a privacy accounting method, which will track the accumulated loss over all the different compositions. So two of the particular components of these algorithms is the clipping and the clipping of the gradient and the Gaussian mechanism involved. And these are after the calculation of the gradients, we will perform these operations to ensure that what we get from this gradient is private. First, we have the clipping of the gradient, which involves forcing this gradient to stay within a particular range, and this is performed element-wise. This is needed to avoid gradient explosion and also to preserve differential privacy, ensuring or bounding the influence of each individual example on the training set. Clipping of the gradient is performed in different versions of different implementation of stochastic gradient descent. However, most of the time it is done on the average and not on each particular element. But for differential privacy sake, we should perform this element-wise, as indicated in the algorithm. And then we have our Gaussian mechanism, in which we are going to add noise to the gradient that is calculated over the lots. And thanks to the composition theorems, adding this Gaussian noise will result in epsilon delta differential privacy. However, this statement derives from the composition theorems. And depending on which composition model you are using, you will need to set or calibrate the variance of this noise in order to achieve specific values of the privacy loss. So, but when it comes to estimating the privacy loss associated with a training process, we could do different things, but the most common thing is having this privacy accounting method. And this is thanks to the composability property of differential privacy, we could have an accounting procedure computing the privacy cost that comes from each time we access the training dataset and perform something on it, as well as the cost of all the multiple calculations that we have to do over the layers. And this is accumulated and reported at the end as the overall training cost or overall privacy cost of the training process. And another way of doing or measuring the overall privacy cost of the training is also, which is one of the contribution on the article. So this is a proposed method in this article, is the moments accounting. And basically, this is a generalization of the privacy accounting, and it will keep track of a bound on the moments, higher moments of the privacy loss random variable. In this case, we are considering the specific distribution of the Gaussian noise that we are using with random sampling. And in this case, if we compare the bounds that we can obtain using the moment accounting to the privacy accounting, we could get better bounds using these kind of calculations. However, they might be a little bit more expensive in complexity and more complex in general. So overall, we can see that it is possible to train deep neural networks with non-convex objective without losing privacy, differential privacy, or staying within a privacy budget, without extreme software complexity, training efficiency, and model quality. We could get better estimates on the overall privacy loss if we track the information in the higher moments of the privacy loss, although it might come at a complexity price. And this method of differential private stochastic gradient descent is performed on each one of these gradient calculations. So this can extend to different models and topologies of machine learning, both centralized and distributed, because here the idea is to ensure that what we are producing from the model itself is protecting the data. So then how we implemented this is there is some flexibility to it. So that would be it for my part. And now I will leave Richard to continue with differential privacy in online learning. Thank you.
Can you hear me?
Yes.
Okay, let me share my screen with you. Can you see my presentation?
Not yet.
Okay, let me share my screen. Can you see my screen?
Yes.
Okay. Can you see my presentation?
Yeah.
Okay. Thanks, Raul. My name is Richard Mugisha, and I'm PhD student from Mid Sweden University. I'm going to talk about differential privacy in online learning. So let us start with the differential private to online learning. So here we are going to cover these 4 main points. Background on online learning, overview of online learning algorithm, randomized weighted majority algorithm, and finally, most important thing, we should combine this randomized weighted majority algorithm with differential privacy. And as you know, we are concerned about differential privacy. And this subject comes from this article by Cynthia and Aaron. It's called The Algorithm Foundation of Differential Privacy. On this slide, I'm going to start with the background on online learning. And by a simple definition, online learning is just learning from expert advice. And somebody can imagine that you are betting on horse races and you don't have to know anything about horses. And you should suppose you have access to the opinion of some expert on their basis. And this expert make prediction about which horse is gonna win. What you should keep in mind is that expert can sometimes make losses, and as you know, no experts are not perfect. On their basis, we can choose one of the expert advice, and after betting, you can learn which horse has actually won. And this idea of betting on expert basis is known as learning from expert advice. So through our next slides, we will use this concept of learning from expert advice. On this slide, I'm going to talk about how we can measure the performance of our online learning algorithm. And the most important thing is this expression. So we have the regret of the algorithm over a sequence of losses spanning over interval t is given by this, and this can be calculated as follows. This is the total average loss of the algorithm. And here we have this expression as well. It can be calculated as follows. This is the total average loss of expert I over T rounds. And as you can see, we have the minimum. So if I go back to our definition, the regret of the algorithm A is defined as the difference between the loss that the algorithm may actually occur and the loss of the best expert. So here we have the loss of the best expert. That's why we have a minimum value of the loss of the expert. By having this concept of regret, we will be able to evaluate our algorithm. So before talking about this randomized weighted majority algorithm, we should understand the main goal in online learning. So the main goal in online learning is to design algorithm such that the regret is guaranteed to tend to zero as t goes to infinity. So this is the main goal. So this t is just the length of the sequence of losses. As the length of the sequence of resource t goes to infinity, the regret is guaranteed to be 0. So it's guaranteed to be 0. And to achieve this, this can be achieved by using the multiplicative weight algorithm, which has got a famous name, which is the randomized weighted majority algorithm. And of course, it has got other names such as hedge, exponential gradient descent, and multiplicative weight, and so on. So, as I said, the goal of our online learning is to make this regret as small as possible. So as t goes to infinity. So we will use this concept actually in the coming slides. So when we talk about randomized weight majority algorithm, to make things simple, there is a theorem here that is used to define this randomized weight majority algorithm. By definition or by theorem, this expression is given as the expectation of the regret of the randomized weighted the majority algorithm for losses spanning over a length t is given by this expression, is upper bounded by this expression. And the most important thing in this expression is this update parameter. So this update parameter is a parameter for this algorithm. So this is by definition. This is by definition of the randomized weighted the majority algorithm. And this k is the number of experts. T, as I said, is the length of a sequence of losses. And sometimes this update parameter is chosen as follow, and plugging this into this formula, we get this final expression. And based on the previous slide, the goal of this online learning, we have to make sure this expression, tends to 0 as t goes to infinity. So this is very interesting. I mean, this t as t goes to infinity, the expectation of the regret should tend to 0. So this is the main idea. This is the main idea about randomized weighted majority algorithm.
Richard,
based on this,
sorry to disrupt you, just to say that you have 2 minutes, okay?
Okay. So here we can use the concept of differential privacy to this randomized weighted majority algorithm. And the most important thing with differential privacy, the update parameter is given by this expression, where epsilon and delta are called differential private parameters. And plugging this in the previous formula, we can see that our expectation of the regret is upper bounded by this expression, where k is the number of experts. And you can see that when t goes to infinity, the expectation of the algorithm tends to 0. To summarize, we have seen that federated learning is emerging as powerful several mechanisms were reviews are privacy and to secure federation learning. Differential privacy to quantify the privacy is reviewed and best notion were presented. Controlling the influence of the training data on learning process is an efficient approach to create privacy preserving the model. The PSG enables this approach in distributed learning and can be used for different machine learning systems, both centralized and distributed. And differential privacy, this is where I have been focused. Differential privacy in online learning is mainly based on randomized weighted majority algorithm. Thank you.
Okay, so thank you very much, Richard, and Jaya, Sina, and Raul for the nice presentation. Does anyone has questions to the presenters? If so, please raise hand. Okay, no one wants to ask a question, so I'll ask a question first. So you presented nice information about the privacy and security in distributed learning, and also the basics of federated learning. So here I'd like to ask you, what is for you, what do you think is the most fundamental? Okay, so now we have a question. So then I'll give the floor to Hossein.
Well, you can continue your question maybe, and I can follow you.
Okay, so my question is, what do you think is the most important feature that differentiates federated learning from general distributed learning?
Are you asking me?
I'm asking the group.
Oh, the group, okay.
Can you repeat the question, Martin, again?
Yeah, so the question is, what do you think is the biggest difference between federated learning and general distributed learning?
So so the way we understand it, that in distributed machine learning, as I mentioned, the server, I mean, if the data is proprietary and if the data can be distributed in a with complete control, then you can have the non-IID case, you don't have privacy concerns there. Whereas in federated learning, this data is not proprietary, it is controlled by each of the individual parties or clients, as I mentioned here, and we need to ensure privacy, and of course that's the major part of our talk today, and also this data will be non-IID and unbalanced.
Okay, okay.
Your question, or if?
Yeah, I think that answers part of my question. I still think that a big part of federated learning that is important is the local computation that you perform, because that also helps to improve the convergence speed, the communication efficiency, and also to increase the privacy. And whereas in other general distributed learning schemes, you don't have these local computations for many iterations. You just evaluate the gradient and then you send to the server.
Okay, yeah, you can do multiple stages on the local points.
Yeah,
okay.
Yeah.
Okay.
Okay, so now I'll give the floor to Hossein. Please ask your question, Hossein.
Yeah, thanks for your presentation as well. The question that I have is actually regarding gradient clipping part. So you have presented that gradient clipping could be quite useful for differential privacy. But as far as I know, one of the most, let's say, usefulness of this gradient clipping is for noise robustness, essentially. You can imagine that if you want to run a stochastic gradient descent, then due to the noise involved, you can get in some updates some very noisy gradients, which is like sampling from the tail of that distribution of the noise, which happens very rarely, but it can happen. And the gradient clipping is actually tries to make the noise to the gradient something like a bounded norm, which can help a lot in reducing the variance actually of the error that you can get, essentially improving the convergence rate and also the robustness. So do you have any comment on that, and also on the differential privacy part, because that wasn't so immediate, at least to me, that how gradient clipping can help with the differential privacy as well.
Okay, can you hear me?
Yes.
Okay, yes, what you're saying is completely correct. So the gradient clipping is normally used for that, to control basically the value of the gradient. So if you have too much noise, or so to avoid this gradient explosion part that we were saying in the slides. So that is overall. In most algorithms, when you apply the gradient clipping, what you do is calculating or performing this clipping over the average gradient, and that is done basically for the sake of that, of reducing or bounding the noise that you get. When it comes to the differential privacy part, it's more related to limiting the contribution that each one of the examples will have on this calculation. So that's why you're clipping it per element, like in an element-wise fashion. So it's, I mean, mathematically, probably there are many demonstrations on this. I unfortunately don't have that right now, but it's on the concept of that limiting what each one of the examples is contributing. That's bounding the contribution of each one of them, keeping some kind of, how to say, it's not like uniformity, but you can find less information of each example. That's kind of the idea.
Okay. Maybe we can take it offline, and I can come maybe to your session on the poster part, and then we can discuss a little bit in detail, because that seems very interesting to me, actually, this aspect of gradient clipping.
Okay.
Okay, great.
Okay, so great. Thanks for the presentation, guys. I think now we have the break, the lunch break, and then we'll be back at 1 for the second special topic presentation, error compensation and variance reduction. So see you at 1, and for now we just stop here for a moment. Okay, see you soon. Okay, we are getting back in 3 minutes. Okay, so okay, so 1 minute more. Yeah. Okay, so good afternoon, everyone. Thank you for joining us again. So now we have the second special topic presentation. The topic of the presentation is error compensation and variance reduction. The presenters are Filippo Vanella, Henrik Hamström, Ming Chen, Morteza Ismaili Tavana. So these are the references that the presentation will be based on. And now I welcome the presenters to share the screen and also to talk.
Hello, can you hear me?
Yes.
Excellent. Let me try to share my presentation. Can you see the slides?
Yes.
Okay, excellent. So welcome back everyone from the lunch break. I hope you had some good food. And I also welcome you to the second special topic presentation of this workshop of machine learning over networks. As Merton mentioned, the topic is going to be error compensation and variance reduction, which are two methods used to improve the communication efficiency when training a machine learning model over a network. The presenters will be me, Henrik, and 3 other students from the course, Morteza, Filippo, and Ming. We will be presenting these 4 papers, where the first one is on variance reduction and will be presented by me, and the remaining 3 is on the topic of error compensation. The second paper is actually more of a lead up to error compensation, but it does not address it specifically. So keep that in mind that this topic will come later, but this is an introduction to the 3rd and 4th paper. But let's get started with variance reduction. So my assumption here will be that you're familiar with basic machine learning algorithms, but that you have no knowledge of variance reduction. However, even though I think you have a basic familiarity, I still want to talk a little bit about stochastic gradient descent, since this will be a natural segue into the variance reduction part. So in SGD, we have an update of this form. And the specific part about SGD compared to classic gradient descent, as you know, is that we have this random sampling. So we're calculating the gradient based on one random data sample or a small batch of random data samples. And the reason we want to do this is because it's very computationally expensive to calculate the gradient using the whole data set, especially considering that data sets are getting increasingly larger as we tackle more and more complicated problems with deep learning. However, the cost of this is that the updates are not going in the steepest descent direction. As you can see in this illustration up here, we have some illustrations that seem to be going in the completely wrong direction. And this is because of the variance that is introduced when we're doing this random sampling. However, still in expectation, we're going towards the optimum. So we will eventually reach it, but here we are presented with a second problem. And that problem is that as we get close to the optimum, we cannot guarantee that the gradient will be 0. Of course, if we calculated the full gradient, it will be 0 when we get to the optimum, so we would stop. But we still have this random variance, so we will be oscillating around the optimum. And this leads to two things. First of all, the convergence per iteration is going to be quite slow. As I said, some steps will be going in the completely wrong direction, and some will just be taking a very inefficient direction. And secondly, if we want to get a greater estimate than just being in this oscillatory region around the optimum, a common method is to introduce this decaying learning rate to make the steps smaller and smaller, which actually lets us converge despite this stochasticity. But introducing this decaying learning rate harms convergence even further, causing even slower convergence per iteration. And in centralized machine learning, this might not be a huge problem, because if the computational cost of each iteration is extremely cheap, we can afford to do a huge number of iterations. But as we're doing it over a network, we are more concerned with the number of iterations, since each iteration is going to be associated with a communication cost as we reach consensus over the network. So the idea of this variance reduction is to make this stochasticity a bit smaller so that we no longer need to have this decaying learning rate. Because if we don't have the decaying learning rate, then the convergence per iteration is going to go up. The basic idea here is to find some sort of balance between classic gradient descent and stochastic gradient descent, where we for a few iterations calculate the full gradient, but for most of them, we're still going to use this cheaper SGD estimate. In practice, the implementation is that we have a certain interval, let's say every 10 or every 100 iterations, at which we take a snapshot of the current weight vector, and then we calculate the full gradient. So here you can see that we're iterating over the entire data set based on this snapshot. So this iteration is going to be very expensive, but as I said, it might only happen once every 10 or every 100 iterations. So all in all, it's still a lot cheaper than pure gradient descent. The update that was proposed using this method called SVRG has the following shape. And as you can see, these first two terms are identical to SGD. So the only thing we're adding is these two terms in the end, with the full gradient being this final term to the right. So the problem with SGD, as I mentioned, was that the update does not converge to 0, even when our weight goes towards the optimum. So we can approach it infinitely, we can even be at the actual optimum, but we will still jump away from it, since we cannot guarantee a 0 gradient. So what we would like to show is that using this SVRG update, we will actually have a 0 update as long as we are close to the optimum. And what I'm going to talk about here is not a rigorous analysis that is available in the paper, but rather an intuition. So this is a little bit hand wavy, but this is the intuition given in the original paper. So the idea here is that first, if we get close to the optimum, then the snapshot is also going to get close to the optimum. This first set is pretty obvious because the snapshot is going to be a copy of the original weight. So if the weight is close to the optimum, we're going to take a copy. The snapshot will also be close to the optimum. And then here in step 2, we can see that if this snapshot is close to the optimum, then the full gradient is going to be 0. Because of course, this is calculated using all samples. So if this is calculated on the optimum point, we will expect the gradient to be 0. And given that both of these things are true, we can start to look at this update again. So this final term, we now know is 0. So it can be omitted completely. Also, we know that this and this term is getting close to the optimum. So we have something like this, where we have the current weights, or the gradient calculated at the current weights, and the gradient calculated at the optimum weight. Since both of these are very close to the optimal point, this difference should be very small, and this is also going to approach to 0. As I said, this is not a rigorous analysis, but it still gives a nice intuition as of why this update works. And given this property, we now know that if we get close to the optimum, we're not going to jump away. The update is now 0. So we no longer need to have this decaying learning rate, which is why I'm using a fixed learning rate here. And this update has been proven to converge linearly with a fixed learning rate. So when we're talking about training over a network, as I mentioned, we are kind of inherently more communication efficient than SGD because we have much fewer iterations. But we also have a big disadvantage, which is that SVRG is very sensitive to quantization, which is not the case for SGD. So why do I want to mention this? Well, it's because it's very natural when you're training something over a network to quantize the updates in order to have cheaper communication costs for each communication round. But as I mentioned, the whole point was that this full gradient has no stochastic element to it. This is supposed to be deterministic. That's why we calculated with the entire data set. But if we then quantized it before communicating, we're once again introducing some stochasticity to this element. And then we suddenly lose this property that the update goes to 0. So if we just do the naive thing, we just do SVRG, we just quantize the update and transmit it, it's no longer true that this property holds, and we once again have to introduce this decaying learning rate, which slows down the convergence per iteration again. However, very recently, in the end of last year, there was a paper proposed to do this quantization in a different way. So instead of doing this naive approach of just quantizing every update and transmitting it, they let each worker maintain a state. And this state is going to represent the latest gradient that was used in the previous iteration. And then instead of transmitting the full gradient, what you will do is you will calculate this update and you will quantize this difference and transmit over the network. The idea here is that if you quantize the full gradient and get an error, that can be quite a large error in the gradient. But if we have a lot of iterations and we're only quantizing the iteration, then by the law of large numbers, in expectation, these errors should cancel each other out, and we will get closer to the true gradient. And by using this update that contains the state instead of quantizing the full gradient, it has been proven that we can once again use SVRG with a fixed learning rate, and it will converge to optimum in linear time. So this is a really nice result because it kind of gives us the best of both worlds. We can both do this variance reduction method, which was very communication efficient, and on top of that, we can now also use quantization. So we can become extremely efficient as far as communication goes. Here are some numerical results for this. And I know it's a bit messy. We have a lot of different graphs here, but the one I wanted to look at is this green one. So this is Diana SVRG, where Diana is the name of this quantization method that uses the state, and SVRG is this variance reduced method. Then I also want you to look at QSVRG. So this is when this naive approach where we run SVRG, but we just quantize the full gradient. And as you can see here, the difference in loss function can be several orders of magnitude between these two approaches, which is indicating that this new approach of quantizing for SVRG can be significantly better than QSVRG. Also, on the top, we have this quantization method for SGD. We can see that this is even worse. So as if you're in a scenario where communication is your bottleneck, as they have definitely done in this numerical experiment, we can see that using SVRG with this quantization method can have an enormous benefit over using SGD. So to conclude, SVRG is naturally better than, or not better, but it has some advantages over SGD in a communication constrained scenario, since we need fewer iterations to converge. However, a direct application of quantization to this, it will kind of nullify the advantage of using SVRG because we still have a big stochastic component to this full gradient, which we wanted to avoid. But finally, we have this new idea, which is to store the state of the previous gradient and only quantize the difference. And this update can now lead us to converged even with a fixed learning rate, leading to quite good convergence per iteration once again. That was it for the part on variance reduction. And next I will leave the room to Filippo to start talking about the lead up to error compensation.
Hello, everyone. Can you see my screen presentation?
Yes.
Okay. So as Eric mentioned before, I will introduce this paper that talks about stochastic gradient descent with delayed updates, and in particular focus on convergence analysis. But it will be kind of a background for what the next presenter will present about gradient, error reduction technique in gradient descent. So let's start for the motivation for delayed updates in stochastic gradient descent algorithms. And basically the motivation arises from a problem that is the inherent synchronicity of gradient-based optimization. And this in a distributed environment makes the optimization inefficient. This is because if we imagine a scenario in which we have undistributed workers with a shared memory, in a standard SGD, we have that only one machine is non-idle at each iteration. This problem can be kind of circumvented by mini batches method that split the data in n mini batches and compute the gradients in parallel. And at the end of this gradient computation, the workers execute a combined update, maybe through a shared worker. But still, we have the problem that the slowest machine is the bottleneck for this computation, because we need to have all the gradients in order to be able to execute the shared update. So another possibility is to use asynchronous gradient methods. And this released the synchronicity assumption. And in asynchronous gradient methods, the gradient update is possibly based on gradients from earlier iterates that are also known in the literature as stale updates. So more formally, we focus on this convex quadratic function assumption, where f can be written as in 5, where A is a PSD matrix with the APM values in 0 mu, and we denote by mu the smoothness parameter. Also, we have that P is an RD vector and the C is a constant. We also need the assumption that f is bounded from below, and this implies that there exists a minimizer that we denote by lambda star, and this is proved in lemma 3 of the paper. We focus on this term EK, that is the difference between the kth iterate, the iterate of the weight at the kth iterate minus the optimal weight W star for f. And we can write this difference. We can see that the difference between FWK and FW star is proportional to the norm square of this term EK. So we can focus on the convergence dynamics for EK. Let's look at the difference between asynchronous versus asynchronous gradient descent methods more near. We see that the traditional synchronous GD updates are written as in 7. So we have that the weight vector at the iteration k+1 is equal to the weight vector at the previous iterate minus the eta, that is our step size, and the gradient of the previous weight WK, plus a noise term that is assumed the IID, and with 0 mean. If we focus on asynchronous SGD instead, we have a fixed delay tau that is greater than 0, and the update step WK+1 is based on WK, so next previous weight iterate, and the gradient of the weight at time at iteration k minus tau. So basically, we release the synchronicity assumption, and we compute the gradients from previous iterate of a length tau. And we also need this assumption that W0 to W tau is the weights from 0 to tau iterate are the same. And 2 cases are considered in the paper. The first one is where the weight, where the noise term is equal to 0, and this is name the deterministic delayed gradient descent in the paper, and when the noise is different from 0. And we have the stochastic version that is named the stochastic delayed gradient descent. So the first important result of the paper is contained in theorem 1, and it's about DGD. We denote by calligraphic f mu lambda RD, the class of mu smooth and lambda strongly convex quadratic function, and f mu RD, the class of only mu smooth convex quadratic function. And the theorem 1 bounds basically this quantity. So the difference between FWK and the FW star is less or equal in the case of mu smooth and lambda strongly is proportional to W0, the initial guess, minus W star, the norm square of this difference, and the exponential term that depends on the decaying exponential term that depends on the k. So the iteration number and the delay tau at the denominator. And while in the case of just mu smooth convex quadratic function, we have again this tau over tau. It's basically this difference is proportional to tau and inversely proportional to k. And if we do a comparison with the standard gradient descent, we can see that so these are well-known results in the literature, and we also presented it in the machine learning over course lecture. And we can see that there is this term tau doesn't appear. And basically, we have a linear degradation of the performance of the algorithm in terms of convergence of FWK to FW star. And yeah, this is for approximate a proper choice of the step size parameter. The second theorem is about the number of iterations needed to achieve an epsilon error. And we can see that this is also degraded by a term tau with respect to standard gradient descent, because we have this linear degradation of tau for both mu smooth lambda convex and the mu smooth function. Yeah, and of course, for mu smooth lambda convex, we have a dependence of the log of 1 over epsilon, while for mu smooth, it's just 1 over epsilon. And this, in a way, is in accordance to the gradient descent comparison, where we found the same convergence trend. But the important thing is that this tau degrades the performance also in achieving an error of magnitude epsilon in this delayed gradient descent version. So we can reassume the findings as follows. So when tau is bounded constants, these bounds match the known iteration complexities. But meanwhile, for increasing tau, that is of course the most common case, both bounds deteriorate linearly with tau. So this implies, surprisingly enough, that delayed gradient descent is no better than a trivial algorithm that performs first a single gradient step and then waits for tau rounds till the gradient is received. So we have basically that is equivalent to a non-delayed gradient descent with k over tau gradient steps. So next, the authors looked at this stochastic version, and they showed also that this stochasticity improves a lot the convergence guarantees that this delayed version of the gradient-based method have. So we assume that the noise vector xik has mean 0 and the bounded variance by sigma square. And this time, they focus on the expectation of the difference between these two quantities, because we deal with the random quantity, we deal with random quantities. And this O tilde is hiding a polylog factor in the argument. So we have that this difference for mu smooth lambda strongly convex is basically composed by two terms. The first term is independent of tau, and the second term has tau at the denominator of this exponent. And the same happens for just mu-smooth functions. And we have two terms, and only one depends on the tau parameter. Yeah, and they also focus in theorem 4 and the number of iteration needed to achieve an epsilon error, and they have the similar results. Basically, just one of the two terms in both cases depends on the delay. So this is promising because yeah, by tuning properly the parameters, we can make the effect of the delay negligible. So we can reassume the findings again for this stochastic version. So as in the deterministic delayed gradient descent, we have that for constant bounds, these bounds match the known results for standard gradient descent without delays. And also this bound match the delayed gradient descent for sigma square equals 0, as it should be, because stochasticity is a generalization of the just deterministic case. And in sharp contrast to the deterministic case, we have a dependence on tau that appear only in second order terms. And we can make this dependence negligible for epsilon small enough or k big enough. More specifically, we have these results by inverting the results that are found in the theorems that for when epsilon is sufficiently smaller than this term, so sigma square over mu tau, or k sufficiently larger than this big omega tau mu over lambda, then for strongly convex case, we have a negligible effect of the delay. And the same for the convex case. We can make the effect of the delay negligible for epsilon smaller enough than this quantity, sigma square over mu tau, or k sufficiently larger than this other term, that is big omega of the difference between initial guess and optimal weight parameter mu tau over sigma square. Yeah, that's it for my part. I will hand over to Ming for the next.
Hello, can you hear me?
Yes.
Yeah, so here this paper is going to extend the paper presented by Philip, which focused on the stochastic gradient descent with delayed gradient, but also this paper will also discuss about compressed communications. So it will cover the following three parts. The first one is delayed SGD, and the second one is error compensated SGD, and the last one is local SGD. For the first two, the motivation is because the existing works, they're limited to convex functions, like the one presented before. They focus on quadratic convex functions. But this paper is going to talk about non-convex problems and also quasi-convex problems. And for the last one, the local SGD, the motivation is because the earlier analysis, they focus on variant with just one average step, but more practical of the schemes that perform more frequently averaging of the parallel sequences. So the problem they consider is an unconstrained optimization problem, which they want to minimize the function of f over the variable x. Here, f is a quasi-convex function or non-convex smooth function. And they consider different ways of updating on x, including like different delay and stochastic gradient method. I will talk about this method later. And the framework they adopt is the following, which is called the error compensated framework. They use this to analyze how to derive the bonds and the convergence rates throughout the paper. So for x, t plus the update of x is goes on like the following. The x t plus 1 equals xt minus vt. Here vt is the applied update. And then the error, the aggravated delayed information or the errors, et plus 1 is updated. Et plus 1 equals to et plus gamma t gt minus vt. It should be noted that different schemes for updated x, they vary in the way of the form for vt and et. And also here, the gamma t is the step size, where gt is the stochastic gradient. And also throughout the paper, they use the virtual sequences, which is xt minus et for analyzing, for deriving the bound and convergence rate. So next, let's look at the assumptions adopted in the paper. So the first assumption is called mu quasi-convex. But here it's just with regard to the optimal x. It's not related to the whole any arbitrary x. So f is differentiable and mu quasi-convexity for constant mu, which is equal that to the zero if it is satisfied the following equation. So here it should be noted that because here it's only regarded to the optimal x, so this is more general than the mu strongly convex problem we're used to. So this is a more general form, and it is called the quasi-convex problem. And also when mu is larger than zero, x star is unique, and the function is called strongly quasi-convex. Otherwise, it's called weakly quasi-convex. The assumption 2 is the L-smoothness. So this is the same as the traditional L-smoothness. So f is differentiable, and there exists a constant L such that the following expression satisfies. And here it is worth to mention that mu has to be smaller or equal than L to make these two assumptions hold. And the last assumption, assumption 3, is on the noise of the stochastic gradient. So they adopt the bounded noise, which has two parameters. One is m, the other one is sigma square. So for the gradient, stochastic gradient in the form of gt equals to the derivative of f over xt plus the side t. And this gt is conditionally independent noise. So there exists two constant m and sigma square such that the expectation of the noise over the xt is 0, but the variance is smaller or equal than the m times the norm of the gradient squared plus the sigma squared. So this noise model actually generalizes the user assumptions on noise, and it is. So next, we're going to look at the delayed stochastic gradient descent. So it can be casted as in the ECSGD framework we mentioned before. Here, for the delayed, here we assume like it is a fixed delay with t. And so if like the t is smaller than t, then the Vt is just simply at 0. But if t is larger than t, then we have Vt equals to gamma t minus t times gt minus t. And Et is equal to the I from 1 to t, the summation of this gamma and times t. Then the main finding of this is the iteration complexity for mu quasi-convex function f is given by the following expression, which is in the theorem 15 in the paper. So here we look at, there are two terms. One term is the one with the, one term is the left term, which is the determined by the loss sigma square divided by mu times epsilon. Here epsilon is the threshold for convergence. And the second term is related to the time here, which is term times L divided by mu. And similarly for the non-convex function f, it is given by the following expression here. So the things like we could observe from these two equations is like only the optimization terms, the terms depending on the initial error are impacted by the delay term here. So which is the second term here, just only this one impacted by the delay. But the stochastic terms, the term which depends on sigma, are not affected by the delay. So from these 2 points, we can conclude that delayed stochastic gradient, the convergence for any delayed term asymptotically at the same rate as stochastic gradient SGD without delays. So this delayed SGD is a powerful technique to hide communication cost in distributed environments. And then for arbitrary long convex functions, which is the equation down in the bottom, if the number of iterations is larger than the expression here, then this first term, which has term inside it, then this first term becomes small and the effect of the delay becomes negligible. So now let's look at the error compensated SGD. Similarly, we could cast it as, but in the EC SGD framework as follows. So here we add a C operation, which is called the data approximate compressor, and it satisfies the following. So the expectation of X minus Cx, the variance is smaller or equal than 1 minus 2 times the log square of X. So here, if data is very large, which means the compressed information is very similar to the original one. So there's not much compression loss. And then similarly, the iteration complexity for the quasi-convex function is given by the following. Here, if we compare this equation with the delayed SGD here, the only difference is like we replace the time term by the 1 over data here. And the same holds for the non-convex function f. So following the same argument, we could observe that the stochastic terms, the one dependent on sigma in the rate, they're not affected by the delta parameter, which is the compression loss. Where the impact of the compression becomes negligible if the convergence threshold is smaller than delta times sigma square over L. Similarly, for the arbitrary long convex functions, with the number of iterations is larger than the expression given here, then the first term here in the bottom, the first term inside the bottom with data here, it will become small and the effect of the compression will become negligible. Lastly, let's look at local SGD. Here, local SGD means like we have like key users, and each user, they update themselves for a period of time, but then after every third iterations, they are doing a synchronization as follows. So if the term over t plus 1 is not integer, then it means each user just updates its ungraded. But if it is like the term over t plus 1 is an integer, then there's a combination of all the information for other users. Similarly, the iteration complexity for quasi-convex function is given below. Here, the difference is like the number of users matters here. So the number of key appears in the first term of the equation here and also on the second term. And also the delay, the term also matters here. It also holds for the long convex function f. So the findings are here if we compare it with median batch SGD with batch size 8, with batch size k, then local SGD reaches the same statistic term with term timeless communication, but a worse optimization term. And if we compare it with mini batch SGD with much larger batch size, 30, but with the same number of communication runs, then local SGD has the same complexity. But it should be noted that the bound provided here is not optimal. So to conclude, from this paper, we can know SGD is robust to compressed or delayed stochastic gradient updates. And because of that, it can be applied for distributed parallel implementations, where asynchronous and communication efficient methods are the key to achieve linear speed up for optimization with multiple devices. But the thing that we should keep in mind, the analysis in this paper, they are conducted for just unconstrained objectives. So the future work could be extend the analysis from unconstrained objectives to the constrained ones. Thank you. And now I will hand it to the next speaker, Mortiza. Thank you.
Hello.
Hello.
Hello, everybody. Can you see my screen?
Yeah.
Yeah.
Perfect. My name is Morteza Tawana, and I'm a PhD student at KTH. I'm gonna talk about parallel stochastic gradient descent with double pass error compensated compression. So, yeah, as we know, a widely used framework in distributed learning is data parallelism, which is essentially the equation number one. So here we deal with an optimization problem. We have n workers, and we distribute the data among the workers. Each worker, for instance, worker zeta has access to local data di, and each worker should minimize the loss function of model X given data. So there is a standard approach to solve this, which is parallel SGD, which essentially each worker should calculate the gradient, the local gradient, and then they send over network these gradients, and then they will be aggregated and the SGD algorithm will compute the aggregated gradient. However, the problem with this approach is that it requires high communication cost, and this is the main bottleneck. So we need to evaluate this communication cost. The standard approach for this is actually compressing the local gradients by using quantization or sparsification. And then each worker, instead of sending the gradient, it will send a quantized version of the gradient, and then the aggregated gradient will be an approximation of the true gradient. So, and what is the drawback of this approach? It is actually slow down the convergence due to the loss of information. And we need to somehow compensate this. In the literature, they use this compensation technique that they add error compression error vector delta to the gradient before applying the quantization or compression, and then they send it instead of the previous vector that they were used to send. And then they update this compression error at each iteration. These methods can accelerate the convergence because they, again, try to use the lost information. But these are also good for the case when the compression ratio is high. But there is some challenge regarding this approach. It is because they only do this compression only for workers, but not for the aggregated gradient. So the server doesn't do this compression. And this is kind of impractical because it can save just up to 50% of the bandwidth. So for instance, each worker send a sparsified local stochastic gradient to the parameter server and reduce the communication cost. The aggregation of the local gradient is done at the parameter server and then sent back to each worker. And then the aggregated gradient G can become again dense, and G needs to be compressed again. So the solution is that we should incorporate error compensation on the parameter server as well. This is a general idea for double squeeze algorithm, which incorporate error compensation on both workers and parameter server. Yeah, you can see the algorithm here. We have an initial x0, learning rate gamma, initial error 0, and the number of total iterations, which is t. And then for each iteration on worker side, it computes the error compensated stochastic gradient and then compress it by using quantization or sparsification, and then update the error compensated vector and send that to the parameter server. And then the parameters on the parameter server side, it averaged all the received gradients from the workers, and it also adds another error compensated delta to that one, and then compress this vector again and update the error. So these are like the same technique on the parameter server side. And then at the end on the worker, it updates the local model using this equation. So, but for the compression options also, there are several options. Some of them, like randomized quantization and randomized sparsification, they are unbiased, which is kind of good for convergence. And some others, like 1-bit quantization, clipping, and top K sparsification, they are biased. Yeah, these are in detail, you can see what they are, but I'm going to skip this. The findings of this paper essentially is that double squeeze techniques has kind of same convergence rate as SGD, in the sense that both of them has some asymptotical convergence rate of 0.1 over square T of T. It introduced linear speedup, so that it implies that the average sample complexity is O over 1 divided by n epsilon to power 2. Here, epsilon is the error for the related to the quantization. So it is the variance of the quantization. And the advantage of this over non-error compensated SGD is that it has much more tolerance on the compression variance and bias. So even for this case, the bias technique also works. And it's obvious because it doesn't drop any information, or it tries to keep information in both sides. So the experiments essentially shows that here, for instance, we can see the performance in terms of loss and accuracy versus the epochs. There are, I'm going to pinpoint on these curves here. Vanilla SGD is essentially the SGD without any compression. It is a common centralized parallel SGD implementation. Double squeeze we mentioned before, and MEM SGD here is the case that we just do compression on the worker side, but not on the gradient side, on the parameter server side, sorry. And QSGD is the quantized SGD. So the point here is that MEM-SGD and vanilla and double squeeze, they have pretty close performance, but MEM-SGD has used much more bandwidth. Here you can see the amount of bandwidth that they use, and it is much better than vanilla SGD, of course, in terms of using bandwidth. And this scheme is for the case that they use 1-bit compression for the quantizer. So yes, this was the summary of this paper. I didn't go through the details of the theorems and proofs because I thought that it's a bit boring here to see the equations. And yeah, these are references that used during this for this presentation, and yeah.
Okay, so thank you very much for the presentation. It is very important that we see how this other aspect of the communication efficiency on the variance reduction is being taken care of. And thanks for presenting that to us. Do we have any questions from the attendees? Please raise your hand if you have any question. Yeah, so Ali, let me allow you to talk. Yeah, you can talk now, Ali.
Thank you for the presentation. My question is about the last slide about how to reach the MEM-SGD has a kind of the bandwidth, because I can't understand how it has this kind of the bandwidth for the MEM-SGD. Yeah, this one.
Well, for the MEM-SGD, we assume that they use kind of compression on the worker sides. So yeah, but not on the parameter server side. So that's why we have lower bandwidth. So it's actually it can save up to 50%.
Oh, you mean that it needs less than communication between the server and client?
Yes,
yeah,
exactly.
Yeah. Okay, thank you.
Thanks.
Okay, do we have more questions from the attendees? Okay, so no more questions for now. Okay, so then let me ask you a question. So, Henrik, in your part of the presentation, right?
Mm-hmm.
Yes, so you were talking about that it was important that we have SVRG because we can have the variance reduction, and then that we can also make it into the compressed version. So what do you think about extending that for other variance reduction techniques like SAG and some others? Did the paper address that? What is your view?
Yeah, they have already addressed this, and that was part of the results in the same paper. I just chose to limit myself to SVRG because of the time limitation.
I see. Okay, yeah, thanks. So Hossein, you have a question?
Yeah, and it concerns about these form of double squeeze, because let's call them uplink and downlink for the compressions. So I can understand that the first part of the talk was the downlink uplink compression only when the clients wants to push something to the server, like the gradients or parameters or whatsoever, and then they wanna somehow compress that and then compensate for that error due to quantization and all those sort of things. And then in the second part, it was also from the parameter server as well. So the downlink part is quantized, and then how everything can work. So now the question is,
do you think that this error compensation can go beyond this error compensation framework can go beyond stochastic gradients for specifically for these two-way communication part? So let's take, I don't know, like SVRG. Have you tried that out or read something about that? How that can be worked on error compensation plus SVRG, for example, where we do have this variance reduction, which can mess up a little bit with the iteration or the updates of error compensation.
Well, I actually didn't go through that part, but in the figures here, I see something a bit weird, that this double squeeze is a bit better than the vanilla SGD. I think that this should not be like that, because there is no compression. But here I see that it is a bit better.
No, I guess that's just a random thing. Statistically, they are the same as at least as far as I can see here. So they are not really distinguishable, which means that probably double squeeze is as good as vanilla SGD, but maybe with fewer communication overhead.
Exactly.
Now the question is, what's going to happen if we try to apply this error compensation on variance reduction algorithms, essentially, or variance reduced kind of a stochastic gradient algorithms? Have you tried that on how the iteration works or so? It's not immediate to me.
I actually have a comment on this. I think in the end of my presentation, the thing I was talking about, where you save a state and you quantize the update rather than the whole gradient, it's not quite error compensation, but it's very similar, right? It's similar to what Martezza is talking about.
Can you go there?
That was way back, but yeah. Can you do that, or should I share my screen?
Both would work.
I can share mine. Let's see. So I have to bring it back up. Can you see it?
Yep.
Yeah. So that was here, right? So this is something similar where you keep the previous state and you only send this difference in each iteration.
Mm-hmm.
And the idea here is that as long as we have an unbiased quantization scheme, just as Martezza was talking about, like random dithering, then as we're doing enough iterations, in expectation, these quantization errors should take each other out. And I think this would apply to error compensation as well. I've not read about it, but to me it seems like a very similar scenario.
I didn't quite get that. So you mean the error compensation, the memory should be added after this delta G, you mean?
Yeah, exactly. So you're doing in error compensation, you're doing one update just like this, right? You're taking the difference rather than the full gradient update. So if this is how you're storing your memory and you're doing unbiased quantization, then I believe with enough iterations that the quantization errors should cancel each other out.
Could be. It's just, to be honest, it's not really trivial to me.
No, I agree, because I've not read about this, but just my initial thought, at least.
It could be. I'm not saying it's not. Okay.
Yeah. Okay, so no more questions. Okay, so I put in the chat the links for the special topics, and the special topics will not happen in this session, but in parallel sessions. So I suggest you, if you are interested in special topics 1 or 2, to go to these rooms and interact directly with the presenters and ask questions. And yeah, so feel free to join either of them and just let us know if you have any problem, okay? Thank you.
Hi, Vince. Thanks for joining. You can unmute yourself or activate your video whenever you want. So I would wait for like 3 more minutes and then start with introducing you, and then you can take over for your presentation.
Will I be able to share my screen, Hussein?
Yeah, you can try to check that right now if you want to.
Yeah, let me do that.
Sure.
Let me just find my slide.
Stop sharing.
Okay, here we go. Let me see. Do you see that?
Yeah.
And what if I go to full screen? Let me just see.
Sure.
How's that? Do you see that? Is it full screen now?
Yeah, it's full screen.
Okay, good. So I'm going to mute myself for a few more minutes then.
Absolutely.
Let's see, where am I? Hussein?
Yes, I'm here.
Okay, I'm here whenever you're ready.
Okay. So in just 1 minute, I'm start introducing you.
Sounds good.
Is that fine? So I hope that everyone will come soon, because we had some parallel sessions for posters and people were joining different rooms, but probably they will come soon. So I can start introducing Professor Vincent Poor, which is an honor for us to have him here. So Professor Poor is the Michael Henry Strater University Professor at Princeton University, where his interests include information theory and signal processing and their application in wireless networks, energy systems, and many diverse field of research actually. So he has done fundamental contributions to various fields of signal processing, information theory, and optimization, and received many international recognition that I can't really even list them in a few minutes. He's a member of US National Academy of Engineering and US National Academy of Science, and also a foreign member of the Chinese Academy of Science and the Royal Society. Recent recognition of his works includes the 2017 IEEE Alexander Graham Bell Medal, 2019 ASEE Benjamin Graver Award, and honorary doctorates from Syracuse University in 2017 and University of Waterloo in 2019. Well, I know him from his papers, of course, from my bachelor studies working on cognitive radio network like 10 years ago. So like all of you, I'm super excited to listen to his talk on learning at the wireless age. So Vince, you can have the floor and share your screen and whenever you want.
All right, can you see my screen now?
Yep, I can see
All right, fantastic. All right, well, good afternoon, everyone, or good morning, I guess, from me, because it's still morning in New Jersey. I hope everyone is doing well in these difficult times. I wish I could be there in person to see you all, but this is the way we do things these days. Thank you, Hossein, for the kind introduction, and thank you so much for the invitation. I'm really happy to be part of this exciting workshop. Today, just like Denise and Walid, I'm going to be talking, of course, about learning over wireless. And I think we all discussed this beforehand. We're all going to be talking about something a little different. I was unable to hear Denise's talk this morning because it was, well, I was asleep, to be honest with you, in that time of day. But I look forward to seeing the recording of that later. But I think we all have something different to say, so I think hopefully you'll get something out of my talk as well. Machine learning, of course, and wireless networking are two of the most exciting areas of technology development today. Neither one is particularly new. They go back, of course, quite a while, both of them. But right now, there's a lot happening in each field. And in particular, there's a convergence. That is, there's a lot of machine learning in wireless, and there's a lot that wireless can say about machine learning. So it's a really exciting time. And of course, that's why this workshop has been organized, and I'm happy to be here. So what I'm going to talk about today is this. So first of all, I'll just point out, and I think probably Denise also pointed this out, but there's also, there's two connections between these two fields, machine learning and wireless communications. One of them is the use of machine learning to optimize communication networks. And of course, that's a very natural connection because wireless communications has so many problems that involve decision making and inference and other kinds of and control, optimization, all those kinds of things that machine learning can help with. Also, there's a lot of data in wireless networks because, of course, bits are created every, I don't know, billions of times a second. So, there's a lot of data out there, and there's a lot of optimization problems that can be addressed using that data. So data-driven optimization is a very natural thing for communication networks. The other side of the coin, which I think today's workshop mainly addresses, is the use of mobile networks as platforms for learning, for machine learning. And that's what I'm going to talk about today too. I think that's also what you heard from Denise and what you'll hear from Walid a bit later today. But that's what I'm going to talk about. The other side of the coin, that is using machine learning to optimize communication networks, is also an extremely interesting area. And in fact, we had an ICAF tutorial just a couple weeks ago. In fact, maybe it was last week on this with Yonina Eldar and Nir Schlesinger. And I think it may still be available online if you're interested in seeing that. So anyway, what I'm going to talk about today is the following. First of all, I'll spend a little bit of time motivating this, some of which I think is completely unnecessary for this audience, but I'll just to set the stage, I'll go over that again anyway. Then I'm going to talk about two kinds of learning at the wireless edge. One is federated learning, which you heard about from Denise this morning, I think a bit. And the other is decentralized learning. And I'll talk about the distinction between those in a second. And then I'll wrap up with some conclusions. And in the conclusions, I'll talk a little bit about some open problems that I think are interesting, because realizing there are some students and others in this group who might be interested in that. So let me start out with a little motivation. And here's probably a completely unnecessary slide for this group, but just to set the stage, let me go over this. So this is a very simplistic overview of the state of the art in machine learning in general. Okay, first of all, again, it's not a new field. I mean, it goes back many years, but in decades. But right now, there's just been an explosion of interest in machine learning, mainly because of two things. One is there's a tremendous amount of data available, gathered by smartphones, sensors, gathered on the internet, and so forth. So there's just tremendous amounts of data. And there's plenty of computational power to deal with that data. So in both cases, there's been an enabler of machine learning in so many fields. Now, standard machine learning, which is again a simplistic view, is centralized machine learning. That is where you have all the data in one place in a data center or cloud, and you're able to manipulate it as a whole. And of course, there are many state-of-the-art models for this. Deep neural networks is a very prominent one, and these are run in the cloud on big computers. And there's of course standard software tools like TensorFlow, where you don't really even have to know that much about machine learning to use them. And there's a specialized hardware for that, like NVIDIA and Google's hardware. So this is kind of a very simplistic view of machine learning. But that's not what we're here to talk about today, because of course, the reason we're all here today is that we know that centralized machine learning might not be suitable for a lot of applications which involve wireless, okay? And so prime example is self-driving cars. Another example is first responder networks, where you have an emergency where people have to go out and deploy a network very quickly and so forth, or tactical networks where in a military situation where the military has to go out and deploy a network very quickly without the benefit of infrastructure. So these applications all have particular peculiarities that make them different from the kind of applications you might run on centralized machine learning. For example, first of all, the data is already at the edge of the network. That is created on iPhones or IoT devices in such situations. The uplinks, being wireless, typically have limited capacity. These applications involve low latency. That is, we need decisions or learning and so forth needs to be done quickly. And we may not want to induce the latency that we would get from having to go up all the way to a backhaul, all the way to some centralized server, and then download a model from there. And then also privacy is an issue in a lot of these applications. In fact, all the ones I mentioned, privacy is important. And by keeping the data at the edge, we can maintain better privacy, although there's still some issues of privacy leakage even there. And then also there's the issue of locality and scalability. If we do things at the edge, it's much more scalable. And if we only need to know what's happening at the edge in terms of our models that we're building, it's really not necessary to think about backhauling data all the way to some distant point. So all these things motivate moving learning closer to the network edge. And again, I know this is what we're really talking about today, but I just wanted to be sure to put that out there as a motivator, just to remind everyone. So there are three machine learning models then that we can talk about. One is the standard machine learning model that I just described, where data is collected at the edge. It's uploaded to the cloud. Machine learning is applied there with all the data, and then models can be downloaded to the edge as needed. Another model is federated machine learning, which you heard about earlier today, where the data is collected at the edge and stays at the edge, and the end user devices, such as cell phones or sensors, use their own data to create a shared model, or to try to learn a shared model, and then their instantiations of that model are uploaded to an edge device like an access point or a base station, where the models are aggregated and then sent back down to the end user devices for further updating and so forth. So that process happens iteratively until some kind of convergence. And then finally, decentralized machine learning is performed also on end user devices. They collect their own data, they do their own learning, but instead of communicating with an edge device, which the edge device would normally serve like the role of like the cloud, if you would, they just communicate peer-to-peer with each other. So there's not any aggregator that looks at all the models formed by all the end user devices. So this is the decentralized model. And I'm going to talk about some aspects of each of these models. And of course, you've heard others from Denise, and you're going to hear others from Walid a bit later today. So let's get started. I'll start with federated machine learning. And remember, federated learning is the model shown here. Data is collected by end user devices. They're trying to learn a shared model individually. They upload those models, their own instantiations of those models, to an edge device, which serves as an aggregator. That aggregator sends those models back to the end user devices where they're updated, and the process iterates. Okay. So the whole idea is to enable end user devices to do machine learning without centralizing the data. So the key features here are that the end users, which we'll call UEs here, keep the raw data locally. Training is own devices. That is, all the training is done on the end user devices. There's a shared model, so they're all trying to learn the same model. Federated computation, that is an edge node, which we're going to call an access point, collects the weights trained from end users and updates the model. And then that's downloaded back to the end users where the process is iterated. And sometimes I say collecting trained weights here. Of course, there is a model of federated learning, one that Denise talked about, where you send the gradients instead of the weights. But here I'll just think about sending the weights. And then another thing that you get here is privacy by default, because the data never leaves the end user devices. But I put it in quotes for reasons I'll talk about a bit later. Okay, so here's the issue that I'm going to talk about today, the ones I'm going to address now, and that is that communication to the access point needs to go through wireless channels. So federated learning, of course, can be done without being on a wireless platform. But here I'm interested in the interactions between federated learning and the wireless channel. So because of that, there are two things we have to worry about. First of all, the medium is shared and resource constrained. So the second issue, that is the resource constraint, means that at any given update time, only a limited number of devices can be selected by the edge device to upload their models. Okay, so that's just because we have just a finite amount of bandwidth, and typically we'd have many devices and fewer channels for uploading data on each round. So scheduling is an issue. And also because these are wireless links, transmissions aren't reliable due to interference. So we have a lot of devices out there, we have multiple access points and so forth. So there's going to be interference. So two main questions that come up here are the following. First of all, how should we schedule the devices to update the trained weights? So that's to address the resource constraint. And then how does interference affect the training? That's to address the fact that we have a shared medium. Okay, so I'm going to address those now. Okay, so first of all, let's look at some standard scheduling mechanisms and see how they perform in this context. And the work I'm going to talk about now was published in the Transactions on Communications. I believe it was the January issue this year, and you see the citation at the bottom of the screen there. So the three scheduling mechanisms I want to talk about here are, first of all, random scheduling, where the access point just uniformly selects N out of K end user devices at random. So K is going to be the total number of end user devices that each access point serves. And N is going to be the number of channels that the access point can use to serve them. And so N is less than K, of course, otherwise there's no problem here. So that's random scheduling. We just choose N out of K at random. Round robin, we divide the end user devices up into groups. And then the access point on successive iterations just chooses the groups and queries the groups, if you will, in sequentially selecting each group in time. And then proportional fair, where the access point selects the end user devices at a given time that have the strongest signal to noise ratios at that time. Okay, so random, round robin, and proportional fair. And these are all standard scheduling mechanisms, so they're not ones that we particularly developed for this process, but we can see how they perform in federated learning. So now, of course, there are going to be two ways in which an end user device can fail to upload its model to the access point. One is that in order to be successfully updated, or to successfully participate in the update, an end user device has to be selected, first of all. So it has to be one of the devices selected by the access point. And secondly, it has to, the transmission has to get through successfully. So that means that we have to have some decoding threshold, which we'll call theta, just a parameter of the model. And the received signal to interference plus noise ratio needs to exceed that decoding threshold. Okay. So two ways to succeed, or you could think about it two ways to fail, but anyway, both of these things have to happen. Okay. So now a metric for comparing schedulers based on these this context is to look at the number of communication rounds required to reach an epsilon accurate solution. Okay, so now let me say a little bit about that. I don't have a slide on it, but let me say what I mean by an epsilon accurate solution. So we're going to be looking at the problem of maximizing a strongly concave function or minimizing a strongly convex function. So in that case, we know that the primal and dual problems have the same solution. And when we reach, if we solve primal and dual problems and we reach the same solution, we know that we're within, we have the accurate solution. We have a perfect solution. An epsilon accurate solution is one where the primal and dual problems have a solution within epsilon of one another. So if epsilon is small, we're getting, and since we have strong convexity or strong concavity, we're getting close to the true solution. So we're gonna set epsilon as another parameter, and we're gonna look for how long does it take us, that is, how many rounds of updating do we need to go about to achieve an epsilon accurate solution. So there's two parameters, theta, the decoding threshold, and epsilon, the solution, the degree of accuracy of the solution. And within that, and I hope you can see this on your screen, so the type is a little small, it turns out that we can get lower bounds on the number of communication rounds required to achieve an epsilon accurate solution for each of the three scheduling policies: random scheduling, round robin, and proportional fair. And they're given here in terms of some parameters. So let me just say what the parameters are again. So epsilon is the degree of precision of the solution. Theta, which appears down in the denominator as a part of a function, which is just an integral function. Theta is the decoding threshold. Here, alpha is the path loss exponent. And beta is a precision level that can be achieved at the end user devices. So here we're just going to abstract machine learning down to this parameter beta. Okay. So we're not talking about any particular machine learning algorithm. We just say we can get within beta precision at the end user devices. And then N, which also appears here, is the total number of exemplars distributed over the end user devices. So it's not very meaningful to look at these formulas, I don't think, but if we calculate them for a particular example, I think you can see a little bit about what's going on. So we don't have upper bounds, so we're just going to use these lower bounds as surrogates for performance. And this example shows that performance. So here we have an example, and this is a computation of those bounds for a particular case. And we're looking at two cases on the left and the right. So on the left, the decoding threshold is high. And what that means is that the channel is not very good. That is, we have to have a very high SINR in order, or you might think the code is not very good. We have to have a very high SINR to achieve, to get the message across. And on the right, we have a low SINR threshold, which means that they actually have a very powerful link and we don't need much SINR to get the message across, get messages across. So, and then on the left, in red, you have random scheduling, in blue, you have round robin, and in green you have proportional fair. That's on both of these charts. So you can see that if we have a less powerful code, proportional fair is much better than the other two. It has a lower number of communication rounds. And that's intuitively, that makes sense, because if you need a really good channel to get your message across, then you're going to choose the channels with the best SNRs, right? Which is what proportional fair does. And that's borne out by the chart on the left. On the other hand, if you have a really powerful code and you don't need a lot of SINR, you might as well just use round robin. And that's what the right side shows. In other words, just go through sequentially and let all the, choose all the end user devices in sequence. And you're going to do well, and the others are not going to do as well. So basically you're letting everybody report in turn. And because you have a very low decoding threshold, that means that basically all of those reports are going to get through. So these lower bounds, although they are only lower bounds, they do give us sort of an analytical way of looking at this that agrees with our intuition. We can also do an actual a machine learning problem using these various schedulers. This is basically training a support vector machine on MNIST data, which I'm sure you all know is handwritten character recognition data. And here we've chosen 10,000 sample points and distributed them over 100 devices. And N here is 20 and K is 100. And we look just on the left, we look at loss, which is mean squared error here, I think. And on the right, we look at accuracy, which is % correct. And you can see that indeed, in this case, round robin is better than random scheduling. And I didn't put the decoding threshold here, but the decoding threshold here is a low decoding threshold. So this agrees with what we saw in the lower bounds. And quite remarkably, actually, you can see the distinction. So we see that scheduling does matter. I think that's the bottom line here. And so another question might be, can we optimize scheduling in some way? So those three scheduling techniques that I chose, or those protocols, are just standard ones. So is there something that might be better or optimal for federated learning? So let's address that problem briefly now. So one metric we can apply here is one that might be familiar to a lot of you from other contexts, and that is age of information. So age of information, of course, is a widely studied metric now because of Internet of Things applications and applications involving energy harvesting, where sensors or other remote devices have to be careful about husbanding their energy, and therefore have to optimize when they transmit information to a central location. Now here, that's the kind of problem we have, but we're going to use it to optimize for a different reason, not necessarily for energy savings, but for savings of communication rounds. So here we're going to define it as following. For a given end user device I, the age of information at a given round is 0 if that device is selected. Otherwise, if the device is not selected, that age of information increments by 1. So we can think about a little counter, T sub I, which counts the age, or which increments the age as long as the device is not selected. And then when the device is selected, the age drops back to 0. So SI of T is an indicator which says it's 1 if device I is selected at time T for uploading, and 0 otherwise. Okay, so it's a simple little iterative process. And then what I'm going to talk about now is actually another paper which appeared just at ICAPS just very, very recently. And I think it's probably still online if people want to go out and see the presentation by Howard Yang, who's at SUTD in Singapore. So we can, given age, we can actually set up an optimization problem that minimizes age within some constraints. I'm not going to give the details of that here, but it's in that paper if you're interested. But we can look at some numerical results here based on that. So again, I'm looking here at a support vector machine trained on MNIST data, the exact same problem I looked at just a minute ago before getting into this part. And I'm comparing two things here. One is a wireless round robin in blue. And again, on the left is loss. So small is good. On the right is accuracy. So large is good. And then, so that's the wireless round robin is the one that minimizes the average age. And the other one is maximum pack, where we try to choose pack the maximum number of end user devices into the spectrum as possible, okay, at a given time. So you can see that compared to maximum pack, wireless round robin is much, much better. So minimizing average age seems to be a good way to go. I'll just point out that the age has to be, the average, the selection is on a update by update basis. So every iteration, we have to solve the age minimization problem, but it's a problem that has polynomial complexity, so it's not that hard to do that, okay? All right, well, I'm gonna shift gears now and talk about decentralized learning. And just remember that decentralized learning is the situation where we no longer have the edge device involved, so there's no aggregator. So all we have are end user devices, they collect data, they're doing learning on device, and they may be communicating in a peer-to-peer fashion, but they can't necessarily communicate with the whole network. And although I show it here, them communicating with the whole network, but not necessarily they wouldn't be able to do that. And there's no aggregator, so they're just, all we can do is communicate peer-to-peer. Okay. So to talk about this problem, I want to backtrack a little bit to some work done about a decade ago and talk about a general model for distributed learning, which includes federated learning, decentralized learning, and centralized learning, all in the same model. So in this model, we have the following bipartite graph model for learning. So first of all, one layer of this graph is the training database. So of course, training database means a set of exemplars. What we're trying to do is to learn a function mapping inputs to outputs. That's a general machine learning paradigm. And the inputs are X's and the outputs are Y's, or the outputs are also called targets, right? So we have a training database, which just is a set of N training examples. So that forms one part of the graph. And then we have a set of learning agents, which could be sensors or what have you, could even be the cloud device, of which there are M, and that forms another layer in the bipartite graph. And then the edges in the graph connect nodes into two layers, depending on whether a given learning agent can view the data of a given datum in the training database. So you see here, like learning agent 1 here, L1, which is a triangle with the L1 in it, can see the first, third, and then another training data exemplar, and can learn from those, okay? So this is just a general model for distributed learning, and special cases involve centralized learning, where you just have one learning agent that is connected to every training exemplar, or decentralized learning, where you have the learning agents actually, you can think of the training database residing on the learning agents, and you have the same number of learning agents as you have data, training examples. So the data is fully distributed, the learning is fully distributed. Federated learning could also be viewed as like this, where the learning agents are the edge devices and the training database corresponds to the end user devices. Okay, so now I'm going to be talking about decentralized learning, where the number of learning agents equals the size of the training database. So you have a data point on each learning agent. All right, so a natural way to learn in a situation like this is to do local learning. So that is, we're trying to fit a function mapping X to Y. And we're going to do that by using least squares, some kind of regularized least squares. The learning agents, each learning agent is just going to perform learning, in this case, kernel learning, but it could be any kind of learning, on its own, on the data to which it has access. Okay, so F1 is going to use the first, third, and that other learning exemplar to learn its version of the function f. F2 is going to do the same, L2 is going to do the same, all the way out to the last learning agent. Okay, so that's a very natural way to learn in such a model, but it has a problem, and that is that it's generally locally incoherent. That is, if you have two learning agents that share an exemplar, like here I've called out F1, L1 and LM, they're each going to learn their own version of the function f that maps the x's to the y's. And when they apply their version of f to x1, they're each going to get a different output, that is a different target. And generally, those targets will disagree because they learn from different data sets. So they're not going to learn exactly the same function f. So this is called incoherence. And it turns out that it's provably non-optimal. That is, you can show that if you have an incoherent set of f's, that there's a better set of f's that is coherent and it has a lower overall least squares. Okay, so this is not good. It's good from the point of view of communication, but it's not good from the point of view of optimality. So we might ask the question whether there's some way that we can preserve the communication structure of this graph, that is the locality of data, and get away from incoherence. And the answer is yes. And this comes from an old paper, as I mentioned. It's a decade ago with a former PhD student of Sanj Kulkarni and myself, Joel Pred. And this algorithm works in the following. So let's just look at the case where we have 4 learning agents and 7 training data. So let's think about that. So what happens is the first learning agent is going to learn from its data, in this case, the first, second, and 6th exemplar. It's going to get an estimate of the function f from that learning. And then instead of stopping there, it's going to write its estimates of the targets back down into the database. So it's going to overwrite Y1, Y2, and Y6 using its estimates of those targets based on its function it learned. And then we move to L2, which is going to repeat that process. It's going to learn from its data. It's going to overwrite those targets. And then we're going to move on to L3, same thing, L4, same thing, and then iterate and iterate until convergence. And it turns out that if we do that, that is, if we learn and overwrite the targets, that process eventually converges to a coherent relaxation of global least squares. So, by relaxation, I mean relaxation to the given bipartite graph. Okay, so here we can get that by doing this collaborative technique where we write back in the database. And of course, you can see that they're basically sharing information by doing that. So the database is being used as a way of transferring information from one learner to the next, even if they don't have access to the same data. Okay, so let's see how that works in an example. So here's a case, a very simple case where we're going to have 50 sensors uniformly distributed between -1 and 1 in a linear fashion. And each sensor is going to observe a function of its location plus white Gaussian noise, IID Gaussian noise. And here we're just going to, for this example, just to show how this works, we're going to choose the regression function to be linear. Okay, so f is just a linear function of position. And then we're going to define the graph by defining neighbors. So 2 neighbors, so each, so the sensors are going to be the learning agents, and they're going to be the training data resides at the sensor. So m equals n in that model I showed you. And then the graph is connected by defining neighbors. So a learning agent I is connected to a training datum J if the positions of sensor I and sensor J are within R of each other on the line between -1 and 1, okay? So that's how we define neighborhoods. And then the sensors are going to employ linear kernels. So this is kernel learning, reproducing kernel Hilbert space learning that we're using in this particular example. And so what's shown in this chart is 3 types of learning. So first of all, this test error is mean squared error here in determining the function f. And what's on the horizontal axis is R, the size of the neighborhood. So as R gets bigger, we go from, for small r, we're very highly decentralized. As R gets bigger, we're going closer and closer and closer to a fully connected bipartite graph. And the solid line, which you can hardly see because it's almost at 0, is the performance of centralized learning. That is, if R was equal to 2, so that everything is connected, that would be the performance we would get. Now, the dotted line at the top is the performance of local learning. That is the learning that I told you is incoherent. And you can see that it's not very good. You have to have a pretty big neighborhoods all the way out to 0.6 in this chart before you really hit the performance of centralized learning. So you have pretty big neighborhoods, a lot of connectivity. And then the dashed dotted line, the one between the two, is this algorithm that I just told you, this collaborative algorithm, which we call SN train in this chart. And you can see that it's pretty good, even very low connectivity, but with even 0.2 of R, it's already achieved the performance of centralized learning. So this shows you the power of this technique that I just mentioned. It really helps you overcome the disadvantage of incoherence that you can get from local learning. All right, I want to talk about one more thing, and then I'm going to wrap up. So we've been talking about learning where we're doing function fitting or optimization or minimization of a function or what have you. And now I want to talk a little bit about reinforcement learning very briefly in a decentralized fashion. So of course, I think you probably all know, reinforcement learning is about finding a decision or control strategy in Markov models, okay? Markov decision processes, when you don't know a model for that process, okay? And a particular type of reinforcement learning is so-called Q-learning, where basically on each iteration, you update a Q function and that contains the payoff, trying to converge to an optimum. And if you do centralized reinforcement learning, you typically use gradient descent or gradient ascent to find the optimum, okay? Now, in a distributed setting, like we're talking about here, we can't do classical gradient updates involving all the data. We can only use local data at each learner. So what can we do? Well, first of all, if we just use distributed gradient descent, we don't necessarily get to an optimum. But if we take classical gradient updates, local gradient updates at each learning agent, and at the same time, we also do another update based on consensus among neighbors, then it turns out that if we have the right kind of connectivity in the network, we can get convergence of this kind of dual updating to global Q values, okay? As long as we have connectivity, and there are also some tuning parameters in the iteration and so forth that that have to come into play. But giving those kinds of typical kinds of assumptions, we can get convergence to global optimality. And this is actually shown in this paper shown here. Again, it's not a new paper. It's from 2013 from the Transactions on Signal Processing. It's with Shomo Carr and Jose Mura. Shomo was a postdoc in my group in those days, and we did that work. He's now at Carnegie Mellon. And so we can that's proven in this paper. And I'll just illustrate it briefly here with an example. This is a toy example where it's kind of the simplest possible reinforcement learning problem, where we have binary states and binary actions. We assume here we have 40 agents, And we build a graph by using 2 nearest neighbor connectivity. Okay, so that's how we build a graph. And then on the left, we show how the Q value, so there are 4 Q values here because they're binary states and binary actions. So we look at how do the Q factors converge for centralized versus distributed or decentralized learning. And you can see that centralized here is dotted, so they converge rather quickly. But the distributed also converges rather quickly to the same values. So this just illustrates what I told you, that what I said, that you can prove convergence to centralized values, and you see that in this example. This is just for a typical agent out of 40, but you could choose any one of them, and of course they'd all show the same kind of behavior. And then on the right, this just shows how the consensus works. We choose 10 agents, and we look at their Q factors and over time, and you can see that these are just 10 chosen at random. You can see that over time they all converge to consensus. Okay, so that affirms this behavior as well. All right, well, that's a very interesting problem. I'm not going to talk about it now. We're actually still working on some problems in distributed reinforcement learning, and hopefully we'll have some more results going forward, but this is just sort of a basic problem that shows how that works. All right, so let me wrap up. I think I'm about out of time anyway. So first of all, the first conclusion, which I think we're all here today to talk about anyway, is that wireless networks can be platforms for machine learning. And I talked about 2 things. I talked about federated learning, where edge devices, which we can think of as being access points, interact with end user devices, which we could think about as being smartphones, to learn common models, okay? Then I also talked about decentralized learning, where end user devices, which here could be smartphones or sensors, smart sensors of some type, just interact in a peer-to-peer fashion to learn collaboratively, or to learn models, or to learn actions in the case of reinforcement learning. So I promised to talk about a few issues for research here, and let me throw some of these out, and undoubtedly people at this workshop are already working on these, and there may be other papers on these, but I'll just put these out there for people to think about. One is model efficiency. Now, in what I've talked about, particularly the first part, really I haven't looked much at the issue of the fact that the end user devices are limited devices. I just abstracted the machine learning in the federated learning model to a very simple abstraction, the precision of learning. But really, there's a lot going on at the end user devices. There's energy limitations, there's storage limitations, there's computational power. If it's a smartphone, what you're doing is competing with all the other functions of the phone and so forth. So there's some fundamental trade-offs here between, for example, the number of layers, the number of neurons per layer, energy expenditure, accuracy, and so forth that could be looked at. And of course, end user devices often have very simple learning algorithms, like all the weights are plus or minus 1 or things like that. So all these issues could be looked at in this context, and I think there's some interesting work to be done there. Another issue has to do with the communications itself. So we're talking about basically a lot of devices uploading their over wireless, uploading their models. So they're sending messages, but those models are correlated. So these are not independent messages, really. They're all learning the same thing. So there's some correlation in the models that are being uploaded. And of course, if we have correlated sources in a distributed setting, that's a classical problem in communications, distributed source coding. And so it's possible that distributed source coding could help lower the number of rounds we need, or allow a greater efficiency or something like that. And this also is something that we're looking at tentatively right now. We haven't really got results yet, but one of my postdocs is currently looking at that problem. Another issue is that when we're talking about learning at the edge, we're not really talking about big data. We're really talking about sparse data. So it's sort of the opposite of the sort of big, TensorFlow kind of problem that people think about in modern machine learning. These are problems where we have small training data. So small data, right? These are training sets are small. So that, and of course in wireless settings, or in most settings that we're familiar with in wireless networks, we do have models. It's not like these are model free. So an interesting approach would be to try to incorporate some domain knowledge into the learning at the edge. That would make this both make the models more powerful that we learn, and also it would play a role in lowering the complexity of learning. Okay, so deep unfolding is, for example, is a technique that's been developed over the past few years for that kind of learning. So I think there's a lot to be done there. We actually have some work going on at Princeton too, but again, very, very early stages, so I don't have anything to report there. And then finally, another very interesting problem, and I talked about this earlier just briefly, is that of security and privacy. From security point of view, of course, like every wireless network, there's all kinds of possibility of man-in-the-middle attacks, that sort of thing, malicious end-user devices, you know, and so forth. So these algorithms need to be made secure against that kind of attack. And so I think that's another area that's ripe for research. And there are things going on, but I think it's still a lot to be done there. And then finally, I'll just mention this privacy. You know, one of the things you hear about federated learning is that it gives you privacy by default. But in fact, it doesn't really, because the machine learning, if you do go through and derive parameters of a model from data, there's correlation between those model parameters and the data. You know, so that's really a place where privacy can be broached or breached in these kind of algorithms. So a lot of interesting questions there, as they're really information theoretic questions, I think, about how you can, how much information can leak through parameters in machine learning and so forth, and how we can mitigate that using various privacy paradigms. So that's, I think, an interesting thing as well. And again, there is work going on in these areas. I think we're going to see a lot of developments over the coming years. Anyway, that's my talk. I'm done. Thank you very much. I don't know if we have time for questions or if we have a way to get questions here, but I'm happy to try to answer any that people may have. Thank you.
Yeah, thanks a lot, Vince, for the fantastic presentation. So we may have something like 10 minutes for Q&A, and I know that you have another meeting afterwards, so we try to keep it fast.
I'm okay for about 10 minutes, and that'll be perfect.
That's great. So we have one question in the Q&A, which says essentially about decentralized reinforcement learning part. So the question says, who sends essentially the environment updates information to the agents in decentralized reinforcement learning?
Oh, in the decentralized case, it's basically peer-to-peer. So if I'm one of the end user devices, I'm communicating directly with other end user devices in my that I'm connected to. So my peers, for example, in a sensor network, your peers might be those other devices that are within communication range of you. So it would be device to device.
Okay, that makes sense, I guess. So Henrik, you can unmute yourself and ask your question.
Can you hear me?
Yep.
Okay. I was wondering about this age of information-based scheduling scheme. To me, this seems like a good metric to use since you ensure coverage of all the users and therefore the whole data set. But at the same time, it's just one metric, right? I mean, you have no channel awareness. You're not aware of the fading in different channels and such. I was wondering, have you done any work on combining this?
That's a very good point, actually. I like that a lot. So first of all, when we do minimize the age, we do have constraints. I didn't put the minimization problem up that we're due, but we do have constraints for various channel issues, okay? Energy constraints and so forth, rate constraints and what have you. So there are some of that does come into the optimization. But you're right. I mean, there are known channel conditions and so forth and so on that could be brought into play. But again, the algorithm does take some of that into account by enforcing rate constraints and so forth. So you wouldn't choose devices that have poor channels just because they have old ages, because there's a constraint that makes that that would mitigate against that. Okay, unless their age got really, really old, and then that would have maybe overcome poor channel. But you're right. I think there's a lot more that can be done there. I mean, this is just a paper, a conference paper, and I think we're still working, and I think there are others who are interested in this problem, and I think there's a lot to be done. It's a good point.
Okay, interesting to hear that there's more work to be done in that direction.
Okay, so any more questions? So if not,
we have one in the Q&A.
Okay. Yeah. So, okay. So the question is the federated learning is one of the one-hop communication between edge and sensor devices? How about multi-hop communication?
Yeah, great question. So that'd be very interesting to look at, actually. You could have a relay, for example, in there. I think it just gets more complicated. But certainly from a practical point of view, that's probably what you're going to have, especially if some of the devices are at the far edge of a cell, for example. So yeah, I think that's an interesting question. We didn't look at it. In our case, we really abstracted everything down to just the SINR for single hop. And you could certainly introduce another level of complexity where you have multi-hop or other things of that sort. I think the whole range of, wireless data transmission could be imposed there in one way or the other. You can look at all kinds of things, right? And I just think we looked at the simplest possible model just to try to get some idea of comparison of these things. But other, sure, other things might work. You could have intermediate aggregators, right, that could aggregate a few local devices, and then those aggregated models could be then sent to the edge device. So you could have a relay that aggregates at the relay, and then the relay could forward a few aggregated models to a central aggregator that could aggregate everything. So you could have a hierarchical structure. There are a lot of things you could do, and we haven't looked at those, and I would encourage people who are interested to explore those, because certainly in real networks you do have those kind of opportunities.
I guess that there's also some other works, a very old one in high performance computing, which has nothing to do, of course, with wireless communication, but it's like an abstract graph theoretical sense of view. Then you can somehow try to optimize your computation over some graph. And then those graph, as it mentioned, could correspond to some form of like a cluster of nodes doing some computation, collecting them, relaying them. So that's very interesting. So the next question is about the scalability of decentralized reinforcement learning. So is it scalable to hundreds of nodes? And then the next one is how to deal with the non-stationarity of the environment.
Yeah, so it is scalable completely. I mean, I guess it depends on. It is completely scalable. I think the scalability of the number of nodes is not such an issue. It's more, it may take longer to converge, because one of the issues you need to worry about is connectivity. And I don't mean fully connectivity, but I mean connectivity in the sense that you can get, that a piece of information can get through intermediaries from any point in the network to any other point. So if you look at the graph Laplacian, it's I guess its second eigenvalue is non-zero. So the larger, of course, the larger the network is, the longer it may take for information to diffuse around the network. So I don't really know the constants in that convergence that would bring that into play, but certainly, there would be, if you had thousands of nodes, it would take longer to converge. Okay, but the algorithm itself is fine because everything happens locally. So computationally, it's completely scalable, but it's just going to take longer to converge. I forgot what the other
The other one was about the non-stationarity of the environments.
Yeah, so then of course it's a question of it's a race between convergence and convergence speed and the dynamics of the network. So like any adaptive, basically reinforcement learning is adaptive control, right? So like any adaptive control problem, there's a tension between convergence rate of the algorithms and dynamics of the process. And the same thing appears here. I mean, we haven't really looked at a dynamic environment, so I don't really know what that trade-off might be and where the sticking points might be in that analysis. But I think it's a really interesting question. And again, it's a question that comes up in every adaptive control setting.
Yeah.
I mean, you don't need, let me just say in that response to that question too, I think it's a great thing to ask, because you don't really need adaptive control if you don't have a dynamic plan, right? So, the problem is dynamic in general, and that's why you need to do adaptation. And so there is always that tension, and I think that's an interesting thing to study in this context as well.
Yeah, I guess that if the optimal solution is like time variant, then as you said, there is this trade-off between how fast we can find that optimal solution and how fast we can find the trajectory of the optimal solution, essentially. But that's one question that can be applied to any kind of optimization algorithms, essentially, not really necessarily to this failure.
Yeah, and it's an essential question. I mean, I'm not trying to minimize the question. I think it's probably the question, for practical application. And some of it is just experimental too. You just have a certain kind of time variation and you apply your algorithm to it and see if it tracks.
Yeah, due to time limitation, maybe we can just ask one more, and I can see that there's at least 5 more questions. So the next question was, how do we take care of non-coherence in decentralized machine learning? I guess that we have answered that a little bit. But...
Non-coherent, you mean the lack of coherence? I'm not sure I understand. Yep. Is it lack of coherence in the
learning strategies? So that was.
Yeah. So I guess that was the point of. I think I understand the question. I mean, that's kind of the point of the collaborative learning. The incoherence comes from the fact that you don't modify the data at all as you're learning, and if you go and update the targets iteratively, then you can get rid of the incoherence. Basically, that's sort of the point of that technique that's in that paper with Joel Pred and Sanj Kulkarni. I hope I didn't misunderstand the question, but listen, I do have to go, but I'm happy to, if people want to email me, I'm happy to continue this conversation on email with people. I'm happy to answer further questions.
Yeah, thanks a lot. So we can probably combine the questions and then ask you later on somehow.
Okay.
Thanks a lot for the presentation. A fantastic talk.
Thank you, Hossein. I'm sorry I have to go. I've got a 4-hour meeting on Zoom, so I'd much rather be listening to the talks here or looking at the posters, but I got to go.
Yep.
All right. Take care.
Yeah, you too. Thanks a lot.
Bye-bye.
Bye for now.
Bye.
So if you have any question, feel free to send us those questions, and we're gonna combine them and then ask Vince or create this communication channel between you. But also you can ask some of those questions. I guess that almost most of them are applicable to the panel discussion, and you can ask. And now we have the panel discussion. So Carlo, you are the moderator, and you can take the floor. Carlo, can you hear me?
Yes.
Okay.
So good afternoon, everybody. And now it's time to move here to our panel discussion here. Hossein and Mayrton have put together a distinguished panel of speakers. And In particular, we have Denise Kudus. We have already heard from him in the morning. Then we have Walid Saad from Virginia Tech. We have then Petar Popovsky from Aalborg University, and Hamed Farhadi from Ericsson Research. And I don't know if our panelists are already here, connected. I can see Denise and
yeah, Denise as Hamed are here, but I cannot see Petar and Walid.
Walid is here.
Yeah, I can see Walid as well. So Petar, if you are in the attendees, maybe you can raise your hand so I can see your account. Yeah, I see. Promote. So Petar, you are user 1234 or not? No, he wasn't. Maybe you can start, and then whenever Petar joins, he will join you.
Okay, let's do like that. And finally, my name is Carlo Fischione. I'm a professor in the Division of Networks and Systems Engineering in KTH, and I'm supporting Mayrton and Hussein and Mayrton in the organization of this course and workshop today. I would like to start now with a simple question just to warm up ourselves. Then I will go through a little bit more technical or technological questions, and then we will have also opportunity to get the questions from the audience. So the audience that I see very numerous, please already start to prepare questions that you would like to ask, and especially questions that should be of a higher, so to say, abstraction level. I would like to ask first that to every panelist, if you have any personal somehow reason or feelings why you started to work with machine learning. Is that any episode that has happened in your research or in your technological readings that motivated to work in this area?
Shall we go just random order, or how do we do it?
Yes, the first who wants to exactly to answer is welcome.
Okay, I mean, I can start since I'm the first in those photos. Okay, so maybe I should actually also share start the video.
Dennis, you sent me some introductory slides, and if you want, you can go through them. Just if you want to.
I mean, I shared some slides because, I mean, yeah, you asked these 3 slides. To be honest, I didn't know what to include them. So since I already gave the talk as well, I mean, they're not needed. So let's say, I mean, let me answer this. Let's continue, and then somehow there is the need to use the slides. Then I can refer to those. But to answer this question, kind of how it started. I mean, in my case, I can luckily say that, it's not because of the, kind of just because now it's popular, everybody's doing it, and then I'm also doing it. I mean, it could be the case, that's fine, in many kind of cases, of course, you kind of, I mean, there are certain reasons, of course, why certain topics are popular, and then you might just kind of get interested in that because of the kind of the, let's say, social pressure. So in my case, luckily, actually, I started a bit earlier. And to be honest, like the main reason was that, so my PhD was on information theory. And at some point I was a little bit bored of, doing kind of similar things. And actually, I mean, reinforcement learning, because it was kind of this Markov decision process background of, reinforcement learning seemed something actually that's aligned, let's say, with my information theory statistical background, and it was something different. it wasn't as popular as it was at that. I mean, it was like 2010, 11. So I was at CTTC in Spain. So there were some people who were doing these things, you know, like even much earlier. So that's how it started. But then I was a bit lucky that when I joined Imperial, as opposed to kind of the normal expectation that I, instead of joining the communications and signal processing group within the electrical engineering department, for completely practical reasons, I joined the intelligence systems and networks group, which is basically the group that does the machine learning. And that's how I kind of started talking to people, learned about, you know, neural networks, you know, etc., and then, you know, started collaborating. So yeah, that's how it started.
I remember in the year 2013, 12, that people started to somehow to speak about, and my perception from the opinion of many people is that they were very skeptical about this. But then we have seen that actually there is a need, it's a technological need, and this has for sure reinforced the interest now in the community to work in this exciting area. Yes, it's interesting that things started in a way that many people perhaps discount ideas and then they convert again in the future. Very good. Walid, do you want to?
Yeah, I could go next. So thank you for inviting me to this panel. So I started in learning. It was really part of my PhD. So I finished my PhD in 2010, but we can say we started around 2008 because my PhD was really focused on multi-agent games, and the game theory is, I mean, reinforcement learning and learning in general comes, hand to hand with game theory. So at that time, we used to use it a lot to basically characterize the equilibrium of a game in wireless, right? So you have, let's say, simple power control to more elaborate cases. So we just, I mean, it really continued as a flow. So it was not really a major change of the work that we've been doing. It's just like, we had more neural networks over the time, maybe back in 2000, early on in deep learning. We used it a little bit also in my PhD. We looked a little bit also at this type of classification for security, basically in the days of cognitive radio. So we used some sort of unsupervised learning, so Bayesian non-parametrics at that time, to basically characterize the transmission pattern of primary users. So there were these two big threads which we've been working on, and it just kind of continued with, of course, the new things that started to appear, which were like basically add-ons on that.
There was a natural transition in a sense from your research.
Yeah, it was not, I mean, maybe we rebranded from ML to AI, but it's basically the same.
And very good. It's Hamed, do you want to add if he's online?
Hello, everyone.
Hello.
Thank you, Carlo, for giving this opportunity to be part of this panel. My name is Hamed Farad, and I'm a senior researcher at Ericsson Research. I'm working on AI technology for 5G and future 6G standards. So, well, I would say that my first exposure to this AI domain was a long time ago. Maybe back 15 years ago, when I was trying to implement neural networks at that time on FPGA, when I was undergraduate students. It was a very challenging task at that time, but now due to the vast developments that we have seen in the computational domain and also in the algorithmic domains, these kind of algorithms are very much reachable everywhere, and nowadays we are trying to enable platforms that these type of algorithms could be available everywhere, using this wireless network as a platform for learning and learning models and distributions of the knowledge through the networks. And this is a very exciting time to be. And So
excellent. And you now you're working on these topics from Ericsson. So Ahmed now is the so say in the panel the industrial research representative.
Yeah, if there is a time, I may share a slide somehow
Yes.
reflecting our
That's what. Yes, please.
Okay, let's see. Could you see the slides now?
Yes.
Okay, so I would try to briefly go through how we see AI could potentially have impact on future 5G and 6G networks and systems. I think many of the topics that has been covered in today's workshop and the invited speakers was very insightful and also are part of this journey. And okay, so yeah, artificial intelligence, as I mentioned, is expected to have an important role in the vision of having intelligent, sustainable, and connected world in coming future. So it is expected that massive number of intelligent machines to be connected to the networks. And these intelligent machines that come from very wide area of applications, including intelligent transportation, medical healthcare system, smart grids, and many more vertical applications would require to train models based on the data which may not be locally available. So it is expected that these machines try to connect to the networks to both have access to massive amount of data for training and also to the computational resources that are available in the clusters and clouds. And also the machines may need to interact with the other machines or humans to have kind of supervisions for the training of the models. In this journey, actually, we would expect the machines, depending on their computational capability and also other factors like privacy constraints and considerations, try to train the models over the cloud or over the edge or do it locally in the device. And due to this, actually, we expect that in the short term, we have kind of a huge amount of data uploading to the networks to be processed centrally in the cloud systems. And over the time, we expect that as the hardware mature and the computational becomes less and less expensive at the device side, the devices try to train their model locally, and we have the networks only for coordinations of these trainings and the transfer of the models among different machines and different domains. And we in this industry side also see that there is a rapid development in the chipset, AI-friendly chipsets, the chips that are dedicated for AI processing, and this would reduce the cost of the AI processing and would be a factor that make these technologies to be available everywhere. Another domain that is very exciting and interesting from the wireless communication perspective is the development that we see in the smart material domain. So the development in the smart materials enables to to have some kind of control over the propagation environments. This is something new that we traditionally we haven't seen in the communication domain. In the conventional communication system, we have been focusing on the designing of the transmitters and optimizing the transmitters and also the receivers for given propagation environments. But now, thanks to these materials that could be controlled and adjusted by AIs, there is potential to manipulate and adjust the propagation environment so that improve the quality of communication. In another domain also, we see kind of new ways of interactions with the environments, thanks to technologies like virtual reality and augmented reality, that would require kind of models to be trained at the edge or at the devices, so that enable low delay communication while we maintain minimal traffic to be transferred to the networks.
Hamed, I wanted to. I have many questions that I would like to ask for every one of these boxes, and then I suggest that I keep these questions for that are a little bit more technical for later on.
Yeah, sure.
And then if you can, you could conclude your quick introduction, and then we could move.
Sure, I just wrap it up, and then we can wait for the questions as well. We also see the huge opportunities to developing AI-assisted air interference algorithms that could substantially improve the existing physical layer algorithms that we have for handling the communications over the networks. And by this, I would be willing to hand over the control to Carlo. So that
thank you very much, Hamed. Then I suggest that we have Petar, who has also just joined.
Sorry, hello. There was a glitch in the connection, but I joined already before Dennis started, so I have followed all the introductions.
Okay, very good. And I wanted to start first with a general question on somehow what was the personal reasons to start working in this domain, machine learning and wireless, and before going a little bit into more the technical discussions.
So I have a couple of slides. I can just say that I'm not really, I'm not really still working on machine learning in the same way that I have never worked in statistics. But it's what I'm trying to do is I'm trying to make sense of what type of problems we want to solve and where it makes sense to use some tools which have been developed for machine learning, which are data intensive. So maybe I can share some slides which I have. Is okay?
Absolutely. Yes, please. You should be able to share. Yes.
So as I said, is for me, I mean, I don't have I've never produced a result in machine learning, which it's also similar to the case that I've never produced a result which is significant in statistics, but I'm trying to understand what is the interplay between communication and machine learning. So I'll be fast here. So normally we are looking into the issue of algorithm deficit and model deficit and in certain problems. We are looking into the problems and hypotheses we want to address, and we are looking whether we can use traditional model-based approach or traditional algorithms specified by certain mechanism, proof, and so on. And then we can use machine learning to address problems which are not inherent to the networking capability. What I mean here is, for example, I will illustrate two problems, but I have actually segmented the problem space into three parts. First is problems that are not inherent to the network capability, but are related to communications and machine learning. Second are opportunities arising from the network capability. And third one are constraints arising from the network capability. So I'll go through this now. And this is the way I understand how the problem space is segmented for communication and machine learning. So in the first case, when, for example, there are transmission schemes like designing of a modulation scheme, designing of I don't know, resource allocation thing, which is difficult to do without machine learning because of the complexity. So we apply machine learning to search certain larger space. Then I started more seriously to look into the machine learning tools like 2 years ago when I realized that we have talked a lot about ultra reliability in 5G, but ultra reliability was always based on some models. And actually you cannot offer ultra reliable communication if you don't understand the statistics of the environment where you work. And this is naturally giving the setup of statistical machine learning that needs to be used in order to guarantee certain levels of reliability. Another practical problem that we have started to work on was that a company approached us to say, we have this IoT traffic, the devices are sending quasi-periodically. We don't know whether the device is off or it's just it has a period which is unusually large. And this was not possible to address by usual statistical model. There was some model and there was some algorithm deficit. So we have actually approached that using machine learning. So let me just briefly mention this. In transmission schemes, for example, we made this work where we looked deep learning and applied it to synchronization and channel estimation in NB-IoT. So basically the problem doesn't exist because of machine learning. We have just addressed it using this machine learning tool. In the network troubleshooting, we have made this work where we had a lot of data from
I've lost the voice from Peter. We have a little technical problem. We cannot hear Peter. Let's see if we can resolve quickly. Not, no, it's
connection. Can you hear me?
Yes, now we can hear you.
Yes, okay. So it counts as I said exactly when I speak about ultra reliability, the connection failed, which is it's a sign. So what I'm trying to say is that you cannot guarantee high reliability without having data. So to offer high reliability, we need to have model selection, learning procedure, and then performance evaluation, which is based on statistical machine learning. I'm trying to say that offering high reliability without data-driven methods and machine learning is impossible, simply. Because you cannot guarantee 10 to the minus 5 reliability without having tested an environment where the system should operate. It's a statistically paradoxical setup if we don't use data-driven methods. And then finally, I mentioned the two other places of the problem space. I think there are opportunities arising from the network capability. And here I'm thinking, for example, the distributed computation, which is helping to solve certain complex algorithms by delegating it to the interconnected nodes. There's also the interesting approach of meta learning, where we can have networked what's called entities, which are exchanging some of the features and some of the data related to their models, where they're basically training. And in this meta learning process, they're trying to help each other in a certain network setup. And but there are also constraints arising from the network capability, and they also gave rise to new problems. So one is, for example, the privacy problem of federated learning, where a lot of people in the communication area work because there's a communication cost and there is also privacy constraint. So how do we solve this problem? So I see this is a opportunity in the network setup to share the data, but still you have to protect it based on some privacy requirements. But I personally think one of the absolutely most interesting aspects is the cost of data and the data markets, because we will need more data to train. The question is, who has access to this data? What is the value of the data before training? What is the value of the data after training? So you might be paying for getting a lot of data, but then you don't know whether this data is going to help you in your learning and prediction. And actually, there are some interesting work starting in that area. So with this, I will conclude my briefing work.
Thank you, Peter. I think that also this somehow shows that your research trajectory is somehow encountering naturally machine learning problems, and then this is triggering your curiosity to work in this domain. And at this point, I wanted to start the discussion here with again this sort of warming up question, but then we have Ahmed and Peter who have given a very interesting technical slides, also with some technical point. Then I would like to also give to Denise and Walid the opportunity if they would like to show their slides.
Sure, I can go ahead. Just
please,
give me a second.
please, Walid.
Yes, just a second. I have I prepared like 4 slides, somewhat aligned with Petar, but without the nice matrix. Let me just quickly make this work. Do they appear?
Yes.
Okay. So I wanted to think a little bit also, what are the use cases of machine learning? So basically in 5G and beyond, but let's say wireless in general, right? So first, the first question I would ask is why, right? Why we would need machine learning from that? And I asked this question particularly because in the past when we used to work on it, and Carlo, you mentioned that early on, it wasn't very popular. So people were always skeptical. So the question is really why we want it. So one quick answer is basically relates to the last part of Petar's basically matrix, which is that machine learning and AI will be part of wireless networks, even if it's not used for communication. For example, car or autonomous vehicles will use it for their navigation. And at that point, there will be an intersection between machine learning and wireless. So there will be an interaction between them. And the second aspect is we're clearly heading towards less rigid protocols. And this has been seen going from, let's say, the early on cellular systems all the way to 5G and beyond. So the system should be able to operate itself by itself. And what I mean by that is not just at the network management side, but also on the radio, right? So in terms of radio resource management, in terms of basically even modulation, adaptive modulation encoding, and so on and so forth. And there's this, of course, I put the third bullet, it's probably the first one that comes to mind, is basically the prediction side, right? So caching appeared a few years back, and it was probably one of the first ideas where machine learning is very clear, database machine learning. So from there, you can think beyond that, of course. So based on this, I would identify 3 roles for machine learning in wireless. The first one is, as I mentioned, this data analytics. And I would say that's already there. Caching is a good example for that. So it's not really very far-fetched. So you are collecting some data from the users, and under some privacy constraints, the operators could be able to use them for something useful. The second use case is more this basically self-organizing or AI-driven optimization and control. And that is where things come between, there's an intersection between optimization and machine learning. And the third is essentially this edge learning, which federated learning is, of course, a part of it. So, just elaborating on the 3 use cases in my next slides. So first, yes, in terms of data analytics, when we talk about an application like a smart city with all the IoT environment there, you would have like a data hurricane that wireless networks have to, if not manage, at least use, right? So how can we make sense or make use of this data from various sensors or even from the devices of the users, with, of course, the advent of applications like virtual reality, even the user himself, like how does he move? How does he turn his head becomes important data for wireless design, right? Because if you think about the quality of experience in a VR setting, you would need that data. And I think this use case one is probably pretty much everybody likes it and everybody knows it's really probably the first entry point in terms of ML for wireless. The second one is more the one where perhaps I work more on than the first one, is where you would have tough optimization problems. They could be difficult because of unknown information, like you don't know, for example, activation of devices. You don't know certain evolution of the wireless channel. So there are some uncertainty which you cannot have. And if you formulate an optimization problem with some uncertainty, to solve it, you have two options. Either you assume some distribution, you use some stochastic optimization tools, which is of course fine, but that still has a lot of assumptions and still, relies on some models. Or you go into the route of reinforcement learning, whereby you say, okay, there is some uncertainty. I cannot use traditional optimization, and can I design an algorithm which can, with deep learning, it can do some prediction, but even without deep learning, that can solve that problem. And when you go a little bit more distributed by, let's say, multi-agent, let's say multiple base stations trying to optimize the power without a central controller, then you have this intersection between RL and game theory, because the foundations of the optimization problem is really a game, in the sense that you have a series of, let's say, n optimization problems. Their solution is what we call a fixed point equilibrium, which is a Nash equilibrium in the game theoretic sense. And you can use a multi-agent RL or a variant of it. And this is where also things like meta RL comes into play, where you can also use some sort of control to improve, training, to improve the speed of your solution. And finally, I think the workshop itself is dedicated to this topic, which is what we call edge learning or distributed learning. So most classical machine learning algorithms rely on the leftmost paradigm in my figure, where you send data to a cloud, and the cloud does some processing in it. On the rightmost side is the federated learning algorithm, where you send your basically your model parameters, and you try to learn a common distribution. What we think of as a potentially more interesting use case in a wireless context is the one in the middle, which is more like collaborative federated learning, whereby there are multiple users. They could be different, learning similar, but maybe not exactly the same distribution. And they're trying to communicate over the network. And here, I think Petar covered it well. You have two different angles. One angle is, I can use federated learning to improve whatever, D2D communication, let's say, to improve some sort of communication metric. Or the reverse is true. I have a federated learning algorithm or a collaborative learning algorithm running, and the question is, what is the communication metrics needed to make it run well? So I will talk later in the actually talk about the impact of like transmission errors, of delay on these sorts of algorithms. So I think that's kind of a broad view on where I see ML working in wireless. And that's really my last slide.
Thank you, Walid. Thank you. It's extremely interesting. And I don't know if Denise wants to have one slide, although you already mentioned that maybe not. But I would like to give you the chance.
If for the sake of time, we are doing better not to do it, or I can just briefly show, maybe like very quickly go through them. It's up to you.
Please, you can show that.
Okay, so I think we are all kind of converging the same type of like classification of problems and where ML and communications come together. So that's why I'm not going to go into much details. So the first one I had in mind was also basically ML and communications, which is more or less what I talked about. So this is actually, let's say we want to do some machine distributed learning, whatever kind of type of learning we want to do. And somehow, because either the data is distributed or the agents are distributed, the processing is distributed. So now we like it or not, now they have to communicate. And now we have to design the type of communication system that is, for the particular learning application in mind. And of course, then there is the, I think very similar to also the previous kind of classifications is the ML for communications. So I think when you also mentioned that, when people started using ML for communications, some other people, let's say, being skeptical, was more about, this aspect, because, the first aspect, basically, there's nothing to be skeptical about, because, if you have to do, like distributed kind of learning, you have to communicate somehow. But, and I can kind of understand why people were skeptical for, ML for communications, because this is, as opposed to, let's say, some of the most kind of popular ML applications where all this kind of most striking results came about. Communication problems, at least the problems that we had in mind, were things that we had very good solutions, right? So we had all these kind of amazing networks, like internet over wireless, so on and so forth. So, I mean, what could kind of machine learning get us, and how could this be even better than it? It is still not clear, actually. So this is, I think, research-wise is very interesting, but we still don't have any of these things actually implemented on kind of designing the communication aspects of the network using these ML tools. But I think, I mean, here basically I put some examples. I'm not going to, of course, like mention these at all, but I think the potential here is, either problems that we didn't actually have solutions, right? So good solutions like communication with feedback, like joint source channel coding. I mean, we kind of went around these type of problems. So we built things that work good enough, but we knew that they are not optimal, and we didn't know how to do things even close to optimal. We didn't even know what the optimal is. So I think for that type of problems, and these are becoming more and more kind of pressing, I think ML has a lot to say. And again, I think already mentioned before, kind of these two aspects which are related to security and privacy. So either using kind of machine learning for secure and private communications. This is again related to the ML for communications, but with the security aspect. And again, typically the problems are very hard, so machine learning can help us. And also kind of, for example, some of these kind of concepts, privacies, that are very difficult to quantify. Or let's say, I mean, we can, for example, define privacy statistically, like I can measure information leakage by the mutual information, but its practical meaning is actually not clear. So we don't know if I leak, I don't know, 3 bits per sample of mutual information. So what does it mean? Is it private? Is it not private? Whereas kind of, we can use this kind of adversarial training, etc., to get, let's say, more data dependent measures. Of course, they're also questionable in other aspects. And then, the coding for secure private ML is the kind of area where, again, tools from coding theory, information theory, communication can play important roles. This kind of relates to also some things I already mentioned in the talk today, but, I didn't touch upon this aspect, but, again, so the whole point is that, these tools we know work for, security privacy in general, for secure private communications. Now they can also be used for machine learning problems. So that's all I want to say for now.
Thank you, Denis. Then let me somehow try to make a sort of very rough summary that if we look at the research going on here for machine learning and networks, machine learning and wireless, very, very roughly, we can say that we have two categories. And one is how to do machine learning over networks, over some wireless networks. And the other category, research category, is the usage of machine learning for redesign the wireless, the networks, and for the optimizations and for the protocols. And it seems that also based on the various use cases that we have seen from Ahmed Eriksson, that there is a clear technological need of having machine learning over networks, machine learning that where data is distributed over devices and so on. And the other category of the usage of machine learning for redesigning protocols and wireless is less obvious, and it's perhaps still many important open questions. Therefore here my question here, I would like to hear your opinion from a scientific, from a technical point of view. Is it what would be now more intriguing to work with? Is on the first rough category that I mentioned, or on the second?
I could give a quick answer. I think for someone entering the area, the first, which is machine learning over networks, is a bit of an easier, with a bit of less barrier to entry, because you're a comm theorist, right? And then you can just see it as another application running over your network, and you would focus primarily more on the comm challenges. On the other hand, the second area, there are some fundamental ML challenges, and it would require a little bit more knowledge in how ML works and what doesn't work. So I think that's kind of my very brief view.
Do you think, Walid, that it's something that machine learning will really create some breakthrough in fundamentally new protocols? What is your feeling?
So I think that should be our goal in some sense, right? So I mean, we know that applying some of the machine learning solutions has some interesting results, and we've seen that in a lot of works. But we know also there are many limitations, and working on resolving those limitations is important. For example, when we talk about using RL for let's say adaptive network optimization or resource management, we know it works well, but we also know that there are convergence and reliability challenges. Convergence in the sense that some of the RL tools are slow to converge. We all admit that. We have solutions to that, but I think we need fundamentally new results there to make it, let's say, amenable to deployment in wireless. Second is, for example, RL is not reliable. When we talk about applications where you might encounter wireless network states that you haven't seen before, RL can adapt to it, but it takes time. And it depends a lot on the training, and we don't have a lot of data. So we would need some magic there to redesign some of the algorithms or combine techniques even to make things work. So that's why I say that, yes, we would have protocol breakthroughs, but it's not obvious. And it's not gonna be, let's take this deep Q-learning, run it on our wireless system, and it's great. Doing that, I mean, we've done that maybe 5 years back and worked well, but now is the time to go beyond that.
It seems to me that in this regard, the application of machine learning over IoT and wireless network is again, it's clear technologically motivated, and we see very tangible use cases. But then this other way, that is the design of the wireless using ML, at the moment it looks quite risky. So we don't know whether it will be actually convenient or not. And so it's an area with more uncertainties in a sense, a research area. What do you think?
Okay, sorry, go ahead.
Yeah, go ahead, please.
Okay. No, I was going to say, actually, I mean, exactly for the reason you mentioned might be actually kind of a motivation to look into, this problem more. Because, I mean, I agree that, of course, the data from IoT, how do you kind of generate machine learning algorithms, this kind of anomaly detection, et cetera, et cetera. So you can do a lot of machine learning on network data, either, data collected from wireless devices or even data about the network itself. But to be honest, actually, in my opinion, in academia, I mean, because actually those applications are, very promising, and actually they might have direct kind of applications. I expect, and I see companies are much more onto those, and it might be a bit difficult actually to compete with them, when there is such kind of commercial potential. So if from my personal perspective, actually, I mean, it's more risky kind of direction. Might be more appropriate for academic research, because that's also kind of more open, things, we can come up with things that are maybe not, so much conventional now, but, hopefully for the future, they might change things.
Yes, it's my own personal opinion that I agree with you that in a sense, to do research on the application of ML over IoT, we know that there is research gaps, but also we know what we would expect if we solve those gaps. In the other case, if we instead do research on the usage of ML to radically redesign wireless, we at the moment it's very risky. We don't know what would be the results yet, but nevertheless is intellectually very stimulating and might make much more sense to do this research in academia, since on the other side, the other kind of research can be well done by companies that would like to build new services and products. But Ahmed, I guess you wanted to add something here.
Yeah. Well, I may add a point here, actually, as Denise mentioned also. Actually, we have huge amount of data that are generated in the physical layer and also network layer of our communication network to handle or basically to enable the communication. And this data is somehow hidden from the application point of view. But actually there is a huge potential to exploit this available data, which is in a sense big and huge, and develop models that enhance and improve different components of a communication link. Yeah, there would be big potential for in this path as well for the telecom industry, I would say, to improve the efficiency and like the many different performance metrics that we could measure, and yeah, I would mention that there are two aspects. One is those part of the communication system that we could well design theoretically, like for example channel coding. So we know how to design a good and maybe the best channel code to cope with the situations, but there are some other aspects that we need to rely on the data. For example, the propagation environments, the hardware components that might have some kind of imperfection, and many of those aspects that we do not have very kind of concrete analytical solutions. And we could benefit from this huge amount of data that is generated through the network and train the model and do prediction, classification, and inference, and kind of do data-aided decision within the network to improve the network performance.
But Javed, do you think that if you can reveal that Ericsson believes that maybe in 10 or 15 years from now, radically new wireless protocols will allow us to do something that is much unexpected now? And what could be that?
We would expect that this kind of technologies to be more present in the future air interface as well, and somehow benefit from these technologies. We may not have kind of radical change, so it would be kind of the evolutions of the system that we have, and but it would be more AI-friendly networks and systems. So we are going to have AI or network by, the AI in the design process to make this learning and training over the network and for the networks consistent to the network design that we are going to have.
Very good. I think Petar, you wanted to hear also comment or.
Yeah, so I have a little bit of, on one hand, cautious look on this design of the protocols, because, you know, for many years we have talked about cross-layer design, revisiting the layering and so on. But the layering has not been changed radically. And the reason is that it has not changed radically because this is the way the systems are scaled. So you can find a way that that you can do some cross-layer design within certain setup, but that will not scale to different scenarios. That's why, you know, the layering as we know it is one of the best ways to scale the systems, also backward compatibility and so on. So having said that, we also have to go back to see why the protocols we have designed, they are divided into layers. And there are in principle three reasons. One is to simplify the problems because we could not deal with this complexity of design. Second is to modularize them, to basically to enable different providers to provide different modules, like in object-oriented programming. And the third one is architectural scalability, right? So because this can scale, if you come up with a better design of another module, you can design it as long as it respects the interfaces. So the key point in the current layering that we have are fixed interfaces and modularization. So what I'm thinking is that imagine that we remove this requirement, that the interfaces are fixed, then the machine learning algorithms or AI algorithms would actually work to negotiate different interfaces between two modules or multiple modules, and in this way define the communication protocol on the run. You see, this is one opportunity where over a long run there can be evolution. So we should not think that the protocols have fixed fields, fixed state machine, but this state machine is kind of evolved based on interaction between different AI modules. That is one way, and another way is that we look into what use the low-hanging fruit there is to go back to see which problems have been very difficult in the past to deal with in protocol design, and which ones we have simplified in order to to solve them. If we don't need to simplify based on our approach with machine learning, what could we change? Could we change how the ARQ protocols work? Could we change how the TCP works? Because ARQ protocol and TCP are things which you can describe by hand, and machine learning is solving problems which you cannot describe by hand. And so that means that we have to go back maybe to those problems. But I think the most radical change will be if we learn how to make protocols without standardized interfaces.
This is it appears still quite futuristic, because as we know, many industries now are working with the usage of the standardization, and they build the chips and all the electronic circuits. So it's then perhaps this could be that in the beyond the 5G, I don't know if it will be 6G or 7G network. So we will need to have, so to say, a slice that is reserved for wireless-based designed and for machine learning that is used to redesign the wireless. So we'll have one slice at least for a transition, and then maybe in 30 years, 20 years from now, ML might have even a more prominent role.
Yeah, but we can, for example, standardize certain control channels and procedures, and based on which they can negotiate another type of protocol. Right? We're doing that at the moment, but what negotiation is doing relatively simple things. For example, choosing adaptive modulation encoding. That's a negotiation, but that again you can solve it by hand. The question is what can be negotiated that you cannot solve by hand.
Mm. And also, what would be the big advantage, right, in these new negotiations? What is that we will be able to do that today we are not in the position to do?
Yeah, but keep in mind, as I said, that the protocols have been made to respect certain architecture, in a sense that, for example, they are following the postal service of routing. So let's say if you have a letter to your neighbor, and if you use the postal service, it will take you to the post office and then back to your neighbor, which is totally inefficient, but it's scalable. The question is, how will the protocols in the future figure out what are the local optimizations which without compromising the overall functioning of the protocol?
Yes, this introduces perhaps or somehow allows me to restate what you already mentioned, that there will be a higher degree of autonomy in the future networks, less sort of rigidity.
Indeed.
And I guess also Hamed had mentioned something about this in his rows with these boxes of activities. But there is also another, there is a concept that I wanted to mention that, and is connected now to this these research questions, that when I believe in the 1920s or 1910s, in the beginning at least of the previous century, people were doing experimentation to send information over wireless and to improve protocols. And then all of a sudden they discovered that between a transmitter and the receiver that were a few hundred meters far away, and they discovered that when a car was going through, which is somehow big metal object, and there were strange variations in the radio strength and in the received signals. And so this somehow data-based observation then has led to the creation of very efficient radar systems. It might be also here the case that if you try to remodel, to apply machine learning over wireless networks and for the design of wireless networks, something totally unexpected will emerge that could have a groundbreaking effects in our daily life. At least this is one of the things that we can hope. Please, Ahmed, yes.
Yeah, this is an interesting area that you mentioned, Carlo. So we do envision that the networks or the wireless radio networks that we already have as a kind of basic infrastructure that we have widely spread over different countries and different regions. In future, they may not be only used for communication purpose. This radio infrastructure could be used for a wider range of applications, for example, for radar application, for localization purpose, for energy transfer, and many different vertical applications. And in this wide range of applications, it is envisioned that they could potentially benefit from the collected data. So we could see that the radio networks would be in place, but not only for the communication, but also for wider range of applications that could potentially benefit from the different type of data that are collected and the models that are trained. So
yes, a few years ago, I was, I think about 5 years ago, I heard that the base station networks that Ericsson has can be used to do very accurate weather forecasts, just looking at the received signals and the way they are attenuated by the atmosphere. And that so it's a service that is absolutely not communication service and comes from some sort of data analysis, machine learning from information from the wireless networks. Okay, now we need to finish relatively soon. We have been speaking for almost 1 hour. I think we will have about 5 minutes more. And I have not, so far, I have not picked the questions from the audience. And I wanted to give the chance if there is anyone now in the audience that has question. And I have got at least a few technical questions, but some of them we have been already debating. One is this, for example, is how to incorporate knowledge domain into machine learning workflow and how much it can improve the performance. And is it tough with deep learning? This technical question. Anyone wants to? Again, do you think that there is a way to incorporate a knowledge domain into machine learning workflow?
I may take this question. So there is potential to using this kind of like transfer learning approaches, have these different models or that are pre-trained in different environments, and these models could be possibly distributed over the networks and where specific users could fine-tune the model based on very limited data that it has. So it's envisioned that this kind of transfer learning together with the pre-trained models in different domains could enable this fine-tune models for various range of applications that could be enabled by the networks in the future.
Thank you, Hamed.
Maybe I can mention something, Carlo. I mean, the thing is that let's go back to this design of protocols and communication schemes. By focusing on a certain part, for example, of the communication system, you're using domain knowledge, because you say, okay, now I want to design a retransmission scheme, so it has to be in some sense following some ARQ protocol, state machines, and so on. And the interesting thing is that domain knowledge can help to speed up this, but it can also be restrictive, because you are not maybe asking the questions, what else I can remove from the domain knowledge that I know and search a larger optimization space, right? For example, instead of having ARQ protocols with the feedback 0 or 1, you can work with protocols that have a richer feedback.
Yes, so that's an important concept to keep in mind, that the design space and the knowledge can be much wider, and it's good to try to look to expected solutions, but also unexpected solutions.
I also want to add to very shortly, because this, I think, something that comes a lot, you know, so kind of as if there's this kind of dichotomy between, you know, like either we use our models, optimize, you know, this kind of model-based approach, or there's this kind of complete extreme, you know, neural network, whatever base thing, that solution that, you know, we just, you know, put the data and then it learns whatever. But I think, you know, and also, I mean, if I read the question, you know, like this kind of, it mentions that, okay, you know, how do I learn my wireless domain knowledge kind of to use machine learning? I think the main issue is that, you know, in wireless, as we talked, so we already know a lot of stuff, right? So we already know many kind of coding schemes, modulation schemes, etc. So the issue is that, I mean, we can reuse a lot of that information. For example, I mean, just one kind of specific example, but I think it kind of exemplifies this aspect very good. That so we look at this kind of compression problems. So we use, you know, in general, we know that data compression is very difficult, and even, you know, all these years of standardization, whatever, you know, we have this image compression standards, but now people are already doing better kind of compression with neural networks. But in one component there, you know, after you kind of do this kind of feature extraction neural network, at the end you do lossless compression. So now, you know, with lossless compression, we know how to do. We have actually information theoretically optimal kind of, you know, entropy coding schemes. So now there's no point to use a neural network to do that. So I think that is kind of this type of places where you put together your domain knowledge, you know how to do certain things, you know how to model certain things, but you know where to kind of also, you know, as Petar mentioned, you know, relax the constraints, and, you know, and you don't do things, you know, like, I don't know, you don't relax the constraint too much. For example, you know, make the power a real number, right? So we know that, you know, like as wireless, you know that the power has to be limited. So I think basically you need to know kind of both aspects and, you know, put these two together.
Absolutely. Very good. At this point, we don't have more time, and unfortunately, I cannot get more questions from the audience. I guess that our speakers will be also happy to answer over email if they get any question. And I really would like to thank everyone of our distinguished speakers to have dedicated their precious time to this event today. And now the program is that we have a 10 minutes break, and then we restart at 5:45 with the talk of Walid.
Carlo, I guess that we have already consumed all the break for the panel. So if it's okay with Walid, maybe we can start after just 1 minute or two. Or if you need some more time to rest, we can just give like 10 minutes.
It's up to Walid.
Yep.
I was able to join back. Sorry, I was disconnected. My Wi-Fi router restarted.
Oh, sorry. Yeah, so the question was that we have consumed all the time for this 15 minutes break for the panel discussion. And if you need some time, we can give something like 5 or 10 minutes break. Otherwise, you can just start.
I can start. Again, I'm sorry, I don't know what happened. It's just, yeah, I can start.
That's absolutely fine.
Yeah,
so thanks a lot to Deniz, Petar, and Hamid for this fantastic talk. I really wanted to personally ask lots of questions, but that's the problem of having limited time and limited resources that we're talking about all the day. Thanks a lot for joining this panel discussion. And if anyone has some more questions, maybe you can ask us, and then we can relay these questions to the panel members. So thanks a lot. So now we can go to, well, we have already done that. So now we can go to the talk of Walid. I would just give like 1 minute introduction to Walid, and then he can take the floor. So Walid Saad is a professor at the Department of Electrical and Computer Engineering at Virginia Tech, and the director of the Network Science, Wireless, and Security Lab. His research interests include wireless networks, machine learning, game theory, security, UAVs, cyber-physical systems, and network science. He's a fellow of the IEEE and an IEEE Distinguished Lecturer. He received many recognitions for his publications, including 8 Best Paper Award, the 2015 Fred Ehrlich Prize from IEEE Communication Society. He's a recipient of the NSF Career Award in 2013 and Young Investigator Award from the Office of Naval Research in 2015. Also 2017 IEEE ComSoc Best Young Professional in Academia Award and the 2018 IEEE ComSoc Radio Communication Committee Early Achievement Award. Also the 2019 IEEE ComSoc Communication Theory Technical Committee. And I guess that these lists go on and on. He has also received the Dean's Award for Research Excellence from Virginia Tech in 2019, and he currently serves as an editor of the IEEE Transaction on Wireless Communications, IEEE Transactions on Mobile Computing, and IEEE Transactions on Cognitive Communications and Networking. He is also an editor at large for the IEEE Transactions on Communications. I'm very excited to hear about 2 novel perspectives on distributed machine learning. So Walid, you can have the floor and share your screen whenever you like.
Yes, thank you so much. I'm trying to share the screen now. So let me know if it is okay. Should be okay now.
Yeah, now I can see a screen.
Okay, great. So thank you all again once again for this invitation. So today's talk, I'm gonna talk a little bit about like 2 different angles of distributed machine learning. I guess one of them was partially probably covered in Dr. Poor's talk, but I look at it from a different perspective, and it was a collaboration with him actually. So I'll start with a very quick introduction. I mean, based on the program of the workshop, I guess you heard a lot about these the basics this day. So I'm gonna be very brief there. I'm gonna talk about 2 different very specific problems. The first one is about what we called in the panel machine learning over networks, or what I'd like to call communication for machine learning, where I'm gonna look at a specific problem related to federated learning. And the second part is a little bit more on the learning side, where we look at the idea of having distributed GANs and how that can work. And I have some overview on our broad spectrum of research outside. So as we discussed a little bit early on, so in original, let's say original application of ML was really big data, right? And it was like you have a lot of data that will be concentrated on a cloud and something will happen with it. But we're now moving towards a different paradigm where you still have a lot of data, but this data is small. So you have small data distributed across multiple devices, and you want to make sense out of it. And this data is often private, and I guess Deniz talked about privacy a lot. So you do not want to share this data, but at the same time, you want to collaborate with others to come up with a meaningful learning task. And that task could be anything from keyboard recognition to self-driving navigation. So federated learning, of course, is one of the most popular tools for performing what we call distributed learning. The idea is everyone can keep his or her own data, but we can still share some sort of our neural network weights and come up with a learning task. So the classical federated learning usually rely on a single common task among the devices, but of course that can be generalized. So with that in mind, we wanted to think about, I mean, and this is one of the probably the first thoughts in this problem, is if we deploy federated learning over a cellular network, right? So in terms of learning, let's keep it as it is. Let's not contribute too much there, and let's look at what wireless can do for learning. And this is a problem I wanted to look at today, which we call, I mean, on the slide, you can see communication for learning. And of course, there's the flip side of the coin. I have a slide on that at the end, where we can use federated learning to communicate or improve communication. And in general, we wanted to see if there are multiple learning agents that could be using federated learning, working over a wireless network, what would the wireless network impact on the learning, and how would that change your results, let's say, from a learning perspective? So looking at the figure, one example way to deploy federated learning is you consider a number of users. These users have a local federated learning model. You can see it here. I guess the pointer now appears. And this model, they're trying to learn a common task. And as you know, in federated learning, there's usually a controller. We assume it to be the base station here that collects the weights, the model weights, the vectors from these devices, and comes up with a global model using aggregation. Again, the simple FL here we're gonna use. I'm not gonna be too sophisticated with the federated learning, but of course you can extend. So just again, the couple of quick slides on the federated learning training. The training process is basically looking at minimizing the value function, which is function basically of your weights, of your input and output data, and the number of training samples. Okay, so if you run federated learning in any context, you would be solving some kind of this optimization problem with some variance. And it has been shown to converge and to work well in a classical sense, let's say, without a wireless environment. So again, this is the federated learning training process. You would have the base station transmit this global model, which we call G early on. The users update their local FL model with their own data, and they can also do their own iterations. And then they would transmit the local data to the base station, and this process continues on and ends up usually with the final trained model for everybody that is common and that supposedly works well. Now, this local and global parameter exchange in the machine learning literature is usually done over what they call a communication, quote unquote, channel, which has a bandwidth, but they don't go more into that. So what we wanted to do is to replace that black box with an actual wireless network, and based on the the deployment I mentioned before. And when you do that, you immediately notice that there are at least 3 effects that the wireless network will have on this transmission. One is the wireless transmission errors. I mean, even in the most reliable wireless networks, we cannot get 100% error-free transmission. So the impediments of the wireless channel from fading to interference will affect your federated learning performance. And of course, there's the issue of delay, because you're looking at the convergence time here and energy consumption. So how do these come into play in an FL over wireless? So this is, again, this is the standard training process. I'm just repeating it here. So you can do centralized training if you're not federated learning, or you can do the distributed training. This is just a zoom in on the previous slide. I'm deploying federated learning over users 1 to U. They're transmitting their global models to the base station transmits G. And here on these blue and red links, there will be transmission errors. And we're gonna see what happens with these transmission errors. How do they affect this essentially gradient descent, right, algorithm? So how do they affect that? So formally, we consider a cellular network, 1 base station, U users. It's the users are transmitting in the uplink their weights to the base station. The base station sends back the global updates in the downlink. We focus mainly on the uplink here. We assume the downlink bandwidth is high enough, so we're not going to look at errors on G. And this is a work that appeared for a while now, and we've got a couple of revisions and should be out soon, where we talk about this joint learning and communications, and I'm going to get back to that in a moment. So in terms of the system model, so of course in the uplink, we need the transmission rate, because we're going to look at the transmission delay. So you have the first equation on top here. You have the transmission rate, or the capacity is function of the resource blocks that you allocate to the users. It's function of the transmit power of those users. And you can see the term IN here, which is the interference from other users if they use, of course, the same resource block. And then you have the downlink transmission where also you have the same, basically, the same expression. And that we really just need those to say that we have this delay over the uplink and the downlink. And the delay is function of the packet size. and of the transmission rate. So at first glance, you might think, but the packet size you're sending a neural network, it's very tiny. That's not really true, because in some applications, the neural network can have tens of thousands of weights. And in fact, if I recall well, there has been some works on FL where it was shown that if you actually share the images, they're smaller than sharing the neural network. Of course, that's not the norm, so there are different applications. So this Z is not really small. It's not really short packet IoT type of transmission. Or of course, it could be for very small applications, but in general, it's not. So we say that the local models, when they're transmitted to the base station, they will incur transmission errors. So these transmission errors should be captured by a packet error rate. So we use a well-known expression for the packet error rate, an exponential expression. And again, the results I'm going to show later, they're a function of this Q. So you can use any other Q if you wish. So Qi is your packet success rate or packet error rate, function of the resource blocks, function of the transmit power. And again, M is basically the different values of M give you different types of channel coding that you could use. So the key point that appears is here, right? So this is where we start moving from wireless to FL, right? So, I mean, I started with training of FL, then I talked about the wireless model. I did not link them up together. And now the link will start to appear clearly. So under packet errors, the global federated learning model becomes G. It's still function of P and R, but now it's function of A. And A is whether a user is participating or not in the federated learning. And it's also function of the CW, which is essentially function of Qi. It tells me whether there's a packet error rate or not. So now your global model is function of your indicator function A, which is itself function of the wireless channel. And just for simplicity, we assume that if the packet error rate exceeds the threshold, then the base station will not use those users. You can extend that to the case where you use those users and you look at the bit error rate more like in a more continuous manner. But again, this is a simplification. Keep in mind, again, this was one of the first works in this area. We wanted to kind of simplify the model as much as we can. The problem formulation for us is now the following. We're still doing the FL training. So if you look at the objective function, it's still the same as before. We're trying to minimize basically the loss value function of the FL system itself. But the key is now we're function of this user association. We're function of the resource block allocation matrix, and we're function of the power allocation matrix. So the global model, which in a traditional FL work is usually reliable enough, now it's functions specifically and explicitly on the wireless channel. So again, I did not show the math of converting, the Qi into the CW, but that's not, it's just very small algebra, not really very fundamental. The key point is that your global model becomes function of your wireless channel very explicitly. Now, the constraints here are, the first two constraints are just feasibility constraints. So you allocate the resource block or not, you select a user or not, and you have a total number of resource blocks. And additionally, the wireless network appears in these two constraints. One is the delay constraint. I want to maintain the round trip delay uplink and downlink within a certain gamma T threshold. And I want to maintain energy efficiency. So you can see now you have this is a very classical FL training model. The key point is that we now explicitly have G function of A and P and R, and then we have the constraints on the delay and the energy. So to solve this problem, our first step was to quantify how does wireless affect the value function. And for that, we're doing some global model analysis. We have this basically theorem, which shows an upper bound on the convergence point. So here you have FG star is basically the value function at the optimal solution that we seek to achieve. FGT plus 1 is just an iteration of the federated learning algorithm. If you run this, if you actually do the math of this bound, usually you would get the second term only. The second without wireless. If you don't have wireless, you just get the second term. A is a number less than 1. If t goes to infinity, federated learning will converge. Of course, the convergence is not usually to 0 exactly. It's close to 0, which is fine. However, what this shows explicitly is that now you have a term, a first term, that is directly function of the wireless channel, which adds up to this original convergence result. So now you have this Qi, which is the packet error rate function of the resource blocks and the power, which now is affecting basically your convergence. So if the error is bad, this will be a large value. You converge to something far away from the optimal solution. And that basically quantifies the effect of wireless on FL. And this, from this slide, regardless of the math itself, you can now start thinking about what I called early on, joint learning and communication in the following sense. I am designing this FL over wireless. I mean, usually the way it's done is that someone from Google designs the federated learning algorithm, someone from AT&T designs the wireless network, and then we deploy it. What we can argue through this, again, it's a very simplistic analysis, can be extended though. We can argue that, no, we need these two people to talk and jointly design their algorithms. From the FL side, the way you do your iterations should be aware that there are wireless errors. So the way you do your training, the way you design your algorithm should be error aware or error cognizant. On the other side, the way you design your wireless network should be able to respond or to sustain a federated learning algorithm, knowing that there will be some training process. So these are these two intertwined learning and communication, where you can now, I mean, you can imagine a lot of optimization problem coming out from this result, and of course, any extensions you do to this result. And again, so we can say convergence is affected by the packet error rate and user association. And in general, that's the first observation. Now, moving back to my optimization problem, we can show, and those are in the paper, that using this, you can do some very standard optimization mapping from the original problem. And you end up having, you end up solving the problem, finding the optimal basically power and the optimal resource block allocation. So I'm not gonna go through that too much because it ends up being just a Hungarian method. So that's not really very fancy, it's just a simple optimization problem. The key was to be able to basically link wireless NFL and make sure you're able to solve that optimization problem. So here, I mean, here you can imagine other uses of ML. For example, maybe you don't have information on this problem, you can use other neural networks to solve the optimization, but we don't go there. So now we're going to optimize the wireless to serve the edge FL. So let me show you some simulations. So we used so we did some runs on the MNIST database. I'm going to show those at the end. But also for very simple analysis, we looked at this very simple linear learning task, and it's just as a means of exposition. So we're going to compare with two algorithms. One that I would call baseline B. Think of that as a standard federated learning. It's a communication unaware federated learning. And that's what I'm gonna call baseline B. Baseline A goes a step further. It does federated learning with some sort of user selection. Baseline A kind of selects which user will participate, but the resource allocation is not optimized. In some sense, baseline A is somewhat related to some of the work that Vince perhaps presented early on. So first we look at just this linear learning task. You can see that our optimal, our proposed algorithm, the blue curve, is really very convergent to an optimal FL, and this is like a Gini-aided solution where you can, you know everything, and the communication the communication errors are well known ahead of time. It's much better than baseline B, and it's much better than baseline A. So this is a very simple example to start with. Now we look at the value function. So we're minimizing the value function, but I'm gonna show the figure multiplied by -1. So you're gonna see a maximization gains. So we can see that the value of the loss function of the proposed algorithm is much better, and it becomes, I mean, much better, particularly after convergence, than both other baselines. So you can see how, because we're aware of the errors, we can do much better by designing our wireless network. And you can see this also here. So this is the global loss function. This is the global loss function versus time, and this is the global loss function versus the number of users. The more users we have, our algorithm can cope better with that because you have more input to your neural network. And you can see that we can do much better, again, in terms of the loss function. And this is an example on the MNIST database. So for every row, you have the real data. On top, you have what we obtain from our algorithm. On the bottom, you have what we obtain from FL without wireless aware. Everything in red is an error. So in the first row, I guess our approach and baseline B are pretty much the same. They have one error. Now you can see in the second row, we can, the traditional FL has one error, we have none. And you can see in general, the number of red digits are much larger for the baseline compared to ours. So this shows that the baseline is susceptible to errors. So where do we go from here? So as I mentioned, this is a kind of an entry point to this area. And what else can we do? So we looked at a different work. I'm not gonna present it in detail today. But just a quick way to what happens. I mean, there are some users that cannot participate in FL. We showed that in our work because there are errors, their channel is not good. And some others looked at that also. They said, the number of participating users is not really linear. The more you add users, that doesn't mean that you get a better FL. So, and the reason is usually communication bandwidth related. And what we did in this extension to the work is we looked a little bit more first at the delay, more than just the constraint, as I did early on. But we also used neural networks to basically predict the local models of the users that did not participate. So say a user 1 had a good channel in time slot 1. He sent his local model. But then in time slot 2, he could not participate because of a deep fade. What would the base station do in a traditional work? It would ignore that user because it just didn't receive anything from it, right? What we do instead is we actually predict what would the model of that user look like in the next step. And by using neural networks with some training over time, they become very well apt at predicting that. So this work kind of combines the two aspects of federated learning. One is, here we do distributed learning over wireless. And second is using learning to improve basically that. So that's a nice kind of combination of it. So some concluding remarks on this first half of the presentation before I move to the GAN part. So wireless networks will have to support federated learning and other learning tasks. The question is, at least in this presentation, is what can 6G or other wireless network do for FL rather than the reverse, which we kind of know more about. So we cannot give a direct answer, but we can say we need reliability and low latency because you could see that errors are problematic for FL. So this URLLC paradigm should be extended to look more at this type of FL problems. And we need this sort of joint FL and wireless designs. And I guess I gave a very concrete example on that early on. How can we jointly model both the federated learning performance and the wireless network performance? Keep in mind that the model I presented did not consider other users, right? But in an actual network, you'd have a number of users doing federated learning and a number of users watching Netflix. There is an intersection between the two. They share the same resources. So this kind of coexistence, say, of URLC type FL models with basically eMBB type smartphones is an interesting idea to look at. So the next question we asked as we were working on this area is, well, federated learning, if you look at it, it's always looking at inference model, usually classification or some sort of inference task like this keyboard recognition. But in the same time, as you know, one of the bigger fields recently in ML is this field of generative adversarial networks, or more generally, generative learning, basically generating data from a given distribution, learning a distribution and generating data from that distribution. So this brings me to the second part of the presentation, which we call brainstorming generative adversarial networks. The idea is simple, that we have GANs, they're very famous, but GANs in 90% of the existing literature, they are centralized schemes. What if I have a multi-agent GAN model, or and more generally, a multi-agent generative model? So a couple of quick introductions. I'm sure the audience, you took this course and probably others, so you probably know what a generative model is, but just a couple of slides to get you started with this problem. So the generative approach and the discriminative approach, which is more the inference approach, is a little bit different. Let's say you have an observable variable, random variable X, and you have an output Y, or what we call the target variable. In a generative, in a generative model, we're trying to model the joint probability distribution of X multiplied by Y. Basically, we're trying to find the joint probability distribution of the observable variable and the output. We're trying to generate an output. In English, we're trying to generate fake data from a distribution. The discriminative model, on the other hand, is trying to infer whether a certain point does belong to a distribution or not, given an observation. Now, the beauty of a GAN is that it is a generative model, of course, but it combines the two in it. Now, in the literature, there has been other generative models in the past, the simplest being mixture models. I'm sure everybody is familiar with them. And then there was Bayesian network models. Also, they're very simplistic. But the next step was variational autoencoders, which are also generative models, but they suffer from a lot of problems, from disentanglement to others. And autoencoders had been a little bit popular in wireless, looking at the physical layer. Now, GANs are a little bit beyond these three, and they somewhat look something like this. So simply put, a generative model like GAN tries to find the data that is not seen before, but it fits an input distribution that is trying to learn. So the GAN has two components, a generator and a discriminator. The generator tries to basically generate fake data. The discriminator tries to tell whether it's fake or not. And it is called adversarial because these two will play a game among them, a zero-sum game. And then Ian Goodfellow showed that there is a solution for that game and so on. So he showed that you can use GANs to generate fake data. The biggest example being generating fake celebrity data, doing some of the deep fakes videos and so on. So This is the standard GAN. The thing is, all these GAN implementation, they're usually done in the way that you have one big cloud or a big device that has both the generator and discriminator and has access to all the data. And then he can do the training and run the GAN. However, the question we ask is, can we look at distributed GANs? Can we look at a case where the data of interest is, one, distributed among multiple agents, two, it is private, so the agents do not want to share that data, just like in the federated learning case, and three, it is scarce in the following sense. Remember that in GAN, what you want to do is generate a distribution, right? And generate fake data eventually. And this distribution, let's say the celebrity photos example, everyone maybe has some celebrity photos. Like for example, maybe I have a few female celebrities. Another user has a few male celebrities. Some other user has American celebrities and another has European celebrities. But we want to generate celebrities in general. So we have partial data. That's what I mean by scarce or partial here. We have partial data, but what we want to learn is actually a distribution of celebrity photos. We want to generate any type of celebrity photos. How can we do that? It is not possible with a standard GAN unless all these users share the data with a centralized entity, which has privacy, communication, and other basically implications. So the question we asked, the fundamental question of this paper is, can we learn the distribution of the total data without sharing the private data? In some sense, can we do a federated learning for GAN? So if you look at the literature, there is very, very little work, but there are some competitors for us. I want to mention them. These are the only ones I'm aware of. So there has been a work called federated GAN, basically, federated learning GAN. And the idea in FLGAN is that every user will have his own generator and discriminator. So these are the agents here. And there will be a control center which has a generator and a discriminator. And as is the case in federated learning, they would share this neural network models, and they do some sort of GAN among them. The problem with this application is that this is not distributed. It still needs a centralized center. And the centralized center should have a generator and a discriminator. So this is not a great application for an actual real-world GAN where it's fully distributed. The other two competitors are somewhat similar. They're called MD-GAN and F2U GAN. MD-GAN is more general than F2U GAN. So MD-GAN has basically in the workers, you have discriminators only. So you don't have your own ability to generate fake data. You cannot do that. You have, once again, to rely on a central server. So the problem with MD-GAN is that you cannot basically generate your own data. And in some cases here, you don't have a generator. And also, you have to rely on a central server. So it's distributed, but not fully. Now, F2U GAN is just a special case of MD-GAN where the workers don't exchange. So in the figure, you can see these green lines where the workers exchange their neural network models. On the other hand, in F2U GAN, they don't. So you have a generator here, discriminators, but no communication among workers. So what is the drawback of these papers? I mentioned one already. It's not fully distributed, right? So there is no, to my knowledge, there is no fully distributed GAN implementation. And they have expensive communication requirements, especially if you think about MD-GAN and F2U GAN. You have to send a lot of these basically neural network models among you with a central server and wait and so on. It's really heavy. And agents cannot have different neural network architecture. So you cannot have a different architecture here. They have to have the exact same architecture. So it cannot be heterogeneous. And the agents do not own their own generators when we talk about MD-GAN and F2U GAN. FLGAN they do, but in MD-GAN and F2U GAN they don't. So you have these drawbacks. So the question we ask is, can we create a fully distributed solution, no central server, with multiple heterogeneous agents and with improvement in communication and computing as well? And the answer is yes. So we came up with the idea of brainstorming GAN. The idea is very simple. If you think about GAN among multiple agents, everyone is generating data. These data are basically ideas, right? And if you think about the human case, if you kind of come up with a lot of ideas, unless you speak with others, you cannot really drill down your ideas. So brainstorming works very well when people do it. So we thought, can GAN agents do it? And the idea here for us, what is the brainstorming? Brainstorming, you exchange ideas. In our GAN model, the idea is nothing but the fake data. So this is a very interesting idea because first, I'm not exchanging the neural network models anymore, which as I mentioned, could be huge. I'm exchanging only the fake data, which is not private. And as I'm gonna show at the end, compared to the literature, it's much less computationally heavy, except for a case with FLGAN, I'm gonna talk about it later. But so now what I'm doing is I'm generating fake data, exchanging it. So it's not private, but it comes from the distribution I wanna learn. And I'm allowing every agent to have its own generator and discriminator. It's fully distributed, no central server, no base station, and you have your private generator, your private discriminator. You only send your fake data. You only send the generated output to the other agents. And these agents together should be able to brainstorm these data points to come up with a final distribution that they can use to generate in a distributed way their fake data, or even to use them for inference models if you wish. So the benefits of brainstorming GAN is the following. It's fully distributed. Its communication load depends on the dimensions of the data point rather than the neural network parameters. And as I mentioned, that will be shown later to be much better, especially than MD-GAN and FTU GAN. And agents can have different neural network. You can use any neural network architecture. So the number of layers don't have to be the same. The type of neural network doesn't have to be the same. None of that is required for our application. So first, theoretically, how did we study? So I will now go into the theoretical results on this brainstorming GAN, and then there's a lot of experimental results which are very interesting, as is the case in this machine learning cases. Keep in mind, though, I did not touch upon wireless, but these connections are wireless. So there's a lot of things, there's a rich set of problems you can look at by looking at the wireless angle here. We have some assumptions. I'm going to talk about them in the experiments later. So theoretically, what is the brainstorming GAN? So in a regular GAN, you usually have a value function like this that depends on the discriminator, the generator, and it has a first term that is being maximized by the discriminator. So the discriminator is trying to maximize its ability to basically identify real data. The second term is the generator, which is trying to minimize this so that basically you're trying to make sure that what you generate is fake and still can be undistinguishable by the discriminator. So usually in a traditional GAN, in Goodfellow's paper, you have this term and this term. They're the same as in my equation here. And the discriminator is trying to maximize this value function, and the generator is trying to minimize it. And basically what Goodfellow showed is that this is a game theoretic problem, a zero-sum game, and you can find a Nash equilibrium. We have a key difference here. We have this GJ, which is basically the generated data, the fake data you received from your neighbor. So although the equation has the same structure as the one proposed by Goodfellow, we have this different GJ, which comes into play here in PBI. So PBI is a mixture of your own data and the data of your neighbors. And the rest is, follows Goodfellow basically. So the generator is trying to minimize, the discriminator is trying to maximize. And the key point here is you depend, so you have multiple optimization problems that depend among each other. So the optimization problem of agent 1 depends on agent 2, depends on agent 3. Whenever you have this series of multi-agent optimization problems, you have to, there's no way to solve it without using game theory. And that's essentially the tool we use here. Just similar to the work of Goodfellow, but we have multiple agents, not a single agent. So using some just reformulation, we can formulate the problem as a minimax problem, where this is the total utility of the agents. And the question is there a solution? So can we find the discriminator distribution, the generator distribution that solves this game, which is now among multiple GAN agents? Can we find a Nash equilibrium? And the answer is yes. We first show an intermediary result. We find the optimal discrimination distribution. And interestingly enough, it's a very simple distribution. It's function of the distribution of your own generator and the mixture of data that I explained in the previous slide. So using this result and another, we show that the game between agents has a unique Nash equilibrium. So you have a solution, and this is very strong result because it generalizes what basically Goodfellow did for a single agent to multiple agents. And this solution is actually very tractable. You can find the distribution of your generator. You can find P star GI as function of the real data and a lambda parameter, which you can basically tweak up. Okay, so this is the distribution of your real data. This is a lambda that depends on the communication graph, and COM theorists can work a lot on this lambda. So here we assume that you have some graph that connects the agents. We did not go much beyond that. So let me go to the experimental setup. So we assume that the communication graph is something like this. Every agent has one neighbor. It's basically a ring topology. You can use, again, others. And this is called the strongly connected because every user has a path that reaches it from another user. So we wanted a strongly connected graph because it makes some of our results simpler. And for exposition purposes, we basically use this type of data. We wanted to say, okay, we have multiple agents. Their ultimate goal is to basically learn a ring data, right? So they're trying to learn a circle, a certain ring data. And in some sense, this is basically a nonlinear combination of a gamma and uniform distribution. It's called the ring dataset. The idea, I mean, why we started with this ring is just because it's very simple to explain. So the idea was very simple at the beginning. We said, what if every one of the agents knows a quadrant of this circle? So one agent knows the upper right part, one agent knows the upper left, one agent knows the lower left, and one agent knows the lower right. Can they figure out the circle by doing this brainstorming GAN? Can they brainstorm together and figure out, well, the distribution we're looking at is a circle? So we're gonna elaborate more on this in the simulation result. So this is the first result. First, we use the GSD, which is a form of basically a distance metric between two distributions. And the lower the GSD, so if you're not familiar with it, you're probably familiar with the KL divergence distance. It's very similar to that. So the GSD is basically the difference between the fake data distribution and the real distribution, the baseline, basically the real world, the real data. And we're doing it here versus the number of available samples. You can see it on this x-axis here, and the y-axis here shows the number of agents. Notice that this special case where you have one agent is the classical GAN. You have one agent, there's no other agent. If the one agent has 100, or in this case, 1,000 data samples, then this agent is the perfect one. A one agent with 1,000 data samples in our experiments knows everything, can generate the circle perfectly. But the problem is a single agent may not know 1,000 data samples, and a single agent may need to communicate with others. This is why this figure is very useful. You can see, like, for example, if you want 2 users and each has only 10 data points, you see like this back of this figure. If you want to have like 9 users here, keep in mind the number of agents is the neighbors. So when I say 9, it means you have 10 users because every agent has 9 neighbors in some sense. Okay, so 9 is really 10 agents. So if you have like 9 neighbors, 10 agents, and you have 10 each, then 10 times 10 is 100, and you can still do much better than if you have a standalone agent, one with a 10, with basically 10 points. So this is the idea. You might have a single GAN agent. If he doesn't brainstorm, his performance will not be good unless he has all the data samples, which we argue in practical applications like IoT and medical problems, it's not true, right? So you don't have the whole data. So the idea is BGAN can compensate the lack of data through brainstorming. For example, a GAN with 10 samples has a GSD of 24. This is actually the one here at the peak. While 10 agents who have 10 samples each, I know they have more samples, but the idea is to show whether having more samples distributed can work, has a much better GSD. It's even almost the half of that. And here you can see, we see the what do my BGAN agent generate? So the first column is a standalone agent, the baseline classical GAN. Second column is BGAN with 5 agents. Last column is BGAN with 10 agents. Here I'm assuming every agent had 1,000 samples, 500, 100, 50, and 10. You can see that a standalone with 10 samples is not great at all. It's a little bit better with BGAN, but still not great, right? Because even for 10 agents, 10 samples each, it's 100 samples. So you still don't get to the circle you want. But you can see how BGAN becomes much better when you have more samples per agent. And the idea here is, again, to show that you can brainstorm instead of relying on your own data only. And this is very, very commonly used in a distributed network. The next experiment, we show again, the Jensen-Shannon divergence, the GSD, versus the number of neighbors and the number of samples. You can see that when the number of samples is small, you have a lot of gains from brainstorming. So you can see when you have more neighbors, like the blue curve, you gain a lot from brainstorming. Even when you have 20, you gain a lot from brainstorming. But naturally, if each agent already has a lot of samples, like 100 or 1,000, the gains are a little bit smaller, right? So if you have everything, you don't need to brainstorm, and that kind of makes sense. And then on the right-hand side, I run a case where I have different, so here I have agents having different neural networks. You can see agent 1 has 723 neurons. This agent has 2,467 neurons. So they have different neural networks structured. And in this case, we change the number of neurons, but you can also change the type of the neuron. You can see that, well, standalone agents, they don't really do well as well as brainstorming GAN when you have different neural network architectures. So even in a standalone GAN, you cannot even implement that. It doesn't make sense to implement that in, FL GAN, not standalone. In a standalone GAN, you don't have a problem of different neural networks because you have one neural network. But if you compare your approach to FL GAN, in FL GAN, you simply cannot do it. So this is why I don't compare with it. In FL GAN, this will actually fail. You cannot do this brainstorming. And brainstorming GAN, you can get as good as the standalone agent, and that's the point I wanted to make. And then what happens if the agents have partial data? Remember the example I gave at the beginning. What if I know part of the circle, you know part of the circle? Can we brainstorm a circle together without sharing our thoughts, by sharing just some description of the thoughts? And the idea is, yes, we take this case where agent 1 has half of the circle, agent 2 has half of the circle, and they are able to generate the full circle. And we also generate it with MNIST. We assume every agent owns a digit. Agent 1 owns digit 0, digit 1, digit 2, digit 3, and so on. You can see that the agent who owns digit 0 was able to generate 1. The agent who owns digit 2 was able to generate 2. The agent who owns digit 2 was able to generate 3. The agent who owns digit 3 was able to generate 4, and so on and so forth. Keep in mind here, it's because my graph is a single neighbor graph. That's why you don't generate more than 1 extra digit, but you can extend that as well. And then we compare with BGAN with FLGAN, MDGAN, and FTU GAN. On the ring data set, you can see it here. We are significantly better than all of them in terms of the JSD divergence. We're significantly much better. We're not too far from the ideal case where you know the entire data. And you can see the comparison between, again, BGAN, FLGAN, MDGAN, and there's a typo here, but that's okay, and F2U on the MNIST data set. And you can see also on the MNIST, we do much, much better than the others, and we're much more stable. So you can see the average, we use the FID here, and the average FID is much more stable than the others. And in terms of complexity, so I mentioned that, and that's basically the last piece of this work. So what do we know about the complexity? The complexity of BGAN is proportional to NBX. B is the batch size, N is the number of agents, and the cardinality of X is the data size. So BGAN is much better clearly than MDGAN, because you can see that MDGAN has NBX plus this term. And BGAN is also much better than F2U, because F2U has NBX plus N. Now, between BGAN and FLGAN, the idea, it's not clear. It really depends on the neural network size. Whenever NBX is greater than the neural network size, basically these two thetas, then you would be worse than FLGAN. Whenever it's less, you would be better. That really is the case depending on the application a lot. But you can see that in terms of compared to the other distributions or distributed GANs, we're much better. And also compared to FLGAN, there are things we can do that they cannot. One is fully distributed. Two is we can use different neural network architectures. They cannot do that anyways. So in conclusion, we showed that a fully distributed neural network architecture independent GAN can be possible. And what can we do with it next, right? So what is the next few ideas we can do? We can use the distributed discriminator for inference. I'm sure many of you saw works on GAN where they use the discriminator as a way to infer rather than generate data, basically a classifier. Here you can use a distributed classifier, and that's kind of interesting. It can have wireless applications, it can have other applications as well. You can look at more sophisticated wireless networks and graphs. I mean, this graph we looked at, a ring graph, it's very simple, and you can look at other things. You can apply BGAN to wireless networks. You can think of problem from physical layer to resource allocation to vehicular networking. So we haven't done that, but we thought of different problems as well. You can apply it to security. We've done some work in IoT where we use a form of BGAN to do intrusion detection. And in the original model, I have something called PBI, which I said is a mixture of your data with the data of others. We used a very simple weighted sum, but you can use others, and it changes a little bit the results. So I'm going to now conclude with just a brief overview on other works I thought they're relevant to this audience and our bigger group work, and then I'll conclude. So there's one problem which I think it came through a little bit in the panel, but that was before I left, where we thought about in wireless, one of the biggest problem is there is a lack of data, right? So data is very sparse. And when you think about applying, let's say, deep reinforcement learning to a problem where you have reliability issues, right? And Petar talked about a little bit reliability. You have a problem where you want to make sure that you respond to deep fades, you respond to surge in traffic. How do you do that? If you deploy a traditional deep RL algorithm, even if you train it offline, you have very little data to train it, and when you deploy it, it will encounter some extreme events it hasn't seen before. So what we came up with in this work is we tried to answer this question: can we train an RL algorithm for rare and extreme events, which are relevant particularly for reliable low latency communication? And the answer was yes. The idea is to combine GAN and RL together. And this is how we do it. So the idea is, look at this upper figure on eyes, and this is a work from Apple, which we kind of adapted to our own. It's called the Refiner GAN. In this Apple work, they had images, a limited, very limited set of unlabeled real images of eyes looking in different directions. What they wanted to do is they wanted to generate more eyes that look in many other directions. So they have a limited data set, and they had an ability to do some synthetic simulated data. So what they did here is they used something called the refiner GAN to combine a real data set with a synthetic data set to combine to generate special cases. For example, an eye looking to the bottom, or an eye looking at the corner of its vision. So we looked at the same idea. We looked at a resource allocation problem. We were trying to do power allocation in the downlink for like vehicular network type of reliable low latency communication. And we said that, well, we have some data. We found some data online, but it's very limited. This data was about packet arrivals and channel information. But at the same time, we know that, okay, we know that there are some models that are well known for wireless, like Poisson arrivals and so on, that we can use to generate a lot of data. But the problem with these models is that they usually don't comply to the real data. What we did is we got this refiner GAN, and we took as input the synthetic data, which we use based on standard models, the real data. And what we do is that through this refiner GAN, we can actually generate special cases that are simulated, but they are also compliant with the real data. For example, in the real data, we had some very rare events that happened related to a very high traffic surge, a high increase in the packet size. So we can find that through this synthetic data plus the real data, we can generate all these extra examples. Think about it as experience. If you use only the real data to train your DeepRL agent, you have very little experience. You will see a certain packet arrival you don't know. You can recover, but you'll take a lot of time. And if you have only simulated model, you have experience in, like, let's say, compare academia and industry, right? So people say that in academia, we don't have experience in the real world. So you have this simulated data. It's good, but it's not close to the real world. So let's say you have this simulated data and real data. Using this GAN refiner, we create an experience for you that is related to both the real world and the simulated data. It has the properties of the real world and the controllability of the simulated data, because simulated data is abundant, right? So think of academic freedom versus industry, right? You have a lot of freedom to generate this data. And then we train the DeepRL agent in this GAN. So instead of training it over real data or over simulated data, we train it with the GAN. This is why we call it an experienced DeepRL. And the application was primarily to do reliable low latency communication, but it can be extended. And to show you an interesting result, so this is, look at these two figures. And we have a vanilla DeepRL algorithm and our experienced agent. First, you can see that our proposed experience agent converge much faster to the final solution, while the other has to fluctuate. Although the two, they converge to the same solution, so we don't have performance benefit in terms of, let's say, in this case, we were looking at the network, at minimizing energy. It's not better, but it converges much faster, much more smoother. And this is the more interesting side. It's the second result. At epoch 50, what we do is we insert a packet surge. The vanilla DeepRL agent struggles. It will go into a transient phase. It's unreliable here. It eventually copes, but it's very unreliable. But the experienced agent just gets a little bit of a problems here, but he recovers much more faster. And this is kind of like a motivation for this experience. And another very quick work I mentioned at the beginning, this is related more to FL. How do you use federated learning for wireless rather than the reverse? One good application is resource allocation, let's say for VR, because in VR, you need to take information from the user, like their orientation, their mobility, and this information is private. So how can you use federated learning to do predictions and then feed that into wireless? And we looked at it in this context. And the idea was to basically reduce the amount of breaks in presence, meaning how often can you make sure that the immersive experience is smooth? So you don't know, as a user of VR, you don't know because of a packet error that you are in a virtual experience. You know that you think that you are in a virtual experience all the time. You don't realize that you're in the real world. So it's kind of a quality of experience idea. And the idea here is we kind of put together a recurrent neural network. It's not deep, actually, a very simple one called EcoState Network with federated learning to do this type of prediction. Now, finally, just a conclusion, what does my group do? Because we do a lot of things. We have a bit of a wide band areas of research. So within the space of 5G, 6G, IoT, whatever you want to call it, we've been focused quite a bit on reliable low latency communication, not in the sense of uplink IoT as was done by many others, but more in the sense of VR and this type of applications where you need high rate, but also some sort of reliability. And we've been looking at terahertz as a means to provide this. I mean, if you think about it, basically millimeter wave and terahertz, one of the issues that's still a problem for 5G now is that they're not reliable. They're really good in terms of bandwidth, but can we guarantee reliable and continuously high bandwidth? And this is something we've been looking at. In the AI-enabled wireless, I think I talked a lot already on this. We have a lot of work being done on drones, all sorts of applications from communication to security. And we've been focused a little bit on reliable learning. So this is a little bit different, somewhat inspired from this experienced DeepRL. The idea is, can machine learning be reliable? And can machine learning forego training? So we're looking at things like this synthetic data, but also at meta learning to get rid of as much as possible. Of course, it's never going to be training free per se, but as much as possible that. And of course, distributed learning, meaning the FL side of the coin that I discussed before. We've been also looking at issues of human aware wireless. So what if your brain or your input from your physiology should be fed into the wireless network? What happens and how do you look at that? We have a project ongoing on age of information, which I think many of you know from the information theory perspective, but we're looking at it more from a networking perspective, and along with some big data for smart cities, and of course game theory, which is a central theme in our group for a long time. So that's just a quick overview of what we're doing. And as a conclusion, first, distributed learning is an immensely exciting area, especially when you merge it with wireless. I mean, I could not cover enough in this talk to say how much interesting stuff you can look at. We were talking in the panel whether it's going to have impact or not. We really don't know now, but I think there are interesting problems to solve. And when you solve them, you would know whether they're going to be practical or whatever else you're going to look at there. And distributed learning, just wanted to make sure that it's not just federated learning. So I know that you had a couple of talks already today on federated learning over wireless, which is why I wanted to kind of delve into a bit more the GAN part, which is one example of that. And this idea of extreme trained deep learning, I think, is an important area with very little work being done. Particularly, it's not very heavily looked upon in the machine learning literature, because when they're doing computer vision, they don't have these extreme conditions that we get in wireless. But when you look at wireless networks, it's different. So there's an exciting kind of world here where you can look at confluence of wireless learning, control, computing, and many other things. And this idea of joint design that I talked about early on is also of interest. And that's the final slide. Thank you. And I'm happy to take questions.
Thanks a lot, Walid, for the very exciting presentation. So if anyone has any question, you may raise your hand or ask in Q&A. I can see Balaji, so let me see. So now you can unmute yourself, Balaji, and ask your question. Balaji, can you hear me? I can unmute you now. Carlo, I saw that you unmuted yourself, so maybe you can just go first until Balaji can handle.
Yes. Thank you, Walid, for this fantastic talk. It was a very large and deep, at the same time, overview of many exciting topics. And I have just a curiosity on, I think it was the second last topic, when you have the multi-agents.
Yes.
And you mentioned that that an essential approach is to use game theory to characterize an equilibrium, and that it was difficult to use an optimization approach instead.
Yeah, let me clarify that. So it's so essentially the idea is you would have every agent. Let me share back the screen. I actually stopped sharing because I thought I was disconnected, so I wanted to make sure I'm still active. This is here. So the idea is what you have. So if you, where is the theory? Here. So in a traditional GAN, you have usually this V with D and G. You don't have this GG. And what they do is they assume you have the discriminator trying to maximize and the generator trying to minimize. This ends up being a maximum problem, which is by definition a game. It's a zero-sum game between two agents. One is the discriminator and the second is the generator. I mean, by definition, you might use optimization techniques to solve it, but the solution is what we call a saddle point equilibrium or a Nash equilibrium. Now, the difference in our case is we also have this GJ. So now we have every agent trying to find his own DNJ. So it's still a game, but it's a game with multiple agents. Every agent is trying to do the min-max of this V, or if you wish, it's really his individual VI. So you have a set of n optimization problem, everyone trying to find his own, but the optimization of agent I depends on the optimization of agent J because of this GJ here. And by really formally by definition, this is a game theoretic setting because you have coupled actions or coupled utility functions. Then you can use, of course, you can use some optimization tools, but what you characterize is a fixed point of these n equations, and that fixed point is called the Nash equilibrium. And in this case, it is unique.
Right, I understand. Okay, yeah. Very good, and thank you. That's no, exactly was my little doubt. And then my further question here is, could you elaborate a little bit more on the role of communications?
In general or in this one specific?
In this specific context, yes.
Okay, so the role of communication is what is the data you receive, right? So how are you connected? What is the shape of the network connectivity? So what we assume here in this this work is that you have you have what we call a strongly connected graph, which means you have a path between any two nodes, and the ring is an example. But the way when you change that, this PBI here, this PBI that I have here, which is the mixture of the data you have, will be changed because it depends where you get this fake data from, who's brainstorming with you, how good is the quality of that over the wireless. We don't assume that here. We assume that we just look really at a binary connectivity network. So our results will still hold even if you're not strongly connected. That still holds. But the way the quality of the data will be different depending on how many are connected to you, depending on how good the wireless is. So we don't touch at all at that. We assume that you have a graph of connectivity. In the simulations, we use the ring graph. In the theory, we don't need an assumption, but we assume it's perfect communication, no bandwidth, nothing issued, nothing there. On the flip side of the coin, GAN has a lot of applications in wireless, and brainstorming GAN is distributed with private data, so you can think of a lot of applications. From caching, you know, I have different users' information to other applications.
Thank you. I see that Balai is probably ready to ask a question.
I'm not sure. Can you ask Balaji? If not, I can see Petar has raised his hand, so you may ask.
Yeah. Thank you, Valid, for the very nice presentation. Just back to this concept of brainstorming. So you're saying that you're using the fake data, you're transferring the fake data to the others, right?
Yeah.
But the fake data has certain privacy leakage, right? Because it does reflect the distribution at the source. Have you quantified that?
So that's a great question. It does not, I mean, so that is an issue not really specific to BGAN, but rather specific to GANs in general. So whether you use a standalone GAN or use multiple agents, when you have the fake data, there could be a possibility to reverse engineering to get back the real data. But that's also true for the neural network. If you have the neural network model, there is a possibility to do that. So I think that's an interesting security problem, which we've been thinking about. We haven't done much of it. The idea is essentially, even for the simplest GAN, the standard GAN, if you know the fake celebrity data, can you reverse back and find the original distribution? There are some works, but I haven't seen much done there. But it's not a unique feature of our work. It's just a feature of GAN in general.
No, but the thing is that, for example, if you take the very basic question of this is that, let's say that I know the distribution of your data. How much do I know about your data? So that will depend on the basically entropy of the distribution and so on, right? So the point is here that I can know more, and maybe Dennis can correct me here, I can know more about your data based on the setup that you have, because I will see what is the knowledge that I'm getting from your data. So basically from your distribution, and that is more knowledge than just looking at the distribution of the data. You see my point?
True. Yeah, no, definitely, I agree with that. So you can, I mean, you can use that to, let's say, if you're trying to figure out what he has, you can use that to get more into the privacy. But essentially, it's definitely better than sharing the actual data, and it's of course better than, or it's similar, let's say, to sharing the neural network model.
Yeah, of course.
So so I agree there is still a privacy issue, but what I was trying to convey is that this is a privacy issue of that relate to GAN and distributed machine learning in general, not specifically because we use it.
No, but, I mean,
but we haven't looked at it. Yeah, I haven't.
The best way to mask your data, there's no better way than randomly sampling the same distribution. So while preserving the distribution, there's no other way, because if you don't do that, you will change the distribution, which you don't want to do.
And in some sense, this is what you do when you send the fake data, right? Because the fake data are just generated data, which are the best knowledge you have. It's not like it's not a structured data, right? But mathematically modeling that is a very good problem. I mean, we've discussed it, but I have never looked at it before.
Okay, thanks.
Okay, any more questions? So if not, maybe I can ask the last question. So, and actually that goes back to the joint paper that you had with Vince on the scheduling part, actually.
Yes.
So coming back to the presentation of Vince, actually, so there you had 3 different schedulers, like the random scheduler.
Let me be clear, that paper is different.
I know. Yeah, I know. But I guess that is a little bit related also to these kind of learning setups. So it's not really, the question is not really about that specific paper, but in general, more about the importance of scheduling, let's say. So in distributed optimization, there is a very huge literature, let's say, on importance sampling, which essentially says that if you are talking about different workers, then how you would take samples from those different workers. So in a stochastic gradient descent, you randomly pick from them, one of them, let's say, and then update. But then, of course, it's not optimal. You can just assign some probability distribution for sampling and then try to optimize over that. And then we may view in communication systems and networking, we may view at that probabilistic sampling as like a probabilistic scheduling, to say that these set of nodes, or we allow these nodes to transmit with these probabilities, something like that. So do you have any idea on that, or have you thought about that? Rather than having like a deterministic setup where you say that these nodes in the federated learning should transmit.
Sure, definitely. So yeah, the extension which I had just a slide on is where we use the stochastic gradient descent. So the one we had, the one I presented was a fully gradient descent. You can add this stochastic gradient descent. It changes it does change the optimization problem. So the optimization problem we have is not universal, in the sense that when you change the gradient descent type, depending on how you sample, it will be different. So you have to redesign it. But what I wanted to say is, depending on what gradient descent you use for your FL, you can revisit the problem again. And that's why the area is kind of rich, right? So you can, if you change the way FL works, you have to revisit the results. So we looked at stochastic gradient descent, but not beyond that.
Okay. I can see one Q&A. Maybe that could be like the last question that we have. So the question reads as follows. In BGAN, every agent had to share their fake data with others. So is the communication link quality between any 2 agents going to affect the overall performance of BGAN?
Yes, it would. We assume communication is good, but if you look at we have this PBI. PBI is a mixture of your own data and the data you received from the others. If there are other errors, there will be some discrepancy. But we assumed like it's received successfully.
Okay, I hope that answers the question, which it does. So thanks a lot, Walid. And if there is no more questions, maybe we can just close these sessions. And thank you again, Walid, all the panelists and all the attendees. So we close today, and tomorrow we continue with the program with special topics. Thanks a lot, and take care for today.
Thank you. Bye.
Thank you. Bye-bye.